I will first start with an introduction. What is Kubernetes? Kubernetes is an open source orchestration system for Docker containers. It lets you schedule containers on a cluster of machines. You can run multiple containers on one machine, and those machines then make up the cluster. You can run long-running services like web applications on your Kubernetes cluster. Kubernetes will manage the state of these containers. You can start a container on a specific node, and Kubernetes will restart a container when it gets killed. It can also move containers from one node to another node. For instance, if you're going to do maintenance on one node, Kubernetes can take all the containers from one node and move them to the other nodes. Instead of just running a few Docker containers on one host manually, because that's what you would do if you wouldn't have Kubernetes, Kubernetes is a platform that will manage the containers for you. Kubernetes clusters can start with one node and can go up to thousands of nodes. Some other popular Docker orchestrators are Docker Swarm, which comes with Docker by default, but isn't as extensive as Kubernetes, and Mesos, which also supports Docker containers, but it was built to run any type of workload. Docker is just one of them. This course will be about Kubernetes, which is in the same category as those two. You can run Kubernetes anywhere. On-premise, in your own data center, public, on the Google Cloud, on AWS, maybe on other clouds, or in a hybrid way. You can run it public and private. Some of your workloads you might want to keep on-premise, so you might run them privately, and other workloads you might run them on the public cloud. So you can have the same system, the same abstraction on the public cloud as on private, which is very powerful. It is highly modular, so you can make changes if necessary. It is open source. The project is on GitHub. You can easily make changes, and they encourage everyone who wants to join the community. You can make changes, which makes it a great community, and it's also backed by Google. So when they did the original release, it was actually written by Google employees, and they are still supporting it. So it's backed by Google, and it incorporates all the good stuff that Google already does for decades. Google already runs containerized applications for more than 10 years, using their own system, Borg it's called, and now they incorporated those ideas in Kubernetes that they then released to the community. Now that I gave you an introduction to Kubernetes, let me just talk a little bit about containers in general. If you already are familiar with containers, you can just skip this lecture and continue with the next one. So let's first talk a little bit about the difference between a virtual machine and a container. On the left here, you see what a virtual machine is. You have a server, the physical machine, then on that physical machine you put a host OS, here in green. Then you have the hypervisor, which is going to manage the guest OS operating systems for you. So you can have multiple guest operating systems on one host operating system using this hypervisor. Every guest operation is completely isolated. It has its own binaries, its own libraries. It can run applications. It is pretty heavy. Like a full virtual machine is a full operating system with the binaries, the libraries, and the application bundled. And it also takes some time to boot up. It needs to go through the whole boot cycle, which can take minutes before your guest operating system is live. So that brings us to containers. So here on the right, you see what a container is. You have still the physical server, then you have a host operating system, and then you can have multiple containers on your host operating system using the Docker engine. Docker is just one example of software that is available. There is other software available for containers as well. Here we have 3 containers. The containers contain binaries and libraries with applications in them. They don't need to boot up the full guest operating system. So when you launch a container, instead of waiting minutes, it will almost instantly start your container. So it's a lot more lightweight than the virtual machines. Containers can also be a couple of megabytes, where virtual machines are often a lot bigger. Then containers on cloud providers are still a little bit different than just running a container on a host operating system, because cloud providers still use this hypervisor to isolate the customers from each other. So you still have a server, a host operating system, a hypervisor, then you have a guest operating system, and on top of that you have containers. Currently that's just how it is, but you will still get all the benefits of containerization even on cloud. You just have this extra abstraction layer between your containers and the host operating system. On cloud providers, you're typically also going to have multiple guest operating systems running then multiple containers, and those nodes together will then form your cluster where you're going to run containers on. Docker is the most popular container software. There are alternatives available. An alternative to Docker is Rocket, which also works with Kubernetes. If you don't want to use Docker, you can use Rocket instead. Docker consists of Docker Engine. It's a Docker runtime. It's a software to make run the Docker images. And also the software that you will use to build those Docker images to then run on your Kubernetes cluster. You also have Docker Hub, which is an online service to store and fetch Docker images. So once you build an image with Docker Engine, you can then store it on the internet using Docker Hub. You have public repositories and you have private repositories where you can store your Docker images. Docker Hub also allows you to build those Docker images online. So they provide a service to you that you don't have to build them on your PC. You can also build them online. The cloud providers itself also have alternatives to Docker Hub. For instance, AWS has its own repository where you can save your Docker images. You can also run your own Docker Hub. You could run your own repository if you would like to. So what are the benefits of Docker? You have isolation. You ship a binary with all the dependencies. No more, it works on my machine, but not in production. It's the same binary that you use on your machine to test your software that you will be then using in production. So there is a closer parity between dev, QA, and production environments because you are using the same binary. Docker makes development teams able to ship faster. We can build images pretty quick. You can then distribute them pretty easily using Docker Hub or another registry, and then your servers can start pulling those images. This would be a lot more cumbersome with virtual machine images than with container images. You can run the same Docker image unchanged on laptops, data center VMs, and cloud providers. So you can have the same image that you run on-premise and in the cloud, and it should act exactly the same. Docker uses Linux containers, which is a kernel feature for operating system level isolation. The reason why containers cannot go to the host system or to other containers, or you don't see information of other containers, is because of this isolation done on a kernel level. If you have read already something about containers, you probably have seen this analogy already. It's a ship with containers on. So basically with containerization, you just build your container, and in that exactly same state, you can run it wherever you want. The container contains all the dependencies, so it should execute exactly the same, whether you run it locally, in the cloud, on Kubernetes, or anywhere you want to run it. And that is the main advantage of using containers. In this lecture, I'll be talking about the Kubernetes setup. I'll first talk about the different ways of setting up Kubernetes. Then I will show you how to set it up locally and on AWS. Kubernetes should really be able to run anywhere, but there are more integrations for certain cloud providers like AWS and Google Cloud. Things like volumes and external load balancers work only with supported cloud platforms. So if the integration for your cloud platform is not available, then you can still use Kubernetes, but you will not be able to use volumes and external load balancers. For AWS and Google Cloud, this is available. Also for Azure, this is available. So for the main providers, this is already available. Other providers have different types of support. You'll have to take a look in the documentation at the cloud provider plugins to see which ones are supported. I will first use Minicube to quickly spin up a local single machine with a Kubernetes cluster. You can use Minicube on your laptop or your desktop to spin up a Kubernetes cluster. I will then show you how to spin up on Amazon AWS using kops. Kops is a tool that can be used to spin up a highly available production cluster. Doing the labs yourself is possible and highly recommended. Using the AWS free tier, which gives you 750 hours of T2 micros per month, so it's not just one T2 micro, it's 750 hours per month. So you can run multiple T2 micros as long as you don't exceed this number of 750 hours per month. The URL to sign up is aws.amazon.com. You can do the same labs using your local machine. You will not be able to test the integrations with the cloud, but you can still use Kubernetes. You can use Minicube from this URL. You can find these URLs as well in the procedure document in the beginning of the course. Or if you want, you can use DigitalOcean and you can use this URL to get a $10 coupon. Let's set up Kubernetes locally using Minicube. Minicube is a tool that makes it easy to run Kubernetes locally. Minicube runs a single node Kubernetes cluster inside a Linux VM. It's aimed on users who want to just test it out or use it for development. It cannot spin up a production cluster. It's a one-node machine with no high availability. Now the good news, it works on Windows, Linux and macOS, so you can use it on your PC whatever you are running. You will need virtualization software installed to run Minicube. For instance, you can use Virtualbox, which is free and can be downloaded from virtualbox.org. You can download Minicube from this URL. You can just copy paste it from the procedure document, or you can just type it over from this video. To launch your cluster, you just need to enter in a shell in Linux, in a terminal on macOS, or in PowerShell or CMD in Windows. Minicube start. If you're using Windows, you first have to cd into the directory where you downloaded Minicube, and then you can start Minicube with this Minicube start command. I will just show you that in a demo in the next lecture. In this demo, I will show you how to do a local Kubernetes setup using Minicube. This is the Kubernetes Minicube GitHub URL. You will find all the GitHub releases under releases right here. So here you can download manually the latest release of Minicube. They have versions for macOS, for Windows and for Linux. The easiest way is to use a package manager. So if you go back to the Minicube main URL, then below you have README, and in this README you're going to find a getting started guide. Using this getting started guide, you can install Minicube for Linux, macOS or Windows. And I would recommend you to follow this guide to install Minicube on your system, because the guide splits out different options, and depending on what OS and version of your OS you're running, you might have to go with a different option. So I'm going to show you this demo on macOS, and on macOS it's pretty straightforward, but if you're on Windows, I will just follow this guide to get it installed. So let's quickly go over the different options. Let's say that you're on Linux. You can just download and install Minicube in user local bin using this command. You would still have to install the command line utility Cubectl, which you can download from the Kubernetes website. In my procedure document, you will find the URLs that you can use to download Cubectl. So this is for Linux. Then for macOS, you have two options. You can use brew, which is the easiest way. It will automatically install the Cubectl command line utility for you, or you can use direct, also using the curl command, and extract it in user local bin Minicube. And then you have the Windows option, and with Windows you can download the Minicube installer, which will install it for you, or you can use a package manager, the Chocolatey package manager. If you don't have this yet, you can download this package manager from here and then run this command, and this will install Minicube for you. So the difficulty that will arise is that Minicube will start a VM to run Kubernetes in. So you cannot, and that is important, you cannot run Minicube within a VM. It will spin up a VM itself. That means that you will have to choose a hypervisor. So you on Windows and also on Mac, you have different hypervisors. So on Windows, you can either use Hyper-V or Virtualbox. And then using these commands here, you can see which hypervisor is installed on your system. So if you have a look here, for example, Hyper-V will only work on Windows 10 Enterprise, Pro or Education. If you have the Home Edition, you will not be able to use Hyper-V, you should use Virtualbox. So then you download Virtualbox and then you use Minicube start VM driver Virtualbox. And using this command, you can make it a default driver. So in general, Home Edition, Virtualbox, otherwise you can use Hyper-V, and with Hyper-V, you still might have to enable it as an administrator. So whether you will be able to run Minicube all depends on the hypervisor. If you have troubles launching Minicube, it will probably be a hypervisor issue. There are alternatives. You can use, for example, Docker for Windows, Docker for Mac, if you have issues starting Minicube. I would still recommend to try Minicube first because it's such an easy way to get Kubernetes running on your system. So to summarize, getting started guide right here to install Minicube. And then if you're not using a package manager, download Cubectl, install and set up Cubectl for Linux or for Mac or for Windows. So for example, if you're on Windows, you can download the latest version from this link. I also have in my procedure document links to the Cubectl version. If you already have Docker for Windows installed, then this will also have a Cubectl version. Probably best to just type Cubectl already in a PowerShell or a CMD on Windows to see if you have Cubectl available. Make sure that if you download the latest version of Minicube, that you also have a new version of Cubectl, which means if you already have a Cubectl installed, you probably want to upgrade that one. Otherwise, you can get some errors when you're trying to connect to your cluster. So let's try to set Minicube up on my machine. So I'll just use brew because that's the easiest. Brew install Minicube. So if you are macOS, it's going to be pretty easy to install Minicube. It will also install the Cubectl for me. So I will have Minicube and the Cubectl. Once this is done, and this command is exactly the same whether you are on Windows, Mac or Linux, you run Minicube start. And if you are on Windows, you might have to add the VM driver here. If you don't add the VM driver, it's going to automatically select one for you. So here it says automatically selected the HyperKit driver, and alternatives is VirtualBox. So for me, it's going to use a HyperKit, but I could also use VirtualBox. HyperKit is preferred over VirtualBox on Mac. So this is then going to set up HyperKit. So I need to give my root password of the machine. And then it's going to download the latest VM image. Now it's creating a new VM, and that's why we cannot run Minicube within our own VM. We need to run it on our host system. So if your host system is Windows, then you need to run it on your Windows machine because it will create a VM, a virtual machine itself. So all our Kubernetes processes will run in this VM that Minicube is creating. So now it is preparing Kubernetes 1.17.0 on Docker 19.035. So because we are using Kubernetes 1.17, you also want to make sure that your Cubectl version is also on 1.17. So if I just open another window, Cubectl version, and I can also see that my Cubectl is version 1.17, 1.17.0. So this one will definitely be compatible with the Kubernetes that I'm running within Minicube. So then once it starts, the VM is going to use kubeadm to set up my cluster. I also have at the end of this course some kubeadm lectures where we use kubeadm manually to set up Kubernetes on a couple of VMs within the cloud. So if you want to do it completely manual on a virtual machine, you can use kubeadm for that. Then it's pulling the images, launching Kubernetes, waiting for the cluster to come online, and now it is done. Minicube also says that it has configured Cubectl to use Minicube. So that basically means that it created a config for us. Where is this config? It is in our home directory in .cube config. So Minicube set this up for us. It set up the certificate, the server. So now we can connect to this server using Cubectl to execute Kubernetes commands. So let's have a look again at the documentation, which has some example commands that we can run to test whether our cluster is running. So here we have the link examples, Minicube start that we did. If you want, you can run a Minicube dashboard to see a dashboard. We're going to skip that for now. I have some lectures later on the dashboard. And then you can do Cubectl create deployment, hello Minicube, which is going to create a deployment using the Echo server image. It's just a test image to see whether it's working. And then we're going to expose the service as a node port. I will explain to you later on what node ports means. Now we're just going to copy paste these commands, see whether our cluster is working, and then later on I will explain in depth what this all means. Cubectl create deployment, hello Minicube. Deployment is created. So now it created a service so they can reach my hello Minicube deployment. And because this is now all created in a Kubernetes within the cluster, I now also need to enter a command to know the IP address and the port where I can connect on to reach this service. So Minicube service hello Minicube. And this went pretty quick, but it actually opened a browser window and it immediately went to the correct URL. So let's have another look at the terminal first. So we have the namespace, default namespace, name hello Minicube, and then the URL that we have. So this is the node port that has been opened on this IP address of my virtual machine. So you see here server 192.168.64.8 on port 8443, which is a Kubernetes API server. Now it created another port. It opened another port, the node port where then my service is reachable on. So then it says opening service default hello Minicube in a default browser. Then it opens within my browser this URL. And this is exactly what the Echo server is returning. The Echo server just returns some information about the request. So we have the client values, server values, and the headers received. There was nobody in the request. When you are finished with the lab and you want to stop Minicube, you can just run Minicube stop, and this will then stop the Minicube VM. If you did something wrong and you want to completely destroy your VM, you can use Minicube delete, and this will then delete the VM completely. And then when you then do Minicube start, it will start a new VM. You don't have to delete it all the time, only when something major went wrong and you cannot recover, or you completely finish with Minicube, you want to make sure that you don't have the VM installed anymore. Then you can use Minicube delete to delete the cluster and delete the profile from your kube config. So that's it for Minicube. Minicube is a very powerful tool that you can use to test with Kubernetes and deploy on Kubernetes using your local machine. It might be a bit tricky to set up for the first time, especially on Windows, but once it is set up, it is pretty easy to use. Minicube is really a great tool to install and use Kubernetes, but sometimes it doesn't spin up, sometimes it doesn't work with your configuration, with your desktop. So there is an alternative. You can download Docker, and the newest versions of Docker allow you to install Kubernetes within the client. So that makes it a lot easier to use Kubernetes if you're already using the Docker client or if Minicube doesn't work for you. So in this demo, I will show you how this works. So if you just type in Docker client Windows Edge in Google, then you will get on this page. storedocker.com, editions, community, it's a community edition. Docker, CE stands for community edition, desktop Windows. And here on this page, you can download the stable version or the Edge version. Because Kubernetes within the Docker client is pretty new, you need the Edge version. At some point, they will include it in the stable version, but now you need the Edge version. So you need to download the Edge version for Windows, or you can download the Edge version for Mac. So I downloaded the Edge version for Mac. It's an installer and it will install Docker in your tray in Mac, but I suppose in Windows it's exactly the same. And once it's started, it starts by default when you start it. Then you can go to Preferences. And when you open your preferences, a window like this will open, and you should have an icon here, Kubernetes. If you don't have this, then you're probably on the stable version and you should download the Edge version. To enable Kubernetes, you just click on this, you click on Kubernetes, and you press Apply. Kubernetes is now starting. This can take a few minutes. So my Kubernetes cluster is now running. This is the macOS terminal that I launched. If you are on Windows, you can just launch the command cmd or a PowerShell to get a terminal. And then you will also be able to use the Docker and kubectl commands. So I can now use a terminal and do kubectl get nodes. And I get my Docker for desktop. If you already tried to use Minicube earlier before that, you might have to change your context. So kubectl config get contexts will show you the context that you have. And now I only have one cluster, one context, but if you're using Minicube, it's possible that there's also a Minicube context here. And then you just have to use kubectl config use context, and then the name of the context will switch you to that cluster. We switched now, but I was already on this context. So this is only if you have multiple contexts, if you used Minicube earlier or you already had a cluster installed earlier. Now I can start using it. Kubectl get nodes. I have one node. Let's try to run a pod. I will run kubectl run hello Kubernetes, and I'm going to use the echo server, port 8080. Deployment hello Kubernetes created. Kubectl expose deployment hello Kubernetes type node port. I'm creating a service so that I can access this hello Kubernetes. So this is just a test. I will explain you in the coming lectures what it all means. Just to see whether the cluster is working, I should now be able to connect to this service. Get service hello Kubernetes. And I should now be able to go to my browser on localhost, and this port I should be able to connect. Localhost and this port, and this just gives me a response. So this is my request URI localhost 8080. That's what my pod is running on. So if you get this, then your Kubernetes install is properly working, and you just created your first application, your first pod on Kubernetes. So in the next lectures, I will go in a bit more detail what all these things mean. This is definitely a good alternative to Minicube if you don't get Minicube running, or you just want to use only the Docker client with Kubernetes, and then you only have to install one package. I just showed you how to use Minicube or the Docker client to get a Kubernetes cluster. Now let's talk a little bit about other tools to run a production cluster. There are multiple tools to install a Kubernetes cluster. I showed you how to use Minicube and the Docker client. Those are for local installs. If you want a production cluster, you will need different tooling. Minicube and Docker client are great for local setups, but not for real clusters. They spin up only a one-node cluster for development and testing. kops and kubeadm are tools to spin up a production cluster. You don't need both tools, just one of them. On AWS, the best tool is kops. At some point, AWS EKS, the hosted Kubernetes, will also be available. At that point, this will probably be the preferred option. With a hosted solution, you don't need to maintain the masters. With kops, you own all the infrastructure, so you also need to maintain the masters. For other installs, or if you cannot get kops to work, you can use kubeadm. Kubeadm is an alternative approach, and kops is still recommended on AWS. You also have AWS integrations with kops automatically. Kubeadm is a more generic tool, so it's an alternative approach if you're not on AWS or if you cannot get it working, but I still recommend you to use kops if you are on AWS because you will get the integrations with IAM and the load balancer and so on. The kubeadm lectures can be found at the end of this course and let you spin up a cluster on DigitalOcean. Because the focus on this course is really on Minikube and kops, I just put the lectures at the end because they provide you an alternative way of setting up a cluster. If you have AWS, you should always try AWS first. If you're going to do bare metal or another cloud provider, then kubeadm can be a good alternative. In this lecture, I will show you the same setup, but this time on AWS, and I'm going to use a tool called kops. To set up Kubernetes on AWS, you can use a tool called kops. Kops stand for Kubernetes Operations. The tool allows you to do production-grade Kubernetes installations, upgrades, and management. I will use this tool to start a Kubernetes cluster on AWS. There's also a legacy tool called kubeup.sh. This was a simple tool to bring up a cluster, but is now deprecated. It doesn't create a production-ready environment. Kops only works on Mac or Linux. So if you're on Windows, you will need to boot a virtual machine first. You can use Vagrant, just a piece of software, to quickly boot up a Linux box. You can download Virtualbox from virtualbox.org and Vagrant from vagrantup.com, because you will need both Virtualbox for the virtualization and Vagrant to spin up a new Linux box. Once downloaded, to boot up a new Linux VM, just type this in your CMD or your PowerShell. So you just look for the tool CMD or PowerShell in Windows, and you first create a new directory. We can call it Ubuntu. You cd into this directory, you type vagrant init ubuntu/xenial64, and then you type vagrant up. And this will bring up a new Linux machine, a new Ubuntu machine that you can use. I will show you the details in the next demo, because Vagrant works on Linux, Mac, or Windows. In this demo, I will show you the setup of Kubernetes with kops. You can use kops on Linux and on Mac. If you have Windows, you first have to install Vagrant and Virtualbox. So what I will first show you is to just start a new VM with Virtualbox. You can do that on Mac, on Linux, and on Windows as well. So first you download Vagrant Up and Virtualbox, then you install it. It's very easy, very straightforward. Then you open a shell or a terminal on Mac, and then you create a directory. In this directory, you do Vagrant init and the Ubuntu box that you want. I'm going to use Ubuntu Xenial64, but you can use any Linux distribution that you want. On the website of Vagrant, you can find other boxes if you would rather run another operating system. This Vagrant init will create a Vagrant file, and then you just do Vagrant up. Vagrant up is then going to use Virtualbox to set up this Ubuntu Xenial64 box. This might take some time, a couple of minutes. And then this is what you should see when it is set up. You also see that within the Linux box you just created, you have a /vagrant that is pointing to the current directory that you are in on your host system. To log in vagrant ssh config, Linux and Mac users will just be able to do vagrant ssh. Windows users need to take a look at this identity file here. This is going to point to a path of the private key that they can use in PuTTY. So PuTTY is a tool for Windows to log in into SSH, and you can use puttygen and PuTTY to first convert this private key using puttygen, and then log in with PuTTY to this box. You can also use Vagrant SSH, but then you need to install the OpenSSH client. So whatever you think is most easy for you, you can do. Either you use puttygen and PuTTY to log in with your private key. The login is Ubuntu, or you install these OpenSSH libraries. If you would be stuck, there's lots of information on the internet on how to convert a key using puttygen and PuTTY. There's lots of screenshots. So have a look there. If it still doesn't work, just use a Q&A and tell me exactly where you're stuck, and I will try to help you. So from now on, I will assume that you have a Linux box available on whatever platform that you are. So from this point on, I'll be using the Linux downloads, and I will be using this box to set up the Kubernetes cluster. So the next step here is that we're going to download kops so that we can install Kubernetes. So you can go to github.com docs/kubernetes/kops. Here there is download the latest release, and you can download the kops Linux AMD 64. Copy link address, and then I can download this kops Linux AMD 64 to this machine. This is downloaded. I can do chmod kops Linux AMD 64 plus executable flag so that I can execute it, and I can move this to user local bin. I have to do a sudo, and then I'm going to download Python pip, because Python pip will allow me to install AWS, the AWS command line utility, which I will also need before I can set up this cluster on AWS. So this is installed, so I should be able to do pip install AWS command line utility. And this is going to give me the command line utility called AWS that I will then be able to use. So if I now type AWS, I can now execute commands on AWS. If you don't have an AWS account yet, you have to open one. AWS, Amazon.com, create an AWS account, and when you create a new account, you will automatically get the free tier. Once you opened an AWS account, you will see a screen like this. These are all the servers that you can use in AWS. And you need to go to Identity and Access Management, because we are going to create a user first so that kops can deploy Kubernetes. So Identity and Access Management, you go to Users, create new user, call it kops, and you are going to generate an access key for this user. This is the access key that you need to configure AWS on your new machine. So remember, you just installed the AWS command line utility. What we're going to do now is we're going to the shell of our VM where we installed AWS, the command line utility, and we're going to type AWS configure. It asks for the AWS access key and for the AWS secret access key. Both were printed when you were creating this user. You can specify a default region or an output format, but that's not necessary. So that's it. Now, what the AWS utility did, it actually created these files in .aws, and our credentials are now configured, so we can now use AWS. One more thing we need to do is we need to give our user, our kops user that we just created, permissions. We should give it administrator permissions. So we close this. Go to our new user, and we're going to attach a policy, and we're going to give it administrator access. You click attach policy, and now our kops user has administrator access. You could also give less permissions to kops, but then you have to do it manually. So the easiest way is to give it administrator access. If you're concerned about giving too much access to your kops user, you can always change it into only what it needs. Next, I'm going to go back to the welcome screen, and I'm going to go to S3. S3 is an object storage. You can compare it with Google Drive or a Dropbox. And we're going to create a new bucket. And this bucket is going to be used for our kops state. And I'm just going to add some random string at the end, which you also should do, and you also should make it random, because this bucket name needs to be unique in Amazon in that region. This region that you specify here is going to be the region where you want to deploy your cluster. So if you want to deploy your cluster in Ireland, you should choose the Ireland region. So depending on where you are, you can choose a different bucket. If you don't know what region to choose, there's a tool, cloudping.info. You do an HTTP ping, and for me, Europe and Frankfurt are the closest ones. I'm going to go with Ireland. You are going to do this from a different location, so you're going to see different results. I'm going to choose Ireland. I'm going to click create, and now I have my kops bucket. Next is the DNS. So kops is also going to set up DNS for us, but we need to set up a domain for that, a subdomain. So you can use root 53 for that. Root 53 allows you to do DNS management. Kops expect you to enter a subdomain, and kops will manage that subdomain for you. But you already need to create this zone in root 53 so that kops can manage this for you. You can either register a new domain name here on Amazon or even somewhere cheap where you can get one for a couple of bucks. There are also free solutions, so you don't need to spend money for a domain name. There is a .tk, and there's also providers that give you subdomains that you then can use in root 53. So you don't need to spend money if you don't want. If you don't have a domain name, it's probably the easiest way to just go for something free. Have a look at the procedure document. I listed some free solutions there. I have my own domain name, so I'm going to get started here with DNS management. I'm going to create a hosted zone. So even if you have your own domain name, or if you opt for one of the free solutions, you still need to create this hosted zone. And this is actually going to cost you some money. Right now, this costs you $0.50 per month to create a hosted zone. So if you don't want to spend any money at all, you might just want to run Minicube. Maybe kops is not the solution for you. So I'm going to click create hosted zone, and I'm going to use kubernetes.newtech.academy. I have the domain name newtech.academy. So what I will do is I will make sure that Kubernetes Newtech Academy is going to forward to root 53. And to make it forward, I need to specify these values here, and those are going to be different for you as name servers for this subdomain. My domain is hosted at Namecheap, so I'll have to go to Namecheap, tell Namecheap Kubernetes.newtech.academy is hosted by root 53. These are the name servers. And you will easily find that if you buy a domain name. It's quite straightforward to make those changes. Just to show you how it works with Namecheap, you have something called Advanced DNS, and here I added 4 new records for Kubernetes for this domain name, so that I have a subdomain kubernetes.newtech.academy, and they point to the root 53 name servers. So I did add new record, and as record, Kubernetes as a host, and then whatever name server that you will see. So if you do this yourself, don't take these name servers, but take the ones that you see when you add a hosted record in Amazon. If you use something else than Namecheap, for instance, a free .tk domain name, then this will look a little bit different, but it's the same principle. You will have to add an NS record for a domain or a subdomain to be able to make this work. Once we set up the DNS, kops is going to manage the DNS for us using root 53. So now we have done all the preparation and we can finally start launching our cluster using kops. And that I will show you in the next demo. This lecture is completely optional. If you didn't have any issues with DNS, then you can skip this lecture, or you can come back to it later on if you realize that at some point your cluster doesn't work because you have an issue with DNS. In this demo, I will show you a little bit about DNS troubleshooting. Kops need to have DNS working properly, otherwise you cannot start your cluster, or you can sometimes start your cluster but not connect to it. So here in this lecture, I will talk a little bit about DNS troubleshooting. On a machine that you are using kops, a Linux machine, you can use the program host. You first need to make sure that host is installed. So you can use sudo apt install byte9 host. In my case, it's already installed. So now we can use the executable host. To make sure that the name servers are properly set, you can do host -t ns. NS stands for name server of, in my case, Kubernetes Newtech Academy. You can see that the name servers of this name, Kubernetes Newtech Academy, point to the root 53 zone. If this doesn't return the Amazon name service of your root 53, then something is not working. In root 53, you also need to make sure that the reply of the name servers also matches exactly this. So these are specific name servers for this zone. You cannot use my name service because yours will be different. The reason why this resolving works, this host -DNS, is because I put these records in place in the DNS control panel of Namecheap. Let's say that you don't use Namecheap and that you only use AWS Route 53. Well, then you need to create a hosted zone. For example, I will create a hosted zone for New Tech Academy. And I will click create. And this New Tech Academy has different name servers. And still, if I go back to my terminal, even though I created this public host name, if I do host DNS of New Tech Academy, it will still point to registerservers.com, which is Namecheap, because Namecheap is still responsible for the name servers. So if I do wish, which is not a tool of this domain name, I can see that the name servers are set on this register. So if you want to host your full domain name on Amazon, which is not necessary, but if you want, then you need to change the name servers in Namecheap, not in the DNS management, but there's also an option name servers, and every domain provider has that option where you can change the name servers, and then you have to point the name servers to these name servers. Then your domain name points to this hosted zone, but that doesn't mean that this hosted zone will work automatically. Then you have to still create name server records that point from your main domain name, New Tech Academy, to Kubernetes New Tech Academy. So then you can copy those, go to New Tech Academy, and then create a record set. And then this is going to be Kubernetes New Tech Academy, and the value will be these name servers. And this is going to be an NS record. And then you're going to have Kubernetes New Tech Academy is going to point to your other Route 53 zone. So this is only necessary if you want to host your main domain as well on Amazon, because then you need to make sure that you register, your domain register uses these records because these are from your main domain, and that you add also here, just like I did in the previous lecture, records and S records to point to Kubernetes New Tech Academy. The third option is that you don't use Kubernetes New Tech Academy, you don't use a subdomain, but you just pass this main domain name as a cluster name and as a DNS name. And then you will have, and then you don't have Kubernetes New Tech Academy, so you can remove this record. Then you only need this, and you use your main domain name as a cluster name and as a DNS name. And then you will have api.newtechacademy instead of api.kubernetes.newtechacademy. So that's the third option that you can use. The best option is to use, like I explained in the previous lecture, you often have a DNS management at your domain register, and then you can just add this NS record. If that's not possible, you can create a second hosted zone for your main domain name, and then you can also add an NS record to Kubernetes New Tech Academy. So that all works. So then at the end, when you do all this configuration, then you need to check whether host NS New Tech Academy resolves to the correct one, and Kubernetes New Tech Academy resolves to the correct Route 53 zone. So in my case, it first goes to my register, and my register I have a DNS record set that points to my hosted zone, my Route 53 hosted zone. So I hope this makes it a little bit more clear. DNS is not an easy topic. You might have to spend some time to set this up. Also, when you set this up, it might take another 30 minutes, 1 hour before those changes are propagated. So these records might be cached sometimes. So sometimes you just have to wait half an hour, 1 hour before you get the correct results. At this point, you should have set up your Vagrant box. You should have set up AWS. So now we can launch our Kubernetes cluster using kops. Here I'm logged in to my Ubuntu Xenial box. Before setting up the cluster, you need to make sure that you have kubectl installed as well. This URL you can find in the procedure document. You can just download it. You move it to use a local bin, exactly where kops is as well, and you give it execution permissions. And then when you type kubectl, you have kubectl available. Before creating the cluster, you will also have to create new SSH keys. And those SSH keys will be used to log in to the cluster. SSH keygen can create new keys. So what I'm going to do is I'm going to create a new key in .ssh id RSA. And this public key, id RSA pub, will be uploaded to our instances. And that way we will be able to log in to our instances using our private key. So id RSA is our private key. This is our public key. Public key goes on the instance and we log in with the private key. And just one thing I want to do before I'm going to enter the kops command is I'm just going to rename the kops binary. I'm going to rename it in just kops rather than having kops Linux AMD64. This is the kops command I'm going to execute. And this kops command is not going to do anything yet because it needs another step before it's really going to execute the commands on AWS. But this one is going to create one master, a T2 micro, and 2 nodes, also T2 macro. So we have kops create cluster, we give it a name. This needs to be the full DNS name of the cluster. I have Kubernetes New Tech Academy, the one that I set up in Route 53. I'm going to save the state in S3. This is my S3 bucket. And I'm going to launch it in the EU West 1A zone. You're probably going to use another zone, US East 1A, US West 1A, and so on. Node count is 2, and the node size is T2 micro. The master size is also T2 micro, and the DNS zone is Kubernetes New Tech Academy. I'm going to execute this, and then you will be able to preview the changes that will be made to AWS. So it's going to make auto-scaling groups for our nodes. It's going to launch a master. It's going to provision also SSD drives. And then if we want to really launch this cluster, then we can just do this with kops update cluster and then the name with --yes. And then it's going to launch. If you want to make changes first, you can edit the cluster using kops edit cluster and then the name. But because the state is on S3, you also have to specify the state. So then the command will work and then you can still make some changes. I'm not going to make any changes at this point. I'm just going to launch the cluster. So I'm going to do kops update cluster and I'm going to specify yes. And again, I will specify the state. This will then launch the cluster. It will take a couple of minutes and then I can try to run one of the examples. So now the cluster has been created and let's have a look what this means. Road config for Kubernetes New Tech Academy in this file. I'm just going to get this file. And this is actually the certificates that we need and the password to log in to our new cluster. That's what kops configured already for us. So for instance, we have here the server HTTPS API Kubernetes New Tech Academy, and that's what we will be able to use. Let's see if the nodes are up. So kubectl get node. 3 nodes in ready status, 1 master. This is going to be the master. It's in a different IP range. And then 2 nodes. Let's try to run the same deployment as we did on the Minicube cluster to test whether our Kubernetes cluster using kops is working. So I'm going to do kubectl run hello Minicube, which is the name of the deployment. And it's going to use this image, the Echo server version 1.4. And Echo server in this Docker container listens on port 8080. So we specify port 8080 as an argument. This is going to create the deployment hello Minicube. And now we can also expose this service so that we can access it externally. We can do that using kubectl expose deployment, the name of the deployment, which is hello Minicube, and we give it a type. This is the type of the service. For example, If you want a load balancer in front of this service, then we can say type load balancer, which I will cover in the next lecture. I'll do now a more simple version, just node port, which will expose a port on every node of this Kubernetes cluster that we can contact this service on. It is on every node except the master. So you can connect to every node on a specific port, but not on the master. So service hello Minicube exposed. So if you now do kubectl get services, we see now our hello Minicube service type node port, and this is the port that we can contact our service on. So this port is now open on every single node in our Kubernetes cluster except the master. Let's have a look at the AWS console. Let's first go to EC2. Make sure that you are in the correct region. I launched it in Ireland, so I'm in the Ireland region. And then you should see 3 running instances. So I have here 2 nodes and 1 master node. This one is terminated, so you can ignore this one. If you don't see your nodes, you can also have a look at the autoscaling group, which is here on the left. Autoscaling groups. You should have 2 autoscaling groups, one for the master and one for the nodes. And it's this autoscaling group that will launch the instances. So if something is wrong, for example, if you're reaching AWS limits, then it should be displayed here. Then for some reason, it couldn't launch an instance. But for us, everything went fine. We have 2 instances running. We exposed the node port, which means that those 2 nodes will reply on this port and redirect my traffic to this service. Before we can access it, we need to make sure that the firewall is not blocking us. So these nodes have also a firewall. They have a security group. And to see the security group, you just can click on the instance and then you can see the inbound and outbound rules. So here port 22 is open, but not the node port that we just created using this service. So we will need to make changes to this. So if I click on the security group, I go to inbound, I click edit, I can add a new rule. I can say custom TCP. I can copy paste a port that is exposed. So this was 30,032. I can paste this here and you can either open it for everyone 0000/0 or only for my IP address. I'm going to choose only my IP address, so only me will be able to access this service. I click save. I can go back to my node and I can take the external IP address of this node or of this node. The IPv4 public IP address is listed here. I can copy this. And if I go to this IP address, port 30,032, I get the response from my service that I launched on my Kubernetes cluster. So this works. I have a running Kubernetes cluster. I have 2 normal nodes and 1 master node. And I created our first deployment, our first service, and I exposed a node port that I now can connect to using the IP addresses of any of those 2 nodes. In the next lecture, I will explain you a better approach using a load balancer that gives you also a host name, and then you can also use DNS to give your service a real DNS name, a real domain name. So once you did this demo and you are not using the cluster anymore, I would recommend you to remove the cluster. So I will show you how to do that. So to delete our cluster, we can do kops delete cluster, then the name of the cluster, Kubernetes New Tech Academy, in my case, and then we can also add the state. So the state is in S3, and then it's going to show us what will be removed. We must specify yes to delete the cluster. So we're going to execute the same command using yes, and that will then bring the cluster down again. And the next time you want to use it again, you can just execute kops create again, just like you did in the beginning of this lecture. So if you have any issues with bringing up this cluster, there's a troubleshooting lecture if you have DNS issues, or you can use a Q&A to ask me questions if you run into any problems. If everything went fine, just continue with the next lectures. This deleting of the cluster will take a couple of minutes. and then your cluster is removed. Now that you have your own cluster running, locally using Minicube or on AWS using kops, now I can show you how building containers works so you can run your own containers on Kubernetes. So this lecture will be about building your own app in Docker. To build containers, you can use Docker Engine. You can download Docker Engine for Windows, Mac, and Linux. There are 3 different URLs. There are also different ways to set up Docker on your host system. All the installations are pretty easy. You just download the software, you install it, and you can use Docker. You can use that, or you can use my Vagrant DevOps box, which comes with Docker installed. On my GitHub, I have a DevOps box, which is a Vagrant box, which you can use, which will automatically install Docker for you. In the demos, I will always use an Ubuntu Xenial box set up with Vagrant. I showed you how to do this in the AWS preparation demos. If you haven't followed those, but you would like to run an Ubuntu Xenial box, then have a look at those demos. The DevOps box is also Ubuntu Xenial, and you can find the URL for this DevOps box in the procedure document. So whether you use a plain Ubuntu or the DevOps box, it's almost the same. Also, you don't have to use Vagrant. Docker is available for Windows, Mac, and for Linux. So you can use it with whatever operating system you want. Let's talk about Dockerizing a simple app. I'm going to show you how to Dockerize a Node.js app, but you can Dockerize any application you want. So Dockerizing a simple Node.js app only needs a few files. You need a Docker file. Every container you want to build needs a Docker file. Let's just go over the few lines that are in this Docker file. First line, from Node 4.6, we are saying our image is going to be based on the Node image. This Node image is publicly available. Docker will download version 4.6 from this official Node image. Our work directory is going to be /app. In this Linux environment that comes from Node, we are going to create the directory /app. And the current files in this current directory are going to be copied to /app. I will show you the other files in just a moment. They're just going to be the JavaScript files for this Node.js app that are going to be copied to this /app directory. To prepare this Docker image, we're going to execute some commands. You can do that using the run command. So this is going to run npm install. npm install is a command that will install all the dependencies so that we bundle the dependencies together with this Node image. So we will have the Node image with the Linux operating system and all the dependencies, and then we're going to add all dependencies that this app needs. It's going to expose a port, in this case port 3000, and when this container itself starts, then it's going to run npm start. Let's have a look at the other files in this directory that will then be copied to this /app folder. The first one is index.js. A very simple Node.js app, only a few lines. It's going to load some of the dependencies that it needs to start a server, and then when it gets a hit on / the main page, it's just going to say hello world. This app is going to listen on port 3000, and when it starts, it's going to print to the console the example app is listening at host and port. Then a Node.js app typically has a package.json file, and in this package.json file we're going to define the dependencies. It's basically the metadata of this app. So our app has the name my app, it has a version, you can choose whatever version you want. It's a private app, we're not going to put it into a public repository. It has scripts. This is just going to define what happens if you do npm start. So if you take a look at the Docker file, we see npm start, well then node index.js will be executed. It depends on the engine, Node 4.6.1, and it has one dependency. The dependency is Express. So when we do npm install, then it's going to install Express in this /app directory. So we have a /app directory with index.js, package.json, and npm install is going to run when we're going to build this Docker container. Is going to install the dependencies in /app. You will see this working when I do this in the shell. You just need to understand what these three files mean. The flow itself of building the image, you will clearly see when we're going to run the docker build command. So to build this project, docker build can be used. Docker build can be executed manually, or you can use CI/CD software like Jenkins to listen for any changes to your project and then automatically execute a build. We are going to do it manually for now. Later on, you can automate this easily. To build the Docker image from the previous line, this is what we're going to do. We're going to cd to the Docker demo. This Docker demo is also a Git repository on my GitHub. So you can clone this Git repository or you can download this as a zip file. Again, procedure document. You will see the URL as well in the next demo. Here you have then a Docker file, index.js and a package.json. If you want to build then this image using the definition in this Docker file, you enter docker build and that is going to start the build process. After the Docker build process, you have built an image that can run the Node.js app. And that build process that I just explained, that's what I'm going to show you in the next demo. In this demo, I will show you how to build your own Docker image. If you already followed my other training, Learn DevOps Continuously Deliver Better Software, then this will be very familiar and you can actually skip this lecture. In this demo, I'm going to use my Ubuntu Xenial Vagrant box. If you haven't set up one yet, have a look at the demo where I explain how to set up a cluster on AWS. The first demo explains you how to set up a Vagrant box with Linux. Like I said, you can also just download Docker for Windows or Docker for Mac and then execute the commands in a terminal or using CMD or PowerShell on Windows. I'm going to use Linux. You can get exactly the same box, so you should be able to exactly replicate this labs using this Vagrant box. First thing I'm going to do is I'm going to install Docker. I can do that using apt-get install. So I'm just going to apt-get install docker.io, which is going to install Docker for me. This is going to install the latest version that is bundled with Ubuntu. If you want the really latest version, then you will have to get the latest version from their website. And their website also has the instructions how to install the latest one. This one is bundled with Ubuntu version 1.12. Definitely good enough to do the lab. I'm also going to install Git. So apt-get install Git. In our case, it is all installed. Why do I need Git? I'm going to git clone my Git repository. So github.com docker demo. You can also just go to this URL and you can download a zip file. So you don't really need Git. It's just easy to clone it straight here. And then we have the directory docker demo. So in this directory we have the index.js, the package.json and the Docker file I explained. You also have a Docker compose and an index database.js. You don't really have to take a look at that. Those are used in some of my other courses. I just have one Docker demo repository that I always reuse. Docker build is going to use the Docker file. So let's have another look at this Docker file. Looks exactly the same. So now we can execute the Docker build. You can execute Docker build as root with sudo. So you can do sudo docker build and then the current directory. Or you can make sure that the user Ubuntu has access to this Docker group. Because then user Ubuntu, our user, will always be able to execute Docker. And you need to do this as a root. Once you do this, you actually need to log out and log in again. So I'm just gonna exit here, do vagrant SSH again, go to Docker demo, and then now I can do the Docker build of this Docker demo. I just paused the video for a second, and this is what you should get. So Docker has successfully built this container. And if I go back to my Docker build, you can see first it pulled the node image. Then it set the working directory to /app, added the files to /app, then runs npm install. So this gets all the dependencies for Node. It installs it. It's quite a lot. And then it says npm info OK. It exposes port 3000. Make sure that when you start a container, it uses npm start. So then we have this container, and you could already run this container. You can use docker run -p port 3000 is the port that this app is running on, and we want to expose it as port 3000 on the host system. So this Ubuntu Xenial is the host system. And this -t runs a Docker image with this ID. You can also specify the I flag for the interactive mode, so that if you press Ctrl+C, it will actually get killed and you don't have to kill it manually afterwards. Just going to run this. Let's open another window. And I'm just going to do curl localhost 3000, and then we have the hello world. So this is the hello world of the index.js. So that's it. Next, I'm going to explain you how to get this image online on Docker Hub so that Kubernetes can download this image so that we can run this image on our cluster. In this lecture, I'm going to talk about the Docker registry. I'm going to show you how to push containers to Docker Hub. You can run the Docker app by executing docker run locally. That's what I just showed you in the previous demo. Docker can be run locally for development purposes. If you just want to do some local development, you can run your containers locally. You don't need Kubernetes for that. To make an image available to Kubernetes, you need to push the image to a Docker registry, like Docker Hub. The first step will be to make an account on Docker Hub. Then you can push any locally built images to the Docker registry, where the Docker images can be stored in. To push an image to Docker Hub, you first need to use Docker login to log in with your user ID and your password. You then tag your image ID, the one that was outputted when you ran Docker build. You need to tag it with your login / Docker demo or any name that you want to give to your image. Then you can Docker push this image, and then your image will be uploaded to Docker Hub. Or to immediately tag an image during the build process, so you don't have to do it in 2 steps, you can go to Docker demo, do the Docker build again, and then use -t to immediately tag your build. And then you can also log in and push your Docker image to Docker Hub or to any other registry that you want to use. If you're not using anything yet, Docker Hub is the easiest. If you're using AWS, then AWS, for instance, has an alternative, Docker ECR. I will be using Docker Hub, but feel free to use your own one. Just a few remarks. You can build and deploy any application you want using Docker and Kubernetes, if you just take into account a few limitations. You should only run one process in one container. Don't try to create one giant Docker image for your app, but split it up if necessary. All the data in the container is not preserved. When a container stops, all the changes within a container are lost. You can still preserve data using volumes, which is covered later in this course. For more tips, check out the 12-factor app methodology at 12factor.net. So there's a methodology on how to write stateless applications, which is a very interesting read. Have a look at this website if you're interested in that. Here are also a few official images you might want to use for your app. There is Nginx, which is a web server. You can use a PHP image. You can use a Node image, that's the one I used in the demo. You can use a Ruby image. You can use a Python image, or you can use a Java image. And there are many more that you can use to build your containers on hub.docker.com. In this demo, I'm going to show you how to push a Docker image to Docker Hub. I'm again logged in into my Ubuntu Xenial box, and I'm going to use Docker login first. If you don't have a Docker ID yet, you have to go first to hub.docker.com. This is the website. If you're new to Docker, you can create your free Docker ID. You just have to enter your email address and a password, and then you can sign up. And then you can use those credentials to log in here. So I'm going to enter my username and my password, and then I'm logged in. Once logged in, you can create a new repository. Your repository is always going to be prefixed by your username, and then you can enter a name. For instance, you can say Docker demo. Then you give it a short description, maybe a full description, and you can make it public or private. At the moment, you can only have a limited private repositories, but you can have unlimited public repositories. I already have a repository. My repository is Kubernetes demo, and that is the repository that I'm going to use. Feel free to take any name that you want. So the next step is to tag our image, a previously created image, with the repository name that we specified in Docker Hub. So I'm going to use Kubernetes demo. So I'm going to tag this image with this. If you don't remember your tag anymore, you can use Docker images, which is just going to list all the images of your system. Here is my node image, for instance, and then you will see the image that you have created. I have this one now tagged. So this is my image, and my image is now tagged with the name. So I can now Docker push this image to my repository. So I'm going to push this to Docker.io, my name, Kubernetes demo. This will take some time to upload, and then if you take another look at Docker Hub, you will see last pushed a few seconds ago. And then here, we didn't really specify a tag name. It has a tag name latest, and it is 256 megabyte. You can specify a tag name. If you don't, it just takes latest. So Docker tag with :latest is exactly the same as not doing it. So you can either tag it with latest, or you can give it a version ID. I'm not going to give it a version ID. I'm just going to use latest. So now everything is ready to use this image that we just pushed to Docker Hub, to use this in Kubernetes. So that will be the next step. In the next lecture, I will show you how to then run this image on Kubernetes. Now that we uploaded our image to Docker Hub, I will now explain to you how to run this app on Kubernetes. Let's run our newly built application on a new Kubernetes cluster. Before we can launch a container based on this image, we need to create a pod definition. A pod describes an application running on Kubernetes. A pod can contain one or more tightly coupled containers that make up the app. Those apps can easily communicate with each other using their local port numbers. So if you would have another app, you can just connect to that app on that port. Our app only has one container. To make this app running on your Kubernetes cluster, you create a pod file, for instance pod helloworld.yml with the pod definition. This .yml file is in YAML format. If you want to know more about the YAML format, then you can just look it up on Google. It starts with the API version, it's v1. This is a pod definition, so you say kind pod. You can provide metadata, you can give your pod a name. This pod is named node.helloworld.example.com. We can also give it a label. Later on, we can easily filter on labels. This pod has the label app as a key, hello world as a value. In spec, you're going to put the container definitions. We only have one container, so we're going to give it a name. The name of this container is Kubernetes demo, and the image refers to the image that we uploaded to Docker Hub. First your login, Ward Viana is my login, then slash, and then the repository name. The ports that you want to expose on this pod. Here I'm going to expose container port 3000. You can use Cubectl to create the pod on the Kubernetes cluster. You just use Cubectl create -f and then the path to this YAML file. All these YAML files are bundled in another GitHub repository. The URL of that GitHub repository you can find in the procedure document again. Here are then some useful commands that you can use on pods. I will just briefly go over the list now, and then I will then show them in action during the demos. Kubectl get pod gets information about all the running pods. So once you create a new pod, it's probably the first command that you're going to execute. Kubectl describe pod, and then you can insert the pod name, describes just one pod. So this gives you more information. Kubectl expose pod and then a pod name, and then a port and a name. This exposes a port of a pod, so it creates a new service, and then you can connect to your Kubernetes cluster on that port, and then it will redirect to your pod. Kubectl port forward, and then a pod name, and then a port number. You can port forward the exposed pod port to your local machine, and then on your local machine, you can go to that port, and then it will port forward to the pod. You can also attach a pod to see what is really happening in your pod. You can execute commands on the pod. So this then just executes a command in the container. If you have multiple containers, you can specify specific containers using -c. Otherwise, it will just take the first container. You can still label pods after they have been created. So if you want to add another label, then we can do it like this. And then this is very useful for debugging. You can run a shell in a pod, and then you're going to run kubectl. You're going to specify an image, and the image can be busybox. And busybox is a very small image that can start you a shell. And when you have a shell, you can debug anything that goes wrong much easier, because then you are in a new pod and you can connect to your other pod that maybe is malfunctioning. In the next demo, I will then show you how to launch this pod. In this demo, I'm going to show you how to run your first app on Kubernetes using pods. First of all, you will need to clone my GitHub repository. So again, you can use the git clone command, or you can go to this website and you can download a zip file. So this repository is called Kubernetes course. On this machine, I have my Minicube cluster running, just as I explained in one of the previous demos. So I can immediately use kubectl. So kubectl get node is showing me that my Minicube is running. So I have here under first app, I have the hello world YAML file. And this file I'm going to use to create the pod. So I'm going to use kubectl create -f first app hello world.yaml. Kubernetes came back to me. It said pod node hello world example.com created. So if I now use kubectl get pod, then you can see the pod that was previously running, which is a pod that I started when I installed this cluster, which is already running. And then I have another pod node hello world example.com. So let's have a look at this one using describe pod and then the name. At the bottom you see the events, and you see one of the events is that it's now pulling the image. So it's pulling this image, needs to download the image, and then it will start the pod. So here I see some info about the container, my labels, status is pending. If you don't have a very fast internet connection, it can take some time to pull this image. So now it started the container with Docker ID and then the ID. Our pod is now running. There are now multiple ways to get to this pod. The first way is to use port forwarding. We can use kubectl to port forward, and then we just use the name of the pod. We can port forward the pod port, which is 3000, and we can listen locally on port 8081. So then I can locally, on this machine, connect to 8081, and then kubectl is going to make sure that all this traffic is redirected to port 3000. So this stays open. I just have to open a new shell, and I can just do curl localhost on 8081, and then I get the hello world. This is one way to quickly test whether it is working. The second way is to create a service. In the next lecture, I will explain you how to create a service for AWS. If you're running a cluster on AWS, that's going to be interesting for you. If you're using Minicube, you can just expose the port and then connect directly. You can do the same on your AWS cluster, but on AWS, you have the possibility to use a load balancer. So a load balancer is always going to be better for you. Let me first show you how to expose this port. We're going to use kubectl expose. We're going to expose pod, and our pod name is node hello world example.com. And we are going to use type node port, which means that we can directly access port 3000 on Kubernetes and it will redirect to this pod. And actually, in this case, we also need to provide a name for this service. So we'll just say node hello world service, because you cannot use this as a name for a service. So a service node hello world service exposed. Now we just need to know the IP address of the Kubernetes cluster to connect to. If you're on AWS, you can just use your master node. You will have to change your security groups though. If you're on Minicube, Minicube service, this node hello world service --URL. And this gives us the correct mapping. So this port forwards to port 3000. So if we do kubectl get service, we see the newly created service that exposes port 3000. With Minicube, we can use this port to connect to this service, because this is an IP address that I can use from my host system, from my Mac. These IP addresses here are IP addresses within our cluster. So those are two different things. So I'm going to use my browser, and hello world, it is working. This demo is really a continuation of the previous demo. It just became too long, so I split it up. In this demo, I'm going to show you some useful kubectl commands. Some more commands I can use: kubectl attach, and then the pod name. This attaches to our running process, but our process is just running, so we're not going to see much here. If our process would output some log, we would see the logs here. We can also execute something in that container. So we can use kubectl exec to execute a command. So let's say that we use lsapp. That's what is in our /app folder. So this is a list of the files of /app in the running container. If you would create a file here using touch, for instance, app test.txt, this test.txt will disappear if this container is killed. That's what I meant earlier with the data of a container is never persisted. It just disappears when the container is stopped. You need to use volumes, which we will see much later, if you want data to be persisted over time. There's still one command that I want to show you. I first want to show you the service. So I'm going to do describe node hello world service, describe service node hello world service. So it has a label. We expose it as a node port. It has an IP address. So this is an endpoint that is exposed that we could connect to from another pod. You can either use this endpoint or we could use the node port, because the node port is a static port that will be always accessible. I'm going to use this endpoint now. So I'm just going to copy paste this. And what we're going to do is we're going to launch another pod with busybox. So we're going to use image busybox and we're going to execute a shell. And this is going to create a new pod with a new container. And then we can just execute commands on our Kubernetes cluster. I don't have curl here, so what I'm going to do, I'm just going to telnet to this endpoint of my node hello world service. And then I'm going to say get slash. I get a 200 OK back. And this is my express server, so it says hello world. So this is another way of connecting to the pod from within a cluster, not within the same pod, because then I could actually just connect to localhost port 3000 if it was a container in the same pod. This is another pod, and then I can use this endpoint and connect to this pod still. Later on I will talk about service discovery and DNS, and we're not going to use these manual endpoints, but for now I just want to show you what is possible. In the next lecture I will show you how to expose a service that uses the load balancer on AWS. In this lecture I will show you how to set up a load balancer for your first app. In a real world scenario, you need to be able to access the app from outside the cluster. On AWS, you could easily add an external load balancer. This AWS load balancer will route the traffic to the correct pod in Kubernetes. There are other solutions for other cloud providers that don't have a load balancer. Like you can run your own HA proxy or Nginx load balancer in front of your cluster, or you can expose ports directly. In this lecture, I will show you how to do it with AWS. The first app that we launched, you can see the YAML file on the left. It is just going to run the pod with the Kubernetes demo, which just returns hello world on port 3000. This is the pod definition. On the right, we have the service definition, and the service definition is going to put a load balancer in front of our pod so that our pod can be accessed from the internet. This service has type load balancer, and when you specify this type load balancer on AWS, it will start an AWS ELB, an elastic load balancer, which is a service that Amazon provides. This service is defined in a YAML file, but earlier when we were using Minicube, then we were using the command kubectl expose, and that also creates a service. We just don't define it in a YAML file. Here we define our service in a YAML file and then submit it to the cluster. It's basically the same thing. Whatever you do with kubectl, you can also put in YAML files. So this YAML file is of kind service. It has a name, hello world service, and it also has a spec. I will go over the spec in detail in the demo. For now, just remember that you can have different services. This service is of type load balancer and will run an ELB. If you run this pod and this service, you could then point a host name like example.com to the ELB to reach your pod from the internet. So this is the way to make your application available to the internet. I will show you all the details in the next demo. In this demo, I'll be running the first app behind a load balancer. I'm again going to log into my Vagrant box, the same one I used to spin up my AWS Kubernetes cluster with kops. I have the Kubernetes course cloned right here. If you haven't downloaded the course material from GitHub yet, have a look at the procedure document. So here I have two files that I want to use. The first one is our hello world, the pod, and I added here the name. So it's still running on port 3000. I just added a name, Node.js port, which I can then reuse in the service. So our service is going to be of type load balancer, which in our case is going to be an elastic load balancer on AWS. It will be automatically created for us. Port is going to be 80, the standard HTTP port. And the target port is going to be the Node.js port. Then Kubernetes knows that it needs to go to this container. Protocol is TCP. The selector is going to refer to our app. So we have app hello world. It's going to be the service for the pod with the label app hello world. I'm going to run this. kubectl create -f of the pod and then of the service. So this takes some time. While this is setting up, let's have a look in the AWS console. So I'm here on the main page and I go to EC2 and we have now one load balancer running. So this load balancer is internet facing. It's running on port 80 and it's going to refer to our 3 instances. Those 3 instances will route the traffic to our pod. That's why ELB adds all 3 of them. The ELB doesn't know exactly where the pod is running, so it just adds all 3 of them, and every node will then redirect the traffic to where the pod is, because the nodes know where the pod is. So there's a health check on this port. So this is a node port that is exposed on every node, and that will be the port that is used by the ELB. So the mapping is from port 80 on the ELB itself, and it goes to the instance port 32162 to the nodes itself. And then on the node, it will redirect the traffic to the correct pod. This ELB has a DNS name. So what we can actually do is, if you go to root 53, this is our hosted record for the Kubernetes zone, I can create a new record and I can say hello world.kubernetes new tech academy, and I can say this is an alias for our load balancer. So I can create this, and then I can actually use this to directly go to the load balancer and directly to my app. If we go to hello world Kubernetes .new tech academy, you can see hello world. So our root 53 hello world Kubernetes new tech academy goes to our load balancer. Our load balancer redirects the traffic from port 80 to one of those 3 nodes on this instance port, and then the traffic is redirected to our pod, which then gives hello world. If you would go to the security groups, you would also see that we have a new security group for our load balancer, which is right here, our ELB. And then if we go to the nodes or even the master, you see that this one ends with 2A. We have all traffic open between our Kubernetes nodes and the load balancer, so the load balancer can access our Kubernetes cluster. So that's it for this demo. Now we can actually create apps on Kubernetes that you can expose to the internet using the Elastic Load Balancer of Amazon. This is the end of the section Introduction to Kubernetes. Let me recap this section using a few diagrams to make sure you understood the concepts. I showed you how to deploy a first application to the Kubernetes cluster. First, I showed you how to create a container image using the Docker command line. So we created locally an image, we tagged it, and then we uploaded the container image using the Docker push command to Docker Hub. So at this point, Docker Hub has a container image called Kubernetes example. Next, I create a first pod, Kubernetes example, and this is the definition of this first pod. What is important here is that we defined a container. We can define one or more containers in a pod that will run on the Kubernetes cluster. This container image uses the port 3000. That's why I define a port with the name Node.js port, and the container port to contact the server is port 3000. This launched our first pod on the Kubernetes cluster. We used the command kubectl create to send this YAML file to the Kubernetes cluster, and Kubernetes launched this pod. What Kubernetes is going to do then is going to pull the image from Docker Hub, because we defined that image in the YAML file. So it pulls this container image and it starts running the container in this pod in Kubernetes. Next, we want to contact the pod. And because we don't have a service yet, we need to use another way to contact it. One way that you can use to contact a pod from your local machine is using port forward. So using kubectl port forward, and the name of the pod, and then the ports that you want to use. The first port is a local port on your machine that you want to open, and the second port is the port of the pod, in this case 3000. Once we enter this command, we can use our browser on our local machine or a curl command to contact our pod, and we can do that on port 8081. Port forward is not the regular way that you would contact an app. It's just a way for us to contact the app locally because we are administrators of our Kubernetes cluster. The real way to contact a pod is to create a service. So that's what we did next. We created a service. We defined the YAML definitions and we used kubectl create to create the service on the Kubernetes cluster. This, for example, is a YAML definition for a service for the Hello World service that is of type load balancer. If you are on the cloud, on AWS, on Google, on Azure, you can use type load balancer to put a load balancer in front of your service. So this will launch, this will spin up a load balancer on AWS, and then you can contact this load balancer on port 80, because port 80 is defined here, which is a standard HTTP port, on the load balancer host to contact your app. This is a normal way to contact your app, because then you expose your app to the internet, everyone can contact it. Load balancer is not the only way to expose a service. There's also another way to expose a service using a node port, which will just open a port that you define, or when you don't define a node port, it will choose a random port, and it will open that port on every single node of your cluster, except the master node. So that way it doesn't create a load balancer, but it opens a port on your Kubernetes cluster nodes so that you can contact your app. This can be useful, for example, if you're going to deploy on-prem, where you don't have a load balancer, then you can use a node port. There are different ways to contact your app, and you will see in the next lectures, in the next sections, different ways that you can contact your app. These are just 2 ways that I just showed you. Now you might ask yourself, why do we need this service and why don't we just contact the pod directly? Why can we not just put a load balancer in front of a pod? Well, now we have only one pod, but we might have more than one pod. We might have 5 pods. So the service that we create, make sure that we then load balance the requests over the multiple nodes in case that we have multiple nodes. In Kubernetes, we'll always have pods and we'll always put services in front of them. And from outside, we'll always contact the service first, and the service will make sure that your requests are routed to one of the pods that you are running. Let's say that your pod is malfunctioning. Pod 1 is malfunctioning. There are ways that you can use to debug the problem. First of all, you can use kubectl attach to attach to the pod to see what is happening. You can maybe see some output that will help you debug your problem. You can execute a command. For example, if you execute the command bash or sh, it will open a shell and then you can type more commands to debug your problem. Or you can also use kubectl logs to show you the logs of the pod. Maybe there is something in the logs that can help you. So these commands are very helpful to debug issues with your pod. Then there's another possibility. You can also launch a new pod. For example, you can use kubectl run to launch a pod busybox that is using the image busybox to then pull the image busybox from Docker Hub and launch it in a pod. You will then execute the command sh in that pod, and then that will then open a shell, and it allows you to execute more commands to debug the problem. You could, for instance, connect from this busybox pod to the Kubernetes example. So that's it for the recap. I hope I made it a little bit more clear what we try to achieve in the first lectures. In the next lectures, I'll go into more details on how you deploy applications on Kubernetes and how the architecture of Kubernetes really looks like. In the next coming lectures, I'll be talking about Kubernetes Basics. So all the previous lectures were just an introduction. I just showed you how to set up your cluster and how to run a simple application. Now we're going to go a little bit deeper into detail how to run different kind of workloads on Kubernetes. I am first going to start with an architecture diagram. I'm going to give you a 10,000 foot overview of how the nodes in Kubernetes work. This is the architecture diagram and it has a lot of information. So let's start here with something that you already know. In green, you can see the pods. So we have pod 1, 2, and 3 on node 1 and pod 4, 5, and n on node 2. These are pods like we've started in the introduction. Within those pods, you have the containers. So we had just one container, just like pod 2 and 5 only have one container. So the containers here are denoted in red. You can have multiple containers. If you take a look at pod 3, then you see that pod has 2 containers and pod 1 has 3 containers. Those containers can communicate easily to each other. They can just use the port number, so a localhost and a port number, to communicate with each other. If you have 2 small services, let's say one is the backend and one is an authentication service, they can easily communicate with each other. Pods within a cluster can also communicate with each other, but that needs to go over the network. I will show you later on how service discovery works so that pods can easily communicate with each other. Those containers in those pods are running using Docker. So on our nodes, we all have Docker installed. You can also use an alternative container engine, but in our examples, I'm always using Docker. On those nodes, you also have a kubelet and a kube proxy service running. So the kubelet is responsible to launch the pods. So it's going to connect to the master node to get this information. The master node is not shown on this diagram. It's only the nodes that are shown here. The kube proxy is going to feed its information about what pods are on this node to IP tables. And IP tables is the firewall in Linux and can route traffic. So whenever a new pod is launched, then kube proxy is going to change the IP table rules to make sure that this pod is routable within the cluster. That brings us to the service. And the easiest way to remember how a service works is just to imagine yourself a load balancer. So this can be, for instance, the ELB, the Elastic Load Balancer on AWS. This Elastic Load Balancer on AWS is going to be publicly available. So clients from the internet can connect to this load balancer, and this load balancer is then going to forward the traffic to our Kubernetes cluster. It's going to have all the nodes listed, and the traffic is all going to arrive at IP tables. IP tables has then the rules to forward traffic to another node. For instance, if the pod is running on another node, then it needs to go to this destination node. If the pod is on that node, then it will just forward the traffic to the pod and to the specific container in this pod. You have seen that in the AWS example, we have exposed a node port, like a static port. The communication between the service and the node is going over this one port. In AWS's case, the ELB just has one port configured. All the nodes listen to that port, and IP tables will just route the traffic that comes from that port to the correct pod. To translate this to our YAML file, let's have a look how this looks. So we have here a container, and we have the pod definition. So when we started our Kubernetes demo, this specification, this spec here, refers to a container, and this container refers to this red block within this pod. The whole green pod is actually the full definition that you see here on the right. The container is just everything you see under spec. If you would have 2 containers, you would just have a spec with 2 containers. In this lecture, I'm going to show you all about scaling pods. If your application is stateless, you can horizontally scale it. Stateless means that your application doesn't have a state. It doesn't write any local files, and it cannot keep any local session data. If you would have 2 pods and one pod is going to write something locally, then those pods would be out of sync, and that means that each pod would have its own state, and that's why you cannot scale it. If both pods would have always the same files, so they wouldn't really have their own state, and if a request to one pod would always lead to the same result as doing the request from the other pod, then the pod is probably stateless. That means that all traditional databases like MySQL, Postgres, other ones, are stateful. They have database files that cannot be split over multiple instances. Most web applications can be made stateless. Session management, needs to be done outside the container. So if you're going to get hits on your web application and you want to keep information of your visitors, then you need to use an outside service. You cannot store that kind of data within your container. You can, for instance, use Memcache or Redis or even a database to store your sessions. Any files that need to be saved cannot be saved locally on the container, because if you stop your container and you start it again, the file is lost. So you need to also save any files you want to save outside the container, either on some shared storage or on external service. On AWS, this can be, for instance, S3, which is an object storage. Our example app is stateless. If you would run the same app multiple times, it doesn't change state, because in our app, we are actually not running anything. If you have multiple instances of that app, you will just still get hello world. For more information about the best practices, have a look at the 12factorapp.net. This 12-factor explains the best practices for stateless applications. Or you can check out my other course, Learn DevOps, Continuously Delivering Better Software, or I have another course on scaling apps on-premise and in the cloud. Both explain those principles. Later in this course, I will explain you how to use volumes to still run stateful apps. Those stateful apps cannot horizontally scale, but you can run them in a single container and vertically scale. To rather scaling apps horizontally, so adding more pods, you're just going to allocate more resources like CPU, memory, and disk to that pod. That is vertically scaling. Scaling in Kubernetes can be done using the Replication Controller. The Replication Controller will ensure a specified number of pod replicas will run at all time. So you just specify, let's say, 5 pod replicas, and then it's going to run the same pod, but then 5 times. A pod created with the Replica Controller will automatically be replaced if they fail, get deleted, or are terminated. If you tell Kubernetes to run 5 pods, and there are only 4 running because one node crashed, for instance, then Kubernetes will launch another instance of that pod on another node. Using the Replication Controller is also recommended if you just want to make sure your one pod is always running, even after reboots. You can then run a Replication Controller with just one replica. This makes sure that the pod is always running, even when a node crashes. To replicate our example app 2 times, we can use this YAML file. So what has been changed? Instead of kind pod, we say kind replication controller. We still have metadata. We have a name, hello world controller. The replication controller also has a spec. In this spec, I'm telling that we're going to have 2 replicas and that this is the replication controller for the app hello world. That's why we have the selector that says app needs to be hello world, which is going to select the label with app hello world. Then we have a template. Here goes our pod definition. The pod definition also has metadata. We have the label, the same one as you saw under the selector, and then we have the pod specification. We still have one container with the name Kubernetes demo and an image, and we expose port 3000. What the replication controller is going to do in this case is it's just going to run 2 times the pod that is defined in a template. How this works on a Kubernetes cluster, I'm going to show you in the next demo. In this demo, I'm going to show you how to horizontally scale a pod with the replication controller. I just started my Minicube Kubernetes cluster again. So if I type kubectl get nodes, or get node, then I can see Minicube is ready. I have the YAML file in the Kubernetes course, in replication controller, hello world replication controller. I'm going to create this. Replication controller, hello world controller created. So let's have a look. Kubectl get pods. You can now see that this replication controller created 2 pods. Now we have an hello world controller dash and then a random string because the name needs to be unique. And then a second one also with unique name. So these ones are now creating. It needs to pull the image again, so they can take some time. So let's describe one of them. So we need to use now this name. Describe pod and then the name. So this uses the replication controller and it's still the same demo. Let's just wait a few seconds now until the image is pulled. Now the image has been pulled and I have the two pods running. You can see that now I horizontally scaled my pod. I have multiple instances running. If I have multiple nodes, those instances could be running over multiple nodes, and we could put a service in front of that, a load balancer, that will make these multiple pods accessible to other software or customers. If one of those pods crashes, if one of those underlying nodes crashes, then the controller will automatically reschedule these pods. So let me just remove one of those pods. And then we're going to see that the replication controller is just going to create a new pod. It will see that this pod is gone and it will reschedule a new one. So you can see here now, this pod is terminating and 11 seconds ago, a new pod is already running. The controller will always make sure that the correct amount of pods is running. I can also scale those pods just using the kubectl command. I can do kubectl scale and I can say replicas equals to 4 instead of 2. And I can again pass the YAML file, or I can just specify the full name of this replication controller. I'm just going to show it first with the file name. Replication controller hello world controller scaled. So now you can see it is creating 4 pods because we did the scaling operation. Another way to use kubectl scale is first, let's get the name of the replication controller. We can abbreviate this by RC. This is the hello world controller. And we can say kubectl scale replicas only maybe one replica. And then we can say RC / hello world controller. And then it's going to scale it again. So if you do again get pods, you see now 3 of them have been terminated and only one of them is now running. Again, to iterate what I said during the theory, this you can only horizontally scale. So this is horizontally scaling. You can only horizontally scale when your pod is stateless. If you have stateful pods, then you will not be able to do this. If you want to know how to create stateless applications, have a look at the 12-factor app. Have a look at my other courses. If you're already sure that you have a stateful application, you will just have to be a little bit more patient because I will be explaining stateful pods later on in the course. If you want to delete this controller, you can just say kubectl delete rc hello world controller. And then the controller is deleted and the last pod is now terminating. These scaling operations are all saved in Kubernetes itself as a backend etcd, where it saves all those settings like number of replicas. You don't always need to have those in the YAML files. It's easy to have them in YAML files because then you have your state easily available to you in files and you can do testing and you can put those things in version control, but it's not a necessity. In this lecture, I will be talking about deployments in Kubernetes. Let me first talk about the replication set. The replication set is the next generation replication controller. So it's a newer version of the replication controller that I just explained to you in the previous lecture. It supports a new selector that can do selection based on filtering according to a set of values. For instance, the selection could be environment is either going to be dev or QA. Not only based on equality like the replication controller. In the replication controller, you could only say environment equals dev. You couldn't do anything more complex. With the replication set, you can do more complex matching. This replica set, rather than the replication controller, is used by the deployment object. Let's talk about deployments now. A deployment is a declaration in Kubernetes that allows you to do app deployments and updates. When using the deployment object, you define the state of your application. Kubernetes will then make sure the cluster matches your desired state. A state can just be run this application and make sure it is replicated 5 times. It's just the way to describe this to Kubernetes is most easily done now with deployments. That's why just using the replication controller that we saw earlier or the replication set might be cumbersome to deploy apps. So those two things might not be fit to deploy your apps. It would just be too much manual work to then do updates and rollbacks and so on. The deployment object is much easier to use and gives you more possibilities. So what are those possibilities? With a deployment object, you can create a deployment, for instance, just deploying an app, update a deployment, deploying a new version of your app. You can also do rolling updates, which means zero downtime deployments. You're not immediately going to update your whole app, but you're going to do it in steps so that you will have zero downtime during this deployment. You can also easily roll back to a previous version of your app. You can pause and resume a deployment as well. For instance, if you want to roll out to only a certain percentage of your running pods. So this is an example of deployment. It looks, again, very similar to the previous specifications that I showed you. Currently, this is still in V1 beta. That's why you see another API version than V1. For sure, in the next releases, this will become stable and will go to V1. Again, this object has metadata. We give it a name. The name here is hello world-deployment. Then we have the specs. I'm going to run 3 replicas of this pod, and the template is below. Template has, again, metadata. There's a label. The label says app is hello world. The pod specification then, we have 1 container, still our Kubernetes demo, still the same image, and still the same port. So that looks very, very similar to all the other things that we have seen earlier, but I will now show you what the deployments really can do for you. To get information on the current deployments, you can use kubectl get deployments. Because deployments are using replica sets, you can use kubectl get rs, rs stands for replica set, to get the information about the replica sets. Kubectl get pods with show labels can show you the pods that are running. You can use pods or just pod, and that will just show you the pods that are running, including the labels. So whenever we add a label to our pod, like the app label, then we can see those if we add show labels. Kubectl rollout status and then type deployment and then the name of the deployment object gets the deployment status. So if you want to know whether the deployment was successfully completed, then we can use this command, and this command will show us that. Kubectl set image of our deployment hello world deployment. We can change our image from Kubernetes demo to Kubernetes demo with the tag 2. We can actually run another version of this Kubernetes demo. There's a version 2 in this repository that is going to say hello world v2. And if you want to use that newer version of the Kubernetes demo image, then you can just tag your image with the specific version that you want. If you don't use any version, you will use the version tagged with the latest. If you specify one, then that exact version will be retrieved. So using this command can actually update your application to the latest version. You can achieve the same thing using kubectl edit, and then you can edit this deployment object. Kubectl rollout status is going to give you the status of the rollout. If you update your image to a new version, then you can use this rollout status to see how the deployment is progressing. Kubectl rollout history, if you want to see a history of your deployed versions. So let's say that you first have version 1, then version 2, version 3. Kubectl rollout history will show you those different versions. And this brings us to something very useful. If you release a new version of your app, let's say version 3, and you want to go back to version 2, then you can do Cubectl rollout undo, and this rolls back to the previous version. If you want to roll back to another version, you can see all the versions using rollout history. If you want to then roll back to version 1, for instance, you can just specify using rollout undo, you can specify to revision and then the revision number. That gives you the possibility to roll back to any version. In the next demo, I'm going to show you how this all works. In this demo, I will show you how deployment works on Kubernetes. In my Kubernetes course, from my GitHub repository, I have deployment helloworld.yaml. And this is the file that I showed you during the theory. Now I'm going to create this deployment on my local Kubernetes cluster. Deployment hello world deployment created. Let's try Cubectl get deployments. Deployments. I asked for 3 replicas. So my desired state was 3 replicas and the current state is 3 replicas, which means that it already launched these 3 replicas. All the replicas are up to date. They are running the version Kubernetes demo latest version that I asked to run, and they are also available. So they are running for a minimum amount of seconds, which means I should be able to connect to them. I can also get the replica sets. So this is the replica set that has been created for this deployment. So you don't need to create those replica sets yourself. Kubernetes does it for you. I can also do get pods to see the pods. These are 3 pods. And I can also say show labels. And then you see the label. So I said that my label should be app hello world. So you see here app hello world is the label for this pod. It also has a pod template hash, which is automatically generated. I can also ask the rollout status of this deployment, hello world deployment, and it is successfully rolled out. We didn't really need to enter this command because we could have seen this information using the get deployments. But this is just another way to see if our app is deployed. If I log in to hubdocker.com, then I also pushed earlier a newer version with tag number 2. So not with tag latest, which is automatically added if you don't specify a tag, but with tag number 2. This is a different version and it is going to say hello world v2 when I would launch this app. So what I'm going to show you is how to change the version of this first version to version 2 and then back to the old version. Let's first check what the app would give back if you would connect to it right now. To do this, we have to run Cubectl expose again. We're going to expose a deployment, and the deployment is going to be the hello world deployment. And the type is going to be a node port. Like we want a static port automatically assigned that we can connect to. This expose command created a service for us. So let's do get service. And now we can see that there has been a service created. So let's describe this service. Hello world deployment. So we see that port 31969 has been opened as a node port for this service so we can connect to our app. Minicube service hello world deployment URL is going to give us the URL of our Minicube cluster. It's going to be the IP that we can use and the port that has been exposed here. The internal IP addresses of Kubernetes are different than the external IP address that we can connect to. So we're going to go to this URL. I'm going to use curl. It gives us hello world. So let's now change this version. So what I'm going to do now, I'm going to set a new image. I'm going to do Cubectl set image of deployment / hello world deployment. And my image, I'm going to change my Kubernetes demo image into my new Kubernetes demo version 2. So we're going to change the Kubernetes demo that was tagged with latest because we didn't provide a tag. So it's going to be latest with the tag number 2. And this now says image updated. We can now follow this rollout status using this command. And it is already successfully rolled out. So if we then curl again to this URL, we see hello world v2. So our image is now updated, and it actually updated all our running pods because we have multiple pods running. So you see 3 of them have been terminated, 3 of them have been started again with this v2 version. Let's say that I want to see the history, Cubectl rollout history. So I see revision 1 and revision 2. You don't see any change cause because when we did the Cubectl create -f of this, we could have added record, and this record would then also show changes right here. Haven't used this, so that's the reason why it shows none. So we're not really happy with this version 2. I rather want to see hello world without the 2. So let's undo this deployment. So I'm going to do Cubectl rollout undo and then the name of our deployment. So now it's rolling back. Successfully rolled out again. It goes very quick because those images are still on file. Again, 3 new containers. And then if I curl, it's back to hello world. So this way you can easily change your versions from one application version to another application version and very quickly do rollbacks if necessary. Let's say that I want to go back to another revision and the revision is already a long time ago. That's also possible, but by default it only keeps 2 revisions. So we would have to edit, Cubectl edit can do that, our deployment object, and we would have to change this limit parameter. So this is our object. We can just make some changes here. And the change that I'm going to make is I'm going to set a revision history limit of 100. I edited this, and now let's do another rollout. Let's go back to number 2. Let's check our history again. And now that we made a few changes, you can see that our history is getting longer. So here I have my 3 revisions, and then if I want to go to another revision, I can say to revision number 3, for instance. And then it is actually rolling back to revision 3, which becomes a new revision because now I'm at 6. Using the undo and to revision can just let you jump to any revision that you want. And I have no idea anymore on what version we are, but we are back on the original version. Deployment objects are the objects that you want to create when you are deploying your applications. You can also use a replica set or the replication controller, but those are just too abstract. Deployment is going to be the way that you want to put your app on Kubernetes. And then you can manage the lifecycle of your app much better using the rollbacks and the rollouts and so on. In the next couple of lectures, we will see some more details about the labels and about health checks, and also how health checks can then improve the resiliency of your app. In this lecture, I'll be talking a little bit more about services. Pods are very dynamic. They come and go on the Kubernetes cluster. When using a replication controller, pods are terminated and created during scaling operations. When using deployments, when updating the image version, for instance, pods are terminated and new pods take the place of older pods. That's why pods should never be accessed directly, but always through a service. A service is the logical bridge between the mortal pods and other services or end users. When using the Cubectl expose command earlier, you created a new service for your pods so that it could be accessed externally. Creating a new service will create an endpoint for your pods. You can either use a cluster IP, which is a virtual IP only reachable from within the cluster. This is the default. Or you can use a node port. And that is a port that is the same on each node that is also reachable externally. If you want to reach your pods externally, this is what you need. Or you can go for a load balancer, and this is used for production applications on the cloud. A load balancer is created by the cloud provider that will route external traffic to every node on the node port. I showed you how this works. I did that using ELB, Elastic Load Balancer, on AWS. The options that I just showed you only allow you to create virtual IPs or ports. There is also a possibility to use DNS names. If you use external name in the service definition, you can provide a DNS name for the service. For instance, for service discovery using DNS. This only works when the DNS add-on is enabled. I will discuss this later in a separate lecture. I'm going to talk about service discovery, and I will then talk also about this DNS add-on. This is an example of a service definition. You could also create the same service using kubectl expose. It does the same thing. It has API version 1. The kind is service. It has a name. The name is Hello World Service. And in the specification, we're going to define the port. So the port that we're going to use is 31001, and it's going to be a node port. So you see at the bottom here, this service is of type node port. The target port is a Node.js port. So this name Node.js port I defined in my pod, and this is port 3000. The protocol is TCP, and the selector is app hello world. So this will be the service for the pod that has the label app hello world. You don't have to specify this node port. If you don't specify it, then it will be a random port. If you specify it, then this port will be used, but this service can only be created if this port is still available. So you will have to manage port collisions yourself. Also note that by default, services can only run between ports 30,000 and 32,767. But you could change this behavior by adding the service node port range argument to the Kube API server. Kube API server is a process that starts, so in the init scripts of your master node, you could change this service node port range if you would want another range for ports. You would then have to make sure that you don't have collisions with ports that are already used on the node. Typically, this is already a good setting. What you're going to do is, if let's say you want to use a default HTTP port, then you're just going to put an AWS load balancer in front of it. In the next demo, I'm going to create this service of type node port. In this short demo, I'm going to show you how to create a new service from a YAML file using a static port. I still have my Minicube running. I don't have any pods, so I'm going to create another pod again. So I'm going to do kubectl create. From my first app, I'm going to create this hello world. So this is the hello world pod, helloworldexample.com. I'm going to describe it again. So this has started. So it has the label app hello world. For this pod, I'm going to run a service. So I have first app hello world node port service. And this is going to open the node port 31001. It's going to use the Node.js port, which is defined right here in the pod definition. There's name Node.js port. This pod has labels app hello world. I have a selector on app hello world. So this is going to be the service for this pod. And I'm specifying this node port. So rather than having a random port, I should be able to access this port, and then I will be able to connect to this pod. So kubectl create this first app hello world node port service. And then for Minicube service, the name of this service is in the metadata, hello world service. I want to know the URL, and you see it has port 31001. This is the IP I can use to connect to the app. So I'm going to do curl of this URL, and I get hello world. Now, if you're on AWS, then you cannot do this command, but you can go straight to the nodes. You just have to change the security groups. I already showed you this in one of the introduction lectures for AWS, how you can do that. This is just showing how you can do the same thing, creating a service, but with a static node port. If we ask the info from our service, we can do kubectl describe, and you can either say service or you can say SVC, which is short for service, and then we can describe this hello world service. And this will give us some more information. If we want to get a list of all the services, we can just do kubectl get SVC, and then we get a summarize of all running services. This was already here. It's one of the services running for Minicube. This is the one we created. So you see here cluster IP. That's the IP here. This is the cluster IP I was talking about in the theory. This is the default cluster IP. This is the default virtual IP that our service gets. This IP is only reachable within the cluster. This is the IP that we can use to externally access the cluster. And then we see node port 31001. We also see that another endpoint has been created. So this endpoint can also be used within the cluster. So there are multiple ways to access your app. This node port is going to be the static way to access our cluster. Let me delete this service and let me then create it again. Let's describe it again. You see IP address is now different. So this virtual IP changes if we don't define it in the YAML file. So this one for us is not static. This port number, because we defined it, is a static port number. This is the one that we can use to configure external services to access our application in this pod. If you would want a static virtual IP, a static cluster IP, we would also have to define this in our YAML file. That's it for this demo. I will come back to services when I'm going to discuss service discovery using DNS. In this lecture, I'll be talking about labels. You've already used labels, but in this lecture, I want to show you some more possibilities. Labels are key value pairs that can be attached to objects. Labels are like tags in AWS or other cloud providers, used to tag resources. If you've been using cloud, then tags will be very familiar to you. Labels are kind of the same thing. You can label your objects, for instance, your pod, following an organizational structure. You can say, I want to tag my pods using key environment and value, either dev, staging, QA, or prod. And then you know whether your pod is part of your development environment or any other environment. You can also add another tag. You maybe have multiple departments. So you could say, I'm going to tag all my pods and I'm going to say this is going to be from engineering. These pods are running software for finance, or these pods are running software for marketing. In our previous examples, I have already been using labels to tag pods. This is how it looks. I always added labels, for instance, the app hello world. Labels are not unique and multiple labels can be added to one object. Once labels are attached to an object, you can use filters to narrow down the results. This is called the label selectors. Using label selectors, you can use matching expressions to match the labels. For instance, a particular pod can only run on a node labeled with environment equals development. More complex matching is also possible. You can say environment needs to be either development or QA. In earlier lectures, I have been using node labels for the services. The services had a label selector to select the correct pod that the service was going to be for. You can also use labels to tag nodes. Once nodes are tagged, you can use the label selector to let pods only run on specific nodes. There are 2 steps required to run a pod on a specific set of nodes. First, you tag the node itself, then you add the node selector to your pod configuration. It can be to a single pod or a pod template within, for instance, a deployment. The first step is to add a label or multiple labels to your nodes, and you can do that using Cubectl label nodes. You just specify the node name and then the label that you want to give it using key equals value. Secondly, you add a pod that uses those labels. Here we have a pod definition, and we just added the node selector. This node selector says hardware needs to be high spec. This pod will only run on nodes that have the label high spec. I will show you how this works using a deployment with a node selector in the next demo. In this demo, I am going to show you how to use the node selector using labels. I'm going to show you how this works using Minicube, because not everyone has an AWS cluster, but it really makes sense only if you have multiple nodes. So our Minicube only has 1 node, but I can still show you how it works. I have in my deployments folder, I have a hello world with a node selector. So let's see what's in here. It's a normal pod specification here, but we have the node selector, so it can only run on the hardware high spec. I'm going to first show you the labels of our nodes. So here you can see the labels. So we don't really have the label hardware high spec. What is then going to happen when we try to start this one? I will show it to you. Kubectl create of this hello world deployment. Let's have a look. We have 3 desired, 3 running, 3 up to date, but 0 available. Let's have a look at our pods. It's all pending. So let's have a look at one of the pods. Kubectl describe pod. And it says failed to fit in any node. This pod is trying to run on one of the nodes and needs to match the node selector. And then matching was, of course, using this hardware high spec. But there's no hardware high spec key value available on any of our nodes. So first we need to add the label. And I can do that using Kubectl label nodes. The name of this node was Minicube, and I want hardware equals high spec as a label. So node Minicube labeled. Let's do a get nodes again with show labels. And what does it say now? Hardware equals high spec. So now we just have to wait a little bit, because the node needs to figure out that this node now has a label. And you can see in our case, it didn't need a lot of time. It is now running. So if you do describe pod, and then let's take this pod, we see in the beginning we had a warning. We couldn't schedule the pod, it was not running, but once we changed the label, it could actually run on this node. If you have multiple nodes, you can specify this label on certain nodes, and your pods will only then be scheduled on these nodes. Very useful if you have different types of hardware. If you want to make sure that a certain workload only runs on a certain type of cluster, then you can use this. So that's it for this demo. You can try it out yourself using Minicube or even on the AWS cluster. In this lecture, I'm going to be explaining health checks. When you put your app in production, you will definitely want to configure health checks. If your application malfunctions, the pod and container can still be running, but the application might not work anymore. The app gives an error because of something internally that went wrong. To detect and resolve problems with your application, you can run health checks. You can run 2 different types of health checks. The first one is running a command in the container periodically. You're just going to execute a command within the container to check whether your container is still working. The other one, and the one that is used most of the time, is periodic checks on a URL using HTTP. Your app probably is going to expose an interface. Using periodic checks on that interface, you can check whether your app is still healthy. The typical production application behind the load balancer should always have health checks implemented in some way to ensure availability and resiliency of the application. Even if you're using AWS and the load balancer, the health checks are not checking whether your pod is healthy. It is only checking whether the node port is accessible. So even when you're using the AWS load balancer, you're going to want these types of health checks as well. This is how a health check looks like on our example container. Here again, I have the pod, the example pod, and here is then in bold the health check. It's a liveness probe using an HTTP GET on just slash, which means just the main website. On a production application, you're probably going to have something like /health, but here I don't have a separate health page, so I'm just using slash. The port is going to be port 3000, which is the container port, or if you give your container port a name, then you can just use that name. There's an initial delay in seconds, so the liveness probe is going to wait 15 seconds, and there's a timeout of 30 seconds. How this exactly works, I will show you in the next demo. In this demo, I'm going to show you how to add a health check to your deployment. In your deployments folder, you will find hello world healthcheck.yaml. This is our deployment object. Still has the Kubernetes demo as a container, but here we add the liveness probe. And this liveness probe is going to check slash on the Node.js port, which is port 3000. And it will wait 15 seconds before doing the first check. And we have a timeout of 30 seconds. We can just do kubectl create and then using kubectl get deployments or get pods, we can get the status of one pod. Describe pod. And in the details, we see there's a liveness HTTP GET on this Node.js port with a delay of 15 seconds, a timeout of 30 seconds, with a delay between the checks of 10 seconds. The pod will consider it healthy when there's one success or unhealthy when there's 3 failures. So then we have 3 pods running on our node, and if one of those pods gives an error, so at that point the container is still running, this container is still running, Node.js is still running, but for some reason our app crashed, doesn't work anymore, doesn't give an HTTP 200 code anymore, which is the normal code, but for instance code 500, which shows that there is something wrong, then what Kubernetes will do is it will terminate the pod and launch a new pod. And this is very important because if the pod is not working anymore and you route traffic to it, then the end user might get an error while there are still other pods that might be healthy. So what you want is that you don't route traffic at all to pods that are not healthy. And that's why we have this health check. So this health check is very useful and you should always include it if you're deploying applications in production. If you want to edit any settings right now of this deployment, you can use kubectl edit. And here you see the settings that you can change. So this is a useful trick to also see what settings are available, like the timeout, like the period, the success threshold, and the failure threshold. So these you can either edit right here or include them in the YAML file if you would want to change them. Otherwise, the default values will be used. The readiness probe. Besides liveness probes, you can also use the readiness probes on a container within a pod. Liveness probes indicates whether a container is running. If the check fails, the container will be restarted. Readiness probes, on the other hand, indicate whether the container is ready to serve requests. If the check fails, the container will not be restarted, but the pod IP address will be removed from the service, so it will not serve any requests anymore. The readiness test will make sure that at startup, the pod will only receive traffic when the test succeeds. You can use these probes in conjunction and you can configure different tests for them. If your container always exits when something goes wrong, you don't really need the liveness probe. But in general, you configure both the liveness probe and the readiness probe. In this demo, I'm going to show you the difference between the liveness probe and the readiness probe. In the previous lecture, I showed you how to use the liveness probe. Let's have a look at this script again. Hello world health check. Here we have the liveness probe defined, an HTTP GET on / within the app. Let's have a look between the difference of this check and the other check. If you do Cubectl create of hello world health check, and immediately afterwards we do a watch of the pods, Cubectl get pods, then you will see that the pod is immediately ready. So it's now running and it became immediately ready. It didn't wait for any check to perform. So that means it's immediately serving requests. The readiness probe is different from the liveness probe because it will first wait until the readiness probe succeeds and only then it will start serving requests. Let's have a look at the hello world liveness readiness YAML. Here I have also a readiness probe. Works exactly in the same way as the liveness probe to define it in the YAML file. You can also use the HTTP GET, but the difference is when we do a create of this one and then we do a watch, you will see now the container is creating. Now it is running, but it's not ready yet. First, this initial delay needs to pass, then the check will be executed once, and only when the check is executed and it came back successful, then the pod will be ready and it will be ready to serve requests. Only now it is ready. So that's the difference between the liveness and the readiness probe. So let me show you again this file. So here we have the initial delay seconds, 15 seconds, and then the readiness probe started checking, and only then when it had a success back, then the pod was ready and the pod IP is added to the service and the service will redirect traffic to that pod. If the readiness probe fails for some reason, then the IP address will also be removed from the service and no traffic will reach this pod until the readiness probe gives a success again. If you use this in combination with the liveness probe and we use the same path, then what's going to happen is it will be removed from the service and the container will be restarted to make sure that the container works again. And the container will be restarted because that's what the liveness probe does. If the probe fails, it will restart the container. So that's it for the liveness and the readiness probe. Let's talk about pod state. In this lecture, I'll walk you through the different statuses and states of a pod and a container. I will talk about the pod status field, which gives you a high-level status, the pod condition, which is the condition of the pod, and the container state, the state of the containers itself. I will then show you the lifecycle of a pod in the next lecture. Pods have a status field, which you see when you do Cubectl get pods. Here you see the status field. In this scenario, all pods are in the running status. This means that the pod has been bound to a node. All containers have been created and at least one container is still running or is starting or restarting. Other valid statuses are pending, the pod has been accepted but is not running. This happens when the container image is still downloading, so if you have a slow network connection, this can actually take some time. If the pod cannot be scheduled because of resource constraints, it will also be in the status. So let's say that you don't have enough CPU or memory anymore, then this pod will stay in pending status, and you will have to investigate, for example, using kubectl describe to see the events to know why exactly the pod is not scheduled. Succeeded, all containers within this pod have been terminated successfully and will not be restarted. Failed, all containers within this pod have been terminated and at least one container returned a failure code. The failure code is the exit code of the process when a container terminates. So exit code 0 means OK, and all other exit codes are a failure. Also, you can have unknown. The state of the pod couldn't be determined. A network error might have been occurred. For example, the node where the pod is running on is down. So these are the pod statuses. You can get the pod conditions using kubectl describe pod and the name of the pod. So here we do a kubectl describe of a pod of the API server in the namespace kubesystem. These pod conditions are conditions which the pod has passed. In this example, initialized, ready, and pod scheduled. There are 5 different types of pod conditions. Pod scheduled, the pod has been scheduled to a node. Ready, pod can serve requests and is going to be added to matching services. Initialized, the initialization containers have been started successfully. I will talk about these initialization containers in the next lecture when we go over the lifecycle. Unschedulable, the pod cannot be scheduled, for example, due to resource constraints. And containers ready, all containers in the pod are ready. There is also a container state. You can get the container state using kubectl get pod, outputting using YAML so that you can see all the data that is available for the pod. And here you have the container statuses. You have some information about your container, and then here in bold you have the state, and the state of this container is running. So this comes from Docker itself. So Docker reports that this container is running. The container state can be running, terminated, or waiting. In this lecture, I want to show you the pod lifecycle. This is a diagram that I created to give you a better idea of what really happens when you launch a pod. This diagram also shows you the init container that you can use, the post start hook, and the pre-stop hook. Those you can define in your YAML file, in your pod specification, to execute commands at certain points in the lifecycle of the pod. Let's start with the init container. When you define an init container in your pod specification, you can launch a new container that is separate from the main container that will execute some commands. This can be interesting if you have volumes, for example, to do some work on those volumes, set some permissions, create some directories before the main container starts. So this is a completely separate container, and the main container will only start after this init container is completed. Then we have the post start hook, and the post start hook starts at the same time as the main container, if you define it in your container definition, and it starts within the main container. So you can just execute some commands within the main container. Again, if you need to do some work, just when the container starts. Then we have the pre-stop hook, and that one is going to be executed when the container stops. So here, again, if you have to do some work when the container stops, then you can use a pre-stop hook. We have the main container, and within the main container, we can also define the readiness probe and the liveness probe. These readiness probes and liveness probes will only start after the initial delay seconds that you define as well in your probes. So the moment that your main container starts, this initial delay seconds will delay the readiness probe and the liveness probe, because often your app needs some time to start, to connect to a database, and it doesn't make sense to immediately start a probe, but often it only makes sense after a couple of seconds to then start checking whether the app is working. So this is the pod lifecycle. Now let's go over the different states. When the container is running the init container, then you will see in the describe, if you go and take a look at the conditions, that initialized is still false, ready is still false, but the pod is scheduled. So the pod is scheduled, the init container is running, it means that initialized is false. Then after the post start hook is executed, initialized will be true, it will still not be ready, and the pod scheduled is still true. The reason why it's not ready is because the readiness probe hasn't executed. So if we have a readiness probe, only after the readiness probe returns success, then we have initialized true, ready true, and then the pod is scheduled. And then the pod is live, it will be added to the service and traffic will be routed to this pod. In the next demo, I will launch a container that has all these elements in it so that you can see them being executed. I'm going to show you a demo of the pod lifecycle. I am in the directory pod lifecycle in the Kubernetes course, and here I have a lifecycle YAML file. This is a deployment, and in the pod specification, I have an init container. So this is the first container that is going to be executed. This is a separate container, just like I showed you in the previous lecture. So we also define an image and a command that will be executed. This container is just going to sleep 10 seconds and then exit. Then we have our main container, the lifecycle container, also image BusyBox, and it's going to write to a file the date, and it's going to say it's running. So the file is /timing, then we're going to echo the app is running, and then we're going to sleep for 120 seconds. We have a readiness probe. This is also going to write to this /timing file so that we have a nice overview of the timings, the liveness probe, the lifecycle, and in the lifecycle we have a post start and a pre-stop. So these are the hooks that we're going to use, and using those hooks we can execute a command in our main container. So here we're also going to write to /timing just to see when this command will execute. And then the pre-stop is also going to write to our file and then is going to sleep for 10 seconds. In the init container is not going to write because that is a separate container, so we would not get that information anyways. We would have to use a volume to share information between the init container and the main containers. So let's run this, and I'm going to show you this in a split screen. So I'm going to use a tool called screen, and I'm going to split my screen. Here at the top, I'm going to run watch n1 kubectl get pods. There are no pods currently. And then here in this other screen, I'll create a pod. And then I will also read this timings file. Kubectl create -f of this lifecycle YAML file. I will press enter, lifecycle created. And now we can already see that it's running the init container. So the init container, which runs first. Let me kubectl execute -it. You see now that the pod is initializing. So I will do cat timings or timing. And we already have the main pod running. So first we have running, that is the main container. Then we have post start and then end post start 10 seconds later. And now the readiness probe. So let me tail this instead. Tail timing -f. It's going to be easier. So the main container started. Now that says running. Then we have the post start that starts. So these two start together. The main container and the hook, the post start hook, start together. It takes 10 seconds. And then we have the end post start. And then after the initial delay, we have the readiness probe and the liveness probe. So those will execute. Both of them will execute as long as the main container is alive. The main container will be alive for 120 seconds. So we still have status running, which means it's still alive. We still see the liveness and the readiness probe. Just have to wait. I will just pause the video for a second and wait until the container stops. And now the container is completed. And then the command is terminated with exit code 137. So the pod has been terminated and the stop hook is also executed, but you don't see it anymore because the sleep command has been terminated. The pod is again running because remember, the liveness check will restart the container when the probe fails. So in this case, the probe failed because the command has been terminated. What's going to happen then is that the liveness probe is going to restart container. The readiness probe will make sure that the container is not in ready status, so that there's no traffic sent to the container. And when the container is started, the readiness and the liveness probe will do their checks again. And when the readiness probe succeeds, the IP address of the pod will be again added to the service and the pod will start serving traffic again. So you can use this file and execute this on your own system to see how this works. These init container and the hooks are very useful to use to execute commands at certain times of your pod lifecycle. In this lecture, I'll be talking about secrets. Secrets provides a way in Kubernetes to distribute credentials, keys, passwords, or secret data to the pods. Even Kubernetes itself uses this secrets mechanism to provide the credentials to access the internal API. That means that pods have access to secrets, and those secrets must be distributed using this secrets mechanism. In the demo, I will show you exactly how that looks like. You can also use the same mechanism to provide secrets to your application. If you have an application that needs credentials, you can use this same mechanism. Secrets could be, for instance, a database login and password, or anything that needs to be kept secret. Secrets is one way to provide secrets, native to Kubernetes. There are still other ways your container can get its secrets if you don't want to use the secrets in Kubernetes. For instance, you could be using an external vault service in your app. There are external vault services that you can use that your app might be contacting. So you can write that completely in the app layer. You don't really need Kubernetes for that. I'll be explaining this native Kubernetes secrets in the next coming slides. Secrets can be used in the following ways. You can use secrets as environment variables. So in your application, you will just have to read the environment variables, and that's where the app will then find the secrets. You can also use secrets as a file in a pod. This setup uses volumes to be mounted in a container. In this volume, you have files. So in your container, you're going to have a volume. It means it's just a directory that your app can access that contains then those secrets. It can be used, for instance, for .env files, if you are familiar with those, or your app can just read this file or these files. So your app, you can just write some code that says you need to go and look in the specific directory for the secrets that you need, for instance, to connect to a database. You can also use an external image to pull the secrets. Obviously, from a private image registry, you cannot put your secrets in a public image registry. In that case, it would mean that you will have a second Docker image and that image would be pulled and your app would then read the data that contains the secrets from that image. First, you need to generate the secrets. So you have a login and password and you need to put that in Kubernetes. To generate secrets using files, you can use these commands. So first we're going to create those files. If you don't have them already, you're just going to create a file username.txt, I'm going to put root in that file, and we're going to create a file password.txt, and we are going to put the string password in that file. Then you can say kubectl or kubecontrol, create secret generic, it's a generic secret, you give it a name, and you say from file username.txt and from file password.txt, and then you have the secret database user pass that has been created that you then later on can use. A secret can also be an SSH key or an SSL certificate. Here you say kubectl create secret generic, you give it a name again, SSL certificate, and the from file is a key rather than a username or a password. So that's a way to distribute keys, for instance. If you want to generate secrets using the YAML definitions, previously we always used YAML files, you're going to create a file secretsdb secret.yaml, And this definition is going to be of kind secret. You're going to give it a name, a type, and then you're going to supply the data. Here you're going to supply base64 strings. On the right, you see how you can generate those base64 strings. So you need a Linux or Mac machine, or you can search online for a base64 generation tool. You say, I have the string root, or you have the string password, and you generate a base64 string for that. Then you use that in your YAML file. After creating the YAML file, you can just use Cubectl to create the database secret. Once the secrets are created, then you can use them. At that point, you have the three options. I will show you the two most common ones, which is the files and environment variables. If you're going to use environment variables, you can create a pod that exposes the secrets as an environment variables. Here we have the pod definition that we always have been using. And what you're going to do is you're going to add env, you're going to give your environment variable a name, and then you're going to say that you want to have the value from another source. The source is going to be the secrets, and you're going to say that the name in the secret is database secret, and the key that you want is username. Database secret is the name of the object in Kubernetes. The key is username. The value will be then the secret value that you stored in Kubernetes. You can do the same with other environment variables that you want to have in your pod. Alternatively, you can provide the secrets in a file. Here we have a volume mount within our container that you want a volume. Volume mount, we give it a name, we give it a path. So this is the path that your app will have to use. It's etc creds. Read-only true, your app that is running in this container cannot change this, can only read this. And then we're going to have a volume definition. And in this volume definition, you're also going to define a name, cred volume. So this name, cred volume, must be equal to the volume mount, because in the volume mount, you're referring to a volume here that you're creating. This volume exists of secrets. So you're going to say secret with a secret name, database secrets. So all the keys and values of database secrets will now be inserted, will now be put in this etc creds folder, and the secrets will be stored in etc creds, database secrets, the name of the secret, and then the keys. You have the key username and password, so you will have two files, username and password, that the application can then read. The only thing that the application needs to do is read those files, and it can then use the secrets within the application. Using volumes and using environment variables, using these two ways, I will show you in the next demo. I am going to show you two demos using secrets. One demo will just be my very simple example app. And in another demo, I'm going to show you how to set up a WordPress using secrets as environment variables. Let's first start with the first one, secrets as volumes. I first need to set up the secrets. In my deployment, I have hello world secrets.yaml. This hello world secrets has the username and the password. Kubecontrol create of this file, deployment hello world secrets.yaml. And then I have another deployment. I have a hello world with secrets as volumes. 3 replicas of this one, 1 container, a volume mount, and this is the volume with the secret name db secrets, the one I just created in Kubernetes. And this will be mounted under etc creds. Kubectl create again. And then let me just get the pods. All of them are running. Let me describe one of them. Describe pod. And what I want to show you first is what I mentioned in the beginning, that Kubernetes itself also uses the secrets in volumes to share the Kubernetes credentials. And that you can see here, Volume mounts, we already have a volume. var run secrets Kubernetes service account from default token. This is a volume that is already mounted and is done by Kubernetes itself to share the secrets within the pod so the pod can access the API. And then we have the etc creds, the one that we created from the cred volume. So let's start a shell, kubectl, execute the pod name. We're going to execute something on the pod. I'm going to add some flags to enable standard input that we can actually type in some commands. And then we're going to execute /bin/bash, which is a shell. And this just gives us a shell on one of the pods. If we then take a look at what's in etc creds username, then you see root is in username and password is in password. So our credentials are available in this etc creds, and your application just has to read those files, and then those values, the data in those files, can be used, for instance, to connect to a database. And that's exactly what I'm going to show you in the next demo. I'm going to show you how to use credentials to spin up a database and WordPress. If you enter mount, then you can also see all the mount points, and here are the two volumes that are mounted. So this one is the default one. If you can have a look at it, it has a token and a certificate that can be used then to access the API. Exit if you want to exit from a shell, and then you're ready for the next demo. In this demo, I will show you how to set up a WordPress using the secrets. It's not a fully working WordPress yet. The more features of Kubernetes you will see, the more I will change the setup a little bit. And at the end of the course, you will actually have a WordPress that is working. We don't know how to use stateful containers yet. That's why whenever you're going to put data in this WordPress, it's not going to be persistent. Whenever your pod shuts down, the data is gone. But that doesn't stop me of showing you already what we can do now using those secrets. So the WordPress files are in a directory called WordPress in my GitHub repository of the Kubernetes course. The first file I want to show you is the WordPress secrets. This WordPress secrets has one secret, a database password. You can change this database password into something more secure, but this is just password. Then we are going to need a deployment. So I have a file called single deployment, no volumes, because we're not using any volumes to persist data yet. That's why I called it that way. It only has one replica. It's just one deployment of our app WordPress. This deployment has two containers. WordPress is a blog software, in case you didn't know yet. This has a container that is referring to the image WordPress version 4 with PHP 7. This container is one of the official WordPress images, and it comes with PHP and Apache, which is the web server. So it's a website, it's blog software, all bundled within one image, and that's what we're going to pull from the Docker repository. It's going to expose port 80, and we need to provide some of the environment variables. We need to provide a password of the database, and that's why we're going to use this WordPress DB password. And if you're wondering why I know this name of this environment variable, this is all explained on the website hubdocker.com of WordPress, and I will just show you that. This is the official repository for WordPress. It's a rich content management system and can utilize plugins, widgets, and themes. And then here you have how to use this image. And then you can see we have a WordPress DB host, WordPress DB user, which is root, that we're not going to change because root is fine for us, and then a password, which we are going to set. You can also change the database name, the table prefix. You can set some other settings like an authentication key and so on. But if you don't set those, then it will be auto-generated, which is fine for us for now. We also have different images. We are going to use the one with PHP 7 and Apache. But you can also use the one without Apache. You can put an Nginx in front of it if you want, but that would make it a little bit more complicated. So we're just going to keep it relatively simple for now. So that's how I found out about this WordPress database passwords. And the value for this key, for this environment variable, is going to come from the WordPress secrets. And I'm going to use the database password for this. The next environment variable that I'm going to define is the WordPress database host. And I'm going to use 127.0.0.1, which is basically localhost. Because this is going to refer to another container, the second container that I have in this spot. I have a MySQL container, which is a database. MySQL version is 5.7. This is also an official image from Docker Hub. So you can also take a look at Docker Hub to read the instructions. It exposes the standard MySQL port 3306. And we're also going to define an environment variable with the MySQL root password. And this MySQL root password is going to have the same value as this one, which is the password that comes from our WordPress secrets. So the password needs to be the same because our database will be set up with this password. The login will always be root. And we also want to let our application know that it can log in using the same password. You can set some more environment variables, but this will do. We have one pod, 2 containers, and only 1 replica. Because if you would increase this to 2, we're going to run 2 databases and it's not going to make sense. We only want 1 database and 1 WordPress in front of it. So let's launch this one. Cubectl create -f of the secrets. Secrets first, WordPress secret. Secrets created. And then now we can create the deployment. WordPress deployment created. So let's have a look at the pods. I still have my hello world from the previous demo. And then here I have the WordPress deployment running. 2 containers this time. Cubectl get or describe pod. And here we have the 2 containers running using our secret. To reach this WordPress, I need to make a service. So I also have a WordPress service that is going to target my HTTP port for my pod. It's the service for the app WordPress, and is going to expose this port as a node port. So type node port. Cubectl create -f, and then Minicube service WordPress service, and then URL. And then I should be able to access our WordPress. I'm going to do this in a web browser. And then here we have our WordPress. So we just need to do some setup. This is going to be my blog, my username. I can use this password. My email address. You can discourage search engines from indexing this website. It's not even online, it's just on my PC. And then you can say install. And then it is installed. It goes very quick. And then you can log in. So I can now log in. And then welcome to WordPress. So I have my dashboard. It's all working. And then if I click on visit website, I can actually visit my blog website. So it was that simple to set up a blog. But it's not fully working yet. Because this container is still going to write some data to the local image. If I'm going to upload media, like images, then those images will be written on the container. If that container restarts, all my images will be gone. So we'll have to find a solution for that. And I will show you what happens when the pod gets killed. Cubectl get pods. So let's say that our pod gets killed. Cubectl, I'm just going to delete my pod. which will be launched again by the deployment. So my pod is deleted and a new pod is launched. But what's going to happen now? Because we launched a MySQL that contains all the data, the installation that we have done now, my login and password that I filled out. But like I said earlier, those images, they boot up. You can write some data to that image, but when you restart a pod, it's nowhere saved because there are no data mounts, there are no volumes that we are using yet to keep the data saved somewhere. It's just if a container restarts, the data will just be gone. So what then happens if our pod gets rescheduled or is killed? Well, I will just refresh this page and all the data is gone and I can just reinstall WordPress because my database is completely wiped. It is reinstalled because the data was not saved. There is still something that we have to find a solution for, and I will explain the solution in the volumes lecture later on. But for now, it's already a very interesting lab because this already touches a lot of things. We had a deployment, a service, secrets, environment variables, and multiple images in our pod. Let's talk about the web UI. Kubernetes comes with a web UI you can use instead of the kubectl commands. You can use it to get an overview of running applications on your cluster and for creating and modifying individual Kubernetes resources and workloads, like kubectl create and delete. Retrieve information on the state of resources, like when you use the describe pod command or describe deployment. In general, you can access the Kubernetes web UI at the Kubernetes master URL/UI. If you cannot access it, for instance, if it's not enabled on your deploy type, you can install it manually using kubectl create, and then you can use the YAML file straight from the Kubernetes repository. If a password is asked, you can retrieve the password by entering kubectl config view. If you're using Minicube, you can use the following command to launch a dashboard. Minicube dashboard is going to open your browser and will go straight to the URL. If you just want to know the URL, you can use Minicube dashboard --URL and then you can copy paste it yourself in the browser that you want. In the next demo, I will briefly show you around the web UI. In this demo, I will show you how to add the web UI in kops. In my Vagrant Kubernetes course, my Git repository, I have a directory dashboard. In this dashboard, I have a README that you can use to start your dashboard on kops. In earlier releases of kops, it was pretty easy to start a dashboard, but in newer releases, they added RBAC by default. So you have to also add a user to be able to log in. To start a dashboard, it's still the same. Although the URL is a little bit updated, but it's still a kubectl apply. So I'm going to do that first. And this is going to create the dashboard. Then I'm going to create a sample user. So this is a user that I'm going to add to the account. This is a service account. It's called admin user. And this is a cluster role binding to bind to this user, this admin user, to bind a certain role. And the role I'm going to add is cluster admin. So we're going to add a user that will be admin, a user that will be able to do everything. Going to create this new user. This new user is created. Now that this user is created, I can retrieve a token. So if I do kubectl in the kube system namespace get secret, and I'm going to filter on admin user. Then I will see here I have admin user token and then this random string. And if I describe this secret, then I can see the secret. Using this token, we can now log into the cluster without using our certificates. So by default in kops, we are using certificates to log in. Those certificates are configured here in kubeconfig. So rather than using those certificates, we're going to use a token. And then the last thing that we need is the password. So if you do kubectl config view, or we just open the editor and edit the config again, then we see the admin login and password that we need to log into the API server. So we're going to log into the API server, enter admin and then password, and then use this token to log in. So let's try that out. So this is the first login. I'm going to enter admin and my password to log in as an admin. And now I am logged into the API server. To access the UI, I just type /UI, and then I will be redirected to the UI, to the Kubernetes dashboard. Two ways to log in, using kubeconfig or using a token. Even if you use kubeconfig, you still need to have your token configured in the config, so it's easier to just copy paste this token here. From here, we can copy paste the token that we need to log into the dashboard. Going to enter this token, click sign in, and then I'm logged in to the dashboard. Here you have an overview of what I am running right now in my cluster. So you can just go a little bit around, click on the links here to see what is running on your cluster. In the next demo, I will show you the same with Minicube, and then I will also go over some dashboard items. In this demo, I'm going to walk you through the web UI. If you're using Minicube, Minicube dashboard URL gives you the correct URL that you need to access the dashboard. If you are on AWS, you can use the commands from the theory to launch your dashboard. In the end, you should both see something like this. This is the Kubernetes web UI. Here we can do exactly the same as with our command utility, kubectl or kubecontrol. We can get information from the namespaces. This divides the cluster in multiple namespaces. We have the default namespace, that's where we have been deploying our apps in. We have one node here, Minicube, the labels, it is ready and it's already ready for 4 days. The allocated resources, so here you find some useful metrics. We have 2 GB of memory approximately. We have 4 of 110 pods running. It's a boot to Docker image. So we can say, we can go to deployments, for instance. We have deployments, replica sets, replication controllers. Most of these things we've already seen. Pods as well. And then the other ones I'm going to cover in the advanced section. And we have services, ingress, volumes. I'm going to cover later. Persistent volumes I'm also going to cover later. Secrets we've already covered. And then config maps is going to be very soon. Deployments, we can just click this create button and you could create a deployment right here. You can specify these app details here, or you can upload a YAML or a JSON file. Rather than using YAML files, you can also use JSON files. It's just a syntax difference. So let's say that I start our hello world deployment. Then if I click on deployments, you see our deployment is now running. It has a label. Well, it is actually spinning up right now. It's not running yet, but now it is running 3 out of 3 pods. And we could just delete it from here again. So we can do the actions here. We also have the details here. It's just a dashboard. You can do exactly the same things as with Kubecontrol. So if you don't really like the Kubecontrol tool and you rather have a UI, you're free to use this one rather than the Kubecontrol. I will continue with Kubecontrol in the next lectures. The next coming lectures are part of the advanced topics. So now you have covered all of the Kubernetes basics, and now we're going to start with advanced topics. The first topic is service discovery using DNS. As of Kubernetes 1.3, DNS is a built-in service launched automatically using the add-on manager. Before 1.3, you had to enter some commands. Now it is already launched automatically. The add-ons in Kubernetes are in the etc Kubernetes add-ons directory on the master node. You might want to take a look there if you are interested in other add-ons. The DNS service can be used within pods to find other services running on the same cluster. Multiple containers within one pod don't need this service, as they can contact each other directly. A container in the same pod can connect to the port of the other container directly using localhost port. So if you have a web service and a database service, then the web service can just connect localhost and then the port of the database, and it will be able to access the database within the same pod. If you want to connect from a web service in one pod to a database in another pod, then you need service discovery because you cannot just access this other pod. You don't know the IP address or port. To make DNS work, a pod will always need a service definition. So only when you create a service for a pod, then the pod really becomes accessible and service discovery will work. So this is an example of how one app could reach another app using DNS. So on the left we have application 1, we have a container in a pod and a service for that pod. The service is app1 and has IP address 10.0.0.1. Then on the right we have application 2. We also have a container in a pod and this has another IP address. It has IP address 10.0.0.2 for service app2. If you would execute commands on the container of pod 1, for instance host app1 service, the name of the service, then you would get the IP address back 10.0.0.1. This is the service discovery in action. You only need the name of the service to find the IP address of that service. If app1 wants to contact app2, it can do a DNS lookup on app2-service and it will get IP address 10.0.0.2. This is only going to work if both applications are in the same namespace. The standard namespace that we have been launching in is the default namespace, because we haven't really specified a namespace. What does that mean? Default stands for the default namespace. Pods and services can be launched in different namespaces to logically separate your cluster. You can have different namespaces just to logically separate your cluster. Default is the default one. There's also kube system where the Kubernetes services run in. If you would want to specify a namespace, then you just do a DNS lookup of app2 service.default, where default is a namespace. If you want to do a lookup on the full hostname, the full hostname is actually the name of the service dot the namespace dot svc for service.cluster.local. And this whole hostname also resolves to 10.0.0.2. This is how one application in one pod can access another application in another pod. These requests here are always on the A type, which is resolving from a host to an IP address. There's also an SRV type if you want to know the port number. So here we just have the IP address, but it's also possible to get the port number. So how does it really work? How does this DNS really work? So let's say that we have a pod. See pod 1 on the left with a container. We can start this container using kubectl run busybox. We're going to run the image busybox, which is just going to give us a shell. And if you use cat to show the contents of a file, here we want to show the contents of etc resolve.conf, then you can see that the name server points to 10.0.0.10, which is the DNS server. And the DNS server is kubedns running in another pod, exposed as a service with IP address 10.0.0.10. And the reason why you didn't see it when you did kubectl get pods is because it runs in another namespace. If you would do -- namespace equals kube system, when you do kubectl get pods, you would see that there are pods running anytime when Kubernetes is running. The reason then why we can use the service name or service name.default or service name.svc.cluster.local, you can see here in the line with search. In Linux, when you look up a DNS name, this can be automatically added. So it will, if you just do a lookup of the service name, then actually it will do a DNS request of service name.default svc cluster.local. So this is how it works under the hood. DNS resolving can help you to do service discovery. In the next demo, I'm going to run a deployment, which is a web app and I'm going to run a separate service. And then you will see that just using DNS names, our web app will be able to find the database, which is the other service. That's for the next demo. So you can just continue with the next lecture, which is the demo. In this demo, I'm going to show you how service discovery works. I have here a folder, service discovery. I'm going to create a few resources again. Or let me first show you what's in it. I'm going to use cat, service discovery, first credentials, the secrets. I have a couple of secrets, a username, password, root password, and a database. I'm only using root password and database actually. I'm going to use the root password rather than using a separate username and password, because that needs extra setup and I want to keep it as simple as possible for this demo, just to show you service discovery. Cubectl create, and I'm going to create a pod, and this is going to be my database pod. So I have here a database again. The name is database, container is MySQL 5.7, runs on 3306, specify a root password, a user, and a password, and a database. I also have a service. It's going to expose a node port, a random node port, kube control create -f service discovery database.yaml and service. Then I have a hello world database.yaml and a service. This one is interesting. It's a deployment. 3 replicas of my Kubernetes demo. I also call it hello world database. It's the same image, but this image also has an index-db.js in the same folder. You might have noticed that when you did the Docker build, that there also was an index.db. If we specify command node index-db.js rather than using npm start, which is executing node index.js, I can override this in my YAML file. So I can execute different commands on my image. For us, it's all the same, Node.js port 3000. But then I'm also adding environment variables here. Host, MySQL user, password from the root password, and a database from the secrets, and the key is database. It's going to run index database, and this is going to connect to our database, and it's going to use the host database service. So this will only work if the DNS resolving works, because my database service is called database service. So this value of the MySQL host needs to resolve to the IP address of this service database service. And then my app will be able to connect to the database. Let's try that out. I'm going to do a create of this hello world database.yaml and this hello world database service.yaml. So this service is very generic. It's just going to also expose my hello world DB. Minicube service, hello world DB service, and I just don't know the URL. So it's going to be the URL that I'm going to connect to. Let's first check whether everything is running. So I'm going to get pod. So we have one database, which is just a pod, and then we have 3 pods for our deployment. All of them are running. Let's check the logs of this pod to see whether we were able to connect to the database. It says connection to database established. So in Node.js, it was able to connect using these credentials to the database. The only thing that this index-database.js does is it's going to create a table, and there is going to be one column that is going to initialize a value at 0, and every time I'm going to do a hit, it's going to do +1. Just instead of the hello world, it's going to do a +1. So hello world you are visitor number 1. You are visitor number 2, you are visitor number 3, and so on. So this is stored in the database. So it actually works. This hello world deployment, this pod, connects to the database service and inserts data in the database. How can I check this? Well, let me do kubectl exec database. I'm going to log into the database. I'm going to execute something on the database, -i, -t, and the command I'm going to execute is MySQL. I'm going to log in as root, and I'm going to give a password. Password is root password. It was defined in the secrets. The database. So show databases. The database is hello world. So I'm going to do use hello world. Show the tables here, and then select star from visits. So this was created by my app. There are 4 records, 4 visits, and this is just a timestamp. So this works. My app was able to discover this service and connect to the database. And this because DNS resolving works, which I could also test by opening a shell on one of the nodes, and I actually need a busy box because I need to do resolvings. So I'm going to do kubectl run busybox, and busybox has NSLOOKUP. So with NSLOOKUP, I can then check whether my service works, my service can resolve. So I'm going to do hello world database service. I'm going to look up, and yes, that works. kubedns answers with hello world database service is at 10.00.52, and this is the full host name. So let me do this NSLOOKUP again, because here we have an overview of our cluster IP addresses. So it will be easier to show you which one is which, because these names are quite confusing. So if I want to find out which is the database service, I can do NSLOOKUP database service. If I want to do a DNS lookup on the service, which is the app layer in our case, then I can do an NSLOOKUP on this one. So I don't have curl here, so I actually need to telnet to this service, and then a get slash gives us you are visitor number 5. So if I just want to connect to the app layer, I can use hello world database service. If I want to connect to the database service, the MySQL, the database, then I can use this host name. And this database service resolves to this IP, and this other service resolves to that IP. And whenever this service will be recreated, DNS would then also be updated. That's it for the DNS discovery. This is also going to be part of our WordPress later on, so I will come back to this. Service discovery is a very important part of running a cluster with lots of services. Ctrl D if you want to exit, and delete pod busybox if you want to delete the busybox. And you obviously have to delete all the running services and pods and deployments. I will now be talking about config maps. Configuration parameters that are not secret, not like credentials, can be put in a config map. The input is again a key value pair. Just like credentials, you had username, password, here we have another key value pair. The config map key value pairs can be read by the app using environment variables again. Also, you can use container command line arguments in the pod configuration, or using volumes. A config map can also contain full configuration files, where the value is actually a configuration file and not just a short string. For instance, a full configuration file can be a web server configuration file. This file can then be mounted using volumes where the application expects its config file. This way, you can inject configuration settings into containers without changing the container itself. Just imagine that you want to use the Nginx container and you of course want to change the configuration, and then you inject that configuration file as a volume in that image. You didn't change the image at all, just the configuration file is different, and you can run any container with the configuration that you want. To generate a config map using files, where you first put your data in a file, you can use the following commands. This command will just get the data that you write on terminal and then put it in app properties until you write the letters EOF. So here we have driver equals JDBC, database equal Postgres, and so on. This is a properties file, key value pairs, and this file we're going to read using kubectl create config map. We're going to call it app config, and we're going to say from file app.properties, and then you have a config map. This is just a very simple config map where you just have very short strings. You don't really have a configuration file, but you could also use a configuration file. And that's what I'm going to show you during the demo. How do you use a config map then? You can create a pod that exposes a config map using a volume. Here we have a pod, still our Kubernetes demo, still container port 3000. We have volume mounts. The name is config volume and the mount path is etc config. So we're going to mount a volume in etc config. The volume itself is just referring to this config map that we used earlier. And then the config values will be stored in files. You will have, for instance, from the previous one, etc config driver, and then the value will be in that file. You can also use hierarchy. If you would use dots in the name, then you can have param.with.hierarchy, then that translates into param as a directory, with as a directory, and hierarchy as a file with the value in. So you can also create hierarchy in your config map. Here is the same example of a pod that exposes the config map as environment variables. You can use env, name, you can say for instance driver, value from, so this is exactly the same as what we did with credentials, but then we have config map key reference rather than the reference from our credentials. You pass the name and a key, and then the value of this environment variable driver will be the value of the config map of the key driver. In the next demo, I'm going to show you how this works using a configuration file. We're going to run an Nginx in front of our pod demo. We are basically going to run a reverse proxy, and we need to update the configuration file for that. That's why we need config map. In this demo, I'm going to show you how config map works. In my Kubernetes course, I have a configuration file for our Nginx. I have directory config map, and then I have reverseproxy.conf. And this configuration is going to make sure that our Nginx is listening on port 80, that the server name is localhost, and that whenever it gets a hit, that it's going to forward its request to this URL, where the hello world Node.js will be running on port 3000. So I'm going to add this reverse proxy conf to config map. So I'm going to create config map, nginx config, from file, config map, reverse proxy.conf. The config map is created. If you want to see my config maps, then I see that this nginx config has been created, and I can also ask to give me the output in YAML format. So this config is now with the key reverse proxy conf in the config map with the name nginx config. Let's have a look at my pod configuration that I'm going to launch. I have nginx.yaml. Hello world-nginx is going to be my pod name. I have two containers. One is going to be the nginx container, the other one the Kubernetes demo container. One is running on container port 80, the other one on 3000. My Nginx has a volume mount with the name config volume, and the mount path is etc nginx confd. This is a predefined configuration path where Nginx, this image, will be looking for its configuration. This config volume is defined here. It's a config volume. It has the same name, so this name here is matching. It's going to look for the config map with name nginx config that I just created for the key reverse proxy conf. So name nginx config, key reverse proxy conf, and is going to put that file with the same name reverseproxy.conf. I can execute this, kubectl create -f config map nginx.yml. I'm also going to create a service. This service is just going to expose a node port, Minicube service nginx, hello world nginx service URL. Let's have a look whether my pod is running. It's all running, so I can do curl, and I'm going to add minus and some v's, which is going to increase the verbosity. It's going to show me who is answering to this request. And it is Nginx that is answering to my request, and it is forwarding it to my other container in this pod because I'm getting hello world back. So this is how I can put an Nginx reverse proxy in front of my Node.js. So let's have a look at this container itself. Kubectl, I want to execute something on my hello world Nginx pod, and I actually want to log in into the container because we have two containers. I need to specify this now of Nginx, and I'm going to execute bash. This is my container, Nginx is running, and now let's have a look. etc nginx confd, and here I have my reverseproxy.conf. So it wrote this config, this process read this config, and then it is forwarding this request to my Node.js. That means that at this point you could, for instance, enable SSL on your Nginx. It can handle the requests for your underlying Node.js app. You could use the same system for, let's say, PHP. You could have an Nginx that then connects to another container that is then going to process the PHP for you. So then you have a container Nginx and PHP, and then you also need separate configuration files. So you need to then configure some PHP directives rather than directives for the proxy for Node.js. So config map allows you to inject configuration files, to inject configuration data within your application. Let's talk about Ingress and the Ingress controller. Ingress is a solution available since Kubernetes 1.1 that allows inbound connections to the cluster. It's an alternative to the external load balancer and the node ports. So it's a very interesting alternative for cloud providers that don't have a load balancer. Ingress allows you to easily expose services that need to be accessible from the outside to the cluster. With Ingress, you can run your own Ingress controller, basically a load balancer within the Kubernetes cluster. There are default Ingress controllers available from Kubernetes, or you can write your own Ingress controller. Basically, you can even write your own load balancer. This is how it works. If you connect from the internet over port 80 or 443, which is HTTP and HTTPS, you're going to be hitting this Ingress controller. You configure what pod needs to be handling the connections from the Ingress controller. You can use an Nginx Ingress controller that comes with Kubernetes. That Nginx Ingress controller is then going to distribute the traffic to your services. So you can have application 1 that can receive traffic from your Ingress controller and application 2. Which one is going to receive traffic is going to be based on rules that you define in this Ingress object. Some of the Ingress rules can be that if you connect to host X, example.com, then you go to pod 1. Do you connect to host Y, .example.com, then you go to pod 2, and application 2 in our case. You can also make rules based on the path. So the first two were rules based on the host. You can also make a rule, for instance, /API v2 needs to go to pod n, like another pod, a third application, for instance. You can create those ingress rules using the ingress object. You can see that the API version here is still in beta. At some point it's going to come out of beta and you have to change this, but for now this is an extension that is in beta. The object is of kind ingress. We give it a name, hello world rules, and then you're going to specify those rules. You can say if it matches the host hello world v1 example.com, then do an HTTP forward to this backend that is described here. You can specify a path, it's just slash. The backend in our case is going to be hello world v1, which is a service that we're going to launch, and this service runs on port 80. Then we're going to have a second host, hello world v2 example.com, also HTTP forward. Path is also slash, and we have another backend. So depending on which host you're going to hit, you are going to get to a different application basically. These example.com hosts are non-existent, but you can configure your own domain name, your own host name. Or you can just work with paths and you can say /v1 goes to my v1 application and /v2 goes to my v2 application. That's also possible. In the next demo, I will show you how this works. In this demo, I'm going to show you an example of an ingress controller. First, let me show you how the ingress controller works. I'm going to use the Nginx ingress controller, which is an existing one. This is a replication controller, so if this one would crash, it would be automatically relaunched. It's called the Nginx ingress controller, and it's an image that comes from a Google container. It's an Nginx ingress controller, and it's this version here. It's going to check the health. We have a readiness probe to know when the container is ready, when we deploy it, and then we have the liveliness probe to periodically check whether our container is still healthy. We're going to specify a pod name, which is our pod name, and the namespace, which is default in our case, unless you specify another namespace. We're going to run this on port 80 and port 443. This ingress controller is going to be working on the standard HTTP port and the HTTPS port. It's going to give these as arguments when it's going to launch the container. So this is the ingress controller that you could write yourself even if you want, but we are going to use one that already exists. We are also going to say that the default backend service is the echo headers default. And this is a service that I'm going to launch. Traffic will be forwarded to this service when there's no match. So I'm going to say these hosts, I'm going to say in my ingress rules, these are the hosts, hello world v1 example.com and hello world v2 example.com. If those don't match, then go to this default service. Let me just kubectl create all those things. I'm going to create the ingress, the object, the controller, the echo service, the hello world v1, and the hello world v2. So these are just services that we're going to access. This is our hello world v1 app, and this is our hello world v2 app. So the only thing that's different between those two is that I'm asking for image version 2, and the other one is just asking for the standard image. Let me check if the pods are up. Yes, they are running now. Let me get the IP address. Minicube IP is just going to give me the IP address of my cluster. If you're testing this on AWS, you have the IP addresses in the EC2 console. You just might have to change your security groups to make sure those ports are open. I'm going to curl this IP address. What's going to happen then? I'm not specifying any hosts. Those are non-existent hosts. So I cannot just go in my browser and type them in because they actually don't exist. You could use real world hosts and then you can just use your browser. I'm just going to give an argument to fake that I'm using those hosts. I don't specify any host, so I'm going to hit this default backend service echo headers default. And this is just going to give the HTTP headers. So curl, I'm hitting this default service now. Let me now pass a header. I'm going to pass the host, and the host is going to be hello world v1 example.com. This curl command has the same effect as going to a real DNS name in your browser. This gives us hello world. So our ingress controller forwarded us now to my hello world v1 deployment. Let's now try v2. And what do I get? Well, I'll show it better. Hello world v2 here. What do I get? Hello world v2. Now our ingress controller forwarded us to hello world v2, to my second hello world. And I'm pointing now towards the pods, but actually I should point towards the services. So this is the default one, and this is if we hit v1, and this is if we hit v2. This is just one from the previous lab, so don't worry about that one. So that's how the ingress controller works. We basically have the capability, it's still in beta now, but it will become stable. We have the capability to just run a load balancer inside our cluster that is going to redirect the traffic to the correct host for us, which is a viable alternative if you don't want to run an ELB or an external load balancer from your cloud provider, because those also cost money and don't have all the capabilities that you maybe need. Because when you write your own controller, you could add all the features that you want. Things like enterprise authentication if necessary. Now that I've shown you how to use the ingress controller, I want to show you how to use external DNS. In the previous lecture, I explained to you how to set up an ingress controller. On the public cloud providers, you can use ingress controller to reduce the cost of your load balancers. You can use one load balancer that captures all the external traffic and sends it to the ingress controller. This as opposed to use many load balancers, one for every app. The ingress controller can be configured to route the different traffic to all your apps based on HTTP rules, host and prefixes. This only works for HTTP or HTTPS based applications. So you need to be able to apply rules based on host or prefixes. If your app doesn't do HTTP or HTTPS, then you cannot use this approach. Then you just create a new load balancer for that app. One great tool to enable such approach is external DNS. This tool will automatically create the necessary DNS records in your external DNS server, like for example root 53. For every host name that you use in ingress, it will create a new record to send traffic to your load balancer. So it will create this new record in your DNS server, like root 53. So that when you use a new host name in your ingress controller, this host name will be automatically created and will be routed to the load balancer and to your ingress. The major cloud DNS providers are supported: Google Cloud DNS, root 53, Azure DNS, Cloudflare, DigitalOcean, and so on. Other setups are also possible without ingress controllers. For example, directly on the host port or using the node port. The node port is still work in progress, but it will be out soon. Let me show you how this external DNS works with a diagram. So we have the internet, we have two pods in our Kubernetes cluster, we have the Nginx controller in one pod and the external DNS in another pod. We have one service in front of our ingress, and that service is of type load balancer, so that service spun up the AWS load balancer on the left here. We're going to add a few ingress rules. So here are 3 rules, and these rules will be read by the Nginx ingress controller. The external DNS tool will also read those rules and will see that it needs to create DNS records for host X, example.com, and host Y, example.com. So external DNS will create those records in AWS root 53 for example, it can be any external DNS provider, so that host X and host Y are going to point to the AWS load balancer. Then the client comes in, it's going to go to AWS root 53 to get the IP address of a host name, for example, host X example.com. Root 53 will reply the IP address. The IP address will be of the load balancer, so it will connect to the load balancer. Load balancer will connect to the ingress service. Ingress service will redirect the traffic to the ingress controller. Ingress controller will read the rules and will see that it needs to route this request to Part-1. So that's how it works in a nutshell with external DNS, the Nginx ingress controller, and an AWS load balancer. This setup I will show you in the next demo. In this demo, I will show you how the external DNS works. In my GitHub repository, I have a folder external DNS, and here I have a README. This is the project page. If you want to read more about it, or you want to read more about the different setups that are available, we need to do a few things before we can use this external DNS. First, we need to create an IAM policy, because we need to give permissions to our nodes to create these DNS records. I have a script for this. This script adds permissions to the node's IAM role, enabling any pod to use these AWS privileges. Usage of Cubectl IAM is recommended, but not yet implemented by default in kops. So this rule will add privileges, but it will add it to every node, and every pod can use it, which is not really desired, but it's still a shortcoming of the default deployment of kops. They are implementing Cubectl IAM, which resolves this, which makes sure that you can put IAM roles on a pod basis rather than on a node basis, but it's not implemented by default, so I've chosen to do the demo this way, and when there's a new version of kops, then there will be a better way of using IAM roles. So to make this work, you need to change the node role. So this is the IAM role. For me, this is Nodes Kubernetes New Tech Academy. So you will have to change this into your cluster name. I'm going to apply this. If you don't get any output, then it is working. I'm going to apply the ingress controller again. I'm going to use apply instead of create because I'm going to make changes to some of the objects later on. You can always use apply instead of create if you want. Apply will actually allow you to make changes to the YAML files and then apply those changes again. So I'm going to start the ingress. In this setup, we still have the host port because that's what I used in the previous lecture, but actually that's not necessary anymore. So if you go to host port here, you could remove these lines if you don't want to expose this port anymore, because we're going to put a load balancer in front of this controller. So the host ports here are actually not really necessary. So you could remove those and then do an apply again. I'm going to create a load balancer for the ingress. This is going to create the load balancer. So now I have an ingress Nginx load balancer, and this will give me this host name. So if I connect to this host name, I'll end up at the ingress controller. That's why you don't need this host port anymore in this setup. Then we're going to create the external DNS and the ingress rule. So let's create these. Also, you see that here, when I did apply service l4.yaml, this service was created, but this config map was configured. If we used create instead of apply, then it would give an error because we already had this config map earlier. So that's why I'm using apply here. All this is created. Let's have a look at my ingress.yaml file. Again, here I have configured instead of apply because I already had an ingress with hello world rules. Now I applied one with the same name. So we are having two hosts, Hello World v1 Kubernetes New Tech Academy and Hello World v2 Kubernetes New Tech Academy. Let's have a look at the pods. Should have an external DNS pod. Let's have a look at the logs. kubectl logs. And now you see we have the Hello World v1 Kubernetes New Tech Academy and v2 added. So all the records are up to date. There's also a record for Ingress Kubernetes New Tech Academy, because if I have a look at service l4.yaml, then I also specified an external DNS annotation here to make sure that I also have a host for this ingress. So now you should be able to go to your browser and you should be able to reach Hello World v1 Kubernetes New Tech Academy and Hello World v2 Kubernetes New Tech Academy. Just like that. There are no more changes necessary. The external DNS created the DNS record for us and it's pointing to the load balancer. The load balancer points to the ingress and the ingress has all the correct rules. So I will use curl, but you can use your browser as well. Curl hello world v1 gives hello world. Curl hello world v2 gives hello world v2. So if I have another look at my ingress, hello world v1 goes to hello world v1 service and hello world v2 goes to the hello world v2 service. So this is all working. So this is a very nice setup that you can use to have your DNS names automatically added. So then someone could just create an application with a service, with an ingress rule, and everything gets automatically created and you can start using your apps immediately. The next coming lectures will all be about volumes. I will show you how to run apps with stateful apps. And one of the demos is also going to show you how to run WordPress together with a database, because those are stateful applications. Volumes in Kubernetes allow you to store data outside the container. When a container stops, all data on the container itself is lost. That's why up until now I've been using most of the time stateless applications, apps that don't keep a local state, but can store their state in external service. With external service, I mean like a database, a caching server like MySQL, object storage like S3 can be used for that, NFS server can be used for that. You can only use those external services even without using volumes, because S3, you could code that in your app. A database you could run as a service. Now I'm going to show you a way to run those services inside your Kubernetes cluster. And then we're going to use volumes for that, and then we can run stateful applications. Persistent volumes in Kubernetes allow you to attach a volume to a container that will exist even when the container stops. So the container stops, the pod stops, but your volume can be reattached to a new container and you can keep the state of your application. You can keep the files that are necessary for your application to run. Volumes can be attached using different volume plugins. Here you have an overview of the different plugins. On the left, we have our node with a couple of pods on, and the containers in the pod can then be used to attach a volume to. Let's say, for instance, pod 1 has a local volume attached to it, so that data can be saved on node 1 and then can be attached to another pod on the same node. The more interesting ones are the ones that don't exist on the node itself. Like if you're running on AWS, for instance, you can use EBS storage. You can attach this EBS to any node in the same AWS availability zone. Your node could completely die. You can spin up another node or you can reuse another node, reattach an EBS volume to that, and then your pod can still be working. That's a big advantage of using these volume plugins that have storage outside your Kubernetes cluster. If you're running on Google Cloud, you can use Google Disk. If you're running on Microsoft Cloud, you can use Azure Disk. And then there are some other network storage providers that you can use that you might be even implement yourself, like NFS or Ceph. Those are a little bit more complicated because you might have to set up a Ceph cluster or an NFS cluster before you can then use those volume plugins. The one that I'm going to discuss is obviously the AWS EBS volume plugin, because we can use it on our AWS cluster. Using volumes, you could deploy applications with state on your cluster. Those applications need to read and write two files on the local file system that need to be persistent in time. You could run a MySQL database using persistent volumes, for instance, although this might not be ready for production yet. Volumes are new since the June 2016 release in Kubernetes, so depending when you're going to take this course, you might still want to be very careful about this. It will become stable at some point in time. Let me show you an AWS EBS example. If your node stops working, the pod can be rescheduled on another node, and the volume can be attached to the new node. So here we have node 1 and node 2. Node 2 doesn't have any pods. Node 1 has my app, and my app is using EBS storage. Let's say that node 1 completely disappears, then what's going to happen is my app will be rescheduled on node 2, and then the container will link the EBS storage again, so that my app can access the data that was written on that storage that is in this EBS storage that is safe and outside the cluster. So this works, but only when those nodes are in the same availability zone. So let's have a look at the definitions that we need to use to create volumes. To use volumes, you need to create a volume first. In the next lecture, I'll show you how we can do this automatically, but now we are going to do this manually. So here I'm using the AWS tool to create a volume in US East 1 that is 10 GB of size. I'm also specifying the availability zone, which is US East 1A. And you need to note down this volume ID, because this is what we are going to need later on. Next, we need to create a pod, or we can create a pod with a container. This is our container that we always use. We can specify volume mounts. The mount path can be /myvol, and the name is myVolume. So this name myVolume comes back under volumes. And then we're going to define AWS Elastic Block Storage, and we're going to specify the volume ID. And that's what I'm going to show you in the next demo. In this demo, I'm going to show you how to start using volumes. I'm going to use my kops cluster again. So I logged in again in my Vagrant Xenial box. And first, you will need to create a volume on AWS. And if you're working with kops, then you must have set up the AWS tool, because that was one of the prerequisites. So I'm going to use the AWS tool to create a volume. I'm going to use AWS EC2 create volume. I'm going to create a volume of size 10 in EUS 1A, and it's going to be general purpose 2, which is just an SSD volume. Make sure that you create your volume in the same zone that your Kubernetes cluster is spun up, otherwise it's not going to work. This is the volume ID that you need to select. You need to copy paste this, and then I'm going to insert this into my hello world with a volume. So I'm going to use this volume ID. I'm going to put it right here. Volume ID, and then this volume ID. And this volume ID is going to be attached to the node that this pod is going to run on. And it's going to be mounted under /myvol. Let me first check whether my nodes are running. I have 3 nodes running. And then I'm going to launch this deployment. Hello world deployment created. kubectl get pod. Container is creating. It's pulling the image. And now the container is created. You have a volume here, my volume, which is a persistent disk resource in AWS Elastic Block Storage with a volume ID. So I should now be able to execute something in this pod. Let me just start bash, and I should have a volume myvol. Let me just write something in this myvol just to see how it works. I'm going to write test in myvol.txt. I'm also going to write text in test2 in /test.txt. So we have 2 files, myvol.txt and test.txt. And just think about what is going to happen if this pod crashes, because we wrote something in / and we wrote something in the volume. When does a pod go? Well, if the node goes, then the pod needs to be rescheduled. So this pod is running on the node with this IP address. So if you want to test what would happen if the node would be rescheduled, we could drain a node, which means we prepare the node to go offline. So we can say kubectl drain and then the node, and then it's going to start draining the node. Just going to use force here. So that pod is for sure killed. Then I'm going to do kubectl get pod, and already a new pod is being created. So if I describe this one, describe pod, and then the new pod, then you can see that this pod is now attached to another instance. You just have to wait a little bit until the warnings go away. And now the volume is attached to this new node. So what happened is that this volume detached from the old node and now is reattached to the new node. So our container has been recreated, but we are still using the same volume. So let me log in again. Let me open a shell on our new pod. And if I take a look in my vol, I will see that I still have my vol.txt, but of course, because this is a new container, I don't have test.txt anymore, because test.txt was not saved in the volume, but in the container itself. And when the pod gets rescheduled, all the information that has been written to the container disappears. So when you have a stateful application that needs to write something, then you always need to use volumes, because then your data will be kept even if the node crashes or even if the node needs to be rescheduled. And this can happen all the time. Stateful applications can only use with volumes or some other mechanism to save the data, not inside the container itself, but using a volume or using external services. In the next lectures, I will show you how Kubernetes can automatically create those volumes for you. When you're finished, make sure that you remove this volume again. So this volume needs to be deleted. AWS EC2 delete volume with volume ID and then the volume ID. Of course, when it's not attached anymore. So you can only do that when it's detached. So first you need to remove your pod, and then if you wait some time, you'll be able to detach it. In this lecture, I'll be talking about volume provisioning. The Kubernetes plugins have the capability to provision storage for you. The AWS plugin can, for instance, provision storage for you by creating the volumes in AWS before attaching them to a node. Instead of you entering the command to create a new volume, Kubernetes will make the API calls to do that for you. This is done using the storage class object. This is still beta when writing this course, but will be stable soon. It's best to double check the correct definitions in the documentation. Every time you see beta, you might want to check that. So here's a link that goes to the definitions of the persistent volumes. I will also keep, of course, my GitHub repository up to date with the latest definitions. To use the auto-provisioned volumes, you can create the following YAML file. It's very simple. The kind is storage class. The API version refers to a beta. The name that I give to my storage class is standard, but you can use any name. The provisioner is going to be AWS EBS, so it's going to provision EBS volumes for us. Then we have EBS specific parameters like type and zone. Type is GP2, the zone is US East 1. This will allow you to create volume claims using the AWS EBS provisioner. Kubernetes will provision volumes of the GP2 type for you, which means general purpose. It's SSD. You also have provisioned SSD and magnetic. Next, you can create a volume claim and specify the size of the volume that you want. So here's my volume claim.yaml. It's of kind persistent volume claim. API version here is v1 because persistent volume claims are part of the stable API. I give it a name, the annotation. This refers to the standard storage class that I created earlier. And then the specifications. It's read-write once. I can only have one EBS volume that I can read and write to at the same time. The request is going to be for 8 GB. Finally, you can then launch a pod using this volume. So here we have again the volume mount, a mount path, a name. This example is an Nginx example. It's if you would want to run Nginx with some static data, then you use the Nginx image, and then you're going to use a mount path that is going to provide a volume for /var/www/html. The name of the volume is mypd. Volumes, here is the name also mypd, and then this persistent volume claim refers to my claim, which is the name of the persistent volume claim from the previous slide. You can then put some static data in this volume, and then when you're going to browse to this URL, you will see your data. It's very simple. The next lecture will be a demo where I will demonstrate this auto provisioning. In this demo, I'm going to show how you can use WordPress with volumes. Let's have a look at the files in WordPress volumes. Lots of files. Let's first start with storage.yaml. Here I'm going to define a storage class, standard storage, GP2 type storage using AWS EBS volumes in the EU West 1A zone, because this is the zone that my Kubernetes cluster is running in. I have a storage class, so I also need a PV claim. And this is going to be the persistent volume claim for my database. So it's going to be called database storage. And I'm going to use 8 GB. And this is going to be the storage that is going to be used in the database pod. So let's have a look at this database pod, WordPress database.yaml. And I'm just using a very simple replication controller with only one replica, because I never want more than one instance of this pod running. It's going to be a MySQL 5.7, and I'm going to add the arguments ignore database directory lost plus found, because this directory lost plus found will exist in our directory where we're going to put our files. It will become clear in a few seconds. This is still the same. This is also the same. I'm just defining the root password, comes from the secrets. And then we have a volume mount. So we're going to mount /varlib MySQL, and this is going to come from MySQL storage. MySQL storage refers to a persistent volume claim called DB storage. This one with 8 GB. This volume will be created by Amazon automatically. We don't have to create it ourselves. Will then be mounted here. And because this is a new partition, a new volume with a partition on it, there is a directory lost plus found that is created in Linux. So that's why we're going to say ignore database directory lost plus found. Otherwise, our database will not start. Then we need a service for that. So we're going to create a service, WordPress database, which we then can use in our other pod, the one that is going to run the WordPress itself. Let me just show you the credentials. We also have WordPress secrets. So here we have a database password, which is just password. And these are all going to be used in the WordPress pod. We need to supply them because WordPress needs them, and they need to be the same for every pod. Let's have a look at how these variables are used in the WordPress web.yaml. It's a deployment. We can run 2 replicas because this pod can horizontally scale. We're going to use still the WordPress for PHP 7. We define a WordPress database password, it's the same as in the MySQL. And then we define this out key, logged in key, and so on. Because those keys need to be the same for all the pods we have 2 pods, so those keys need to be the same because your session might otherwise differ between the pods. So these we just need to do because of WordPress itself. And then we're going to add a volume mount. We're going to use a volume for this WordPress content uploads. In WordPress, you can upload pictures. We want these pictures to be available on all the pods, so we need to have some shared storage. On Amazon, we can use EFS for that, Elastic File System. This is an NFS file system, and this NFS file system is write and read on every node. Every pod that is going to mount this NFS can read and write to that. NFS is not fit for MySQL, that's why we are using block storage for that, but we can use it for images, for just storing small files. This is going to be the server. We just need to change the string because we have to create a new EFS volume first, because this is not auto-provisioned. And then it will mount this EFS right here. So let's see, did I cover everything? Well, we still have a service, a WordPress web service, and this is just going to put a load balancer in front of these 2 pods. That's so that we can connect to the WordPress using our browser. Let's create this EFS volume. We can use the AWS command for that. So first, AWS EFS create file system. You need to specify a creation token, which needs to be unique. I already used 1, I'm going to use 2. And this is going to create an EFS file system. Then we need to create an EFS mount target. We're going to create a mount target using this file system ID. So we're going to say -- file system ID, and then this string that comes from here. And we need to create this in the same subnet ID as our cluster. So we need to figure out first the subnet ID of our cluster. In another window, you can do that with AWS EC2 describe instances. And here, somewhere here, you're going to find one of your instances, and it's going to be the subnet ID. So this is one of our instances. We're going to use this subnet ID. Then we need a security group. And if 2 instances are in the same security group, then they can access each other. So we're just going to use the security group also from this node on Kubernetes. So this is a security group nodes Kubernetes New Tech Academy. So I'm going to use this security group. So it should work. And now it is creating. So we just need to take this string, the file system ID, and replace this in our WordPress web.yaml. So this needs to be the zone EOS1A for me, and then the ID, and then the region right here, and then AmazonAWS.com. So this should work. So let's now create all the resources. Let's start with the database. So I'm going to do kubectl create storage first, -f storage, then the PV claim, the secrets, and the database. Let's have a look whether, and the service immediately as well. And then let's have a look whether our volume is created. Yes. So this is the PVC, this is for storage. DB storage is bound. Okay. The secrets will be created. That's not very difficult. And then we have the WordPress DB. And this can take some time, of course. Describe pod, and it is pulling the image. So it mounted the persistent volume claim and it's pulling this image. So this actually created a new EBS volume for us. And this 8 GB EBS volume is going to be used to store our MySQL data on. This container is started. Here you go. It's now running. So which one do we still need to create? Kube control, create, and then let's create the web services. It can take some time for the EFS to be created, so we have to be patient a little bit, but then we should be able to create the web and the service is going to launch a load balancer. And if you want to use a proper DNS name, you can go to root 53. So if you go to root 53, then you can go to DNS management, your DNS name, and you could create a new record set. You could say WordPress. Actually, I already have one, but you could create a new one. Let me first delete the old one. So WordPress, it's an alias, and then it's going to load the ELB classic load balancer. It takes a few seconds, and then we have our load balancer. So this is the load balancer created by Kubernetes. We click create, and then we'll be able to access WordPress Kubernetes New Tech Academy. And here then we have our WordPress installation. So we just do the install. This is my blog, my username. This is auto-generate password for me. Log in with the same password. And then I have my WordPress running. The main difference now is that two things. I have two pods running that are going to handle the web requests, and one pod running that is going to handle the database. And the database data is saved in a volume, so I'm not going to lose it. I also have this EFS volume to create media, or to be able to upload media. But there is a small bug here that will not allow me immediately to run media, because look, if I select a file, it's going to say unable to create directory in this volume, because this directory is not writable. And this is just because the image, the WordPress image, was not built to be working on Kubernetes with these EFS volumes. So there are a couple of ways to fix this issue. You could just build your own image of WordPress and maintain your own image. Or what I'm going to do is I'm going to change the CMD when it starts, with the risk that if the CMD ever changes for this WordPress, then it might not work anymore. So I'll probably not commit this to my repository, but you can always make the changes yourself to make this working. So let's say that we want to edit our deployment, the WordPress deployment. And then if you scroll down here at the container spec, you just add these commands, bash execute a command, and then change the permissions or change ownership to the correct user and group of this directory, and then run this docker entry point sh apache2 foreground. So if this docker entry point would change in the future, then this command doesn't work, but you just would have to change it into the real command, which you can find on Docker Hub. So you save this, and then we can test it. So now let me refresh this page, and I'm going to add a new file. And now it uploads. This is the file that I uploaded, and I can make a change to a post. My image, add media, this image, insert picture, update, and then this is my block. So let me show you that the volumes actually work. Kube control get pod, and let me just delete this pod here. Delete pod, and let me delete those other pods as well. And I'm just going to delete this last pod as well. So all my pods are removed. And what's going to happen? Kubernetes is just going to spin up some new pods. So this one is creating again. and these ones are already running. So you just have to give it some time. And now everything is running again. Let's have a look at the logs of those things. WordPress successfully installed. Let's execute this pod. Let's execute bin bash in this pod. Let's have a look in our content, our uploads, and here we still have our image. So even after I kill the pod, even after I delete the pod, we still have our image. Let me have a look at the database. Database started again, and then if I refresh, I still have all my data still available. Hello world with the image. Even after my pod was crashed, even after my node would be crashed, Kubernetes would just shuffle the pods to where there is capacity, detach and attach the volume when necessary, so that my block keeps on running. So that's it for this lecture, for this demo. I think this was a very useful demo to show the capabilities of Kubernetes. Some things I showed you are still in beta, so be very careful with those features, but it is all very promising. Also, when you clean up, make sure that you go to Elastic File Systems in AWS and you delete this file system. This is an EFS in AWS, and then you click on Delete File System, because otherwise you will be paying for it. This lecture will be about pod presets. Pod presets can inject information into pods at runtime. Pod presets are used to inject Kubernetes resources like secrets, config maps, volumes, and environment variables. Imagine you have 20 applications you want to deploy, and they all need to get a specific credential. You can edit those 20 specifications and add the credential, or you can use presets to create one preset object which will inject an environment variable or config file to all the matching pods. So this is just an easier way to get certain information in multiple pods, rather than editing all the separate pod definitions or deployment definitions. When injecting environment variables and volume mounts, the pod preset will apply the changes to all containers within the pod. So if the pod has more than one container, the pod presets will be applied to all containers within that pod. This is an example of a pod preset. Here's the API version, currently still alpha. You might have to change it after the pod presets become beta or become stable. In the version that I use in the demo, it is still alpha, but in one of the next versions, it can become beta or stable. So then I will update this API version in GitHub. Kind is a pod preset. You can give the name, and then you have a specification. You need a selector to match, for instance, the labels. So every pod that has the label app equals my app will match, and whatever is defined below will then be applied to these pods. In this case, I have an environment variable, a volume mount, and I specify volumes. So this would then be applied, and then you have a variable mySecret, a volume mount /share, that is just an empty directory that is then defined in volumes. You can use more than one pod preset. They will all be applied to matching pods. If there's a conflict, the pod preset will not be applied to the pod. Pod presets can match 0 or more pods. It's possible that no pods are currently matching, but that matching pods will be launched at a later time. So they don't necessarily need to match, they will just be there, and whenever a new pod is launched that matches, then the presets will be injected in that pod. In the next demo, I will show you how that works. In this demo, I will show you how to work with pod presets. First, I need to launch my cluster with some extra arguments, because these pod presets are still alpha. I'm running 1.10 beta 1. It's the latest version available, not even the stable version, and pod presets are still alpha in this one. It might take a few more versions before they will come out of alpha status. So I have a directory here, pod presets. And first I'm going to create the cluster again. So I'm going to create a cluster with node count 2. And then the cluster configuration has been created. And to edit this cluster, we can use kops edit cluster. And that's what we need, because if we have a look at the README in the pod presets, we need to add this specification for the Kube API server to enable the pod preset in the enable admission plugin and to enable the alpha feature. So let's do kops edit cluster. We have to add the state, and then we need to add this specification. So let's copy this. Let's have a look if it already exists, this Kube API. It doesn't exist yet, so I will just add it at the bottom. This spec I don't need because this is already set here. And then make sure that the indentation is correct. So it's here 2 spaces and it's here 2 spaces. Kube API server, enable admission plugins. We have the pod preset here and we have the runtime config. Settings for this API v1 alpha 1 is going to be enabled. Going to save this, and then we can start a cluster using kops update cluster -- yes, and again the state. After it's set up, we have to wait 5 to 10 minutes before the DNS updates. Let's check whether the cluster is up now. And okay, the cluster is running. Let's have a look at this pod presets.yaml and the deployments.yaml. Pod presets.yaml. So this is of kind pod presets using this API version. So it's very similar as what I showed you in the theory. I have a selector. I'm going to match app equals my app in the labels. And I'm going to make sure that the pods that match will get an environment variable, a volume mounts, and a volume defined in the pod. I then have deployments. I have 2 deployments, and they are just regular deployments with the label app equals my app, but they don't have any environment, they don't have any volume defined. That will be the pod preset that is going to inject that into these 2 deployments. So let's create this pod preset. If you do kubectl get pod presets, then we see now we have our pod preset created in Kubernetes. So now whenever we create a deployment using label app equals my app, then we will see these resources injected in the pods. Let's have a look at the pods. 3 pods per deployment. Let's have a look. Kubectl describe pod, and the name of the pod. I'll pipe this through less. And let's have a look at this. Container creating still, but as you can see, we have the environment my secret equals 1, 2, 3, 4, 5, 6. So it injected our secret, and it also created our mount /share from share volume, and then share volume is defined in the pod. We have a share volume of type empty directory. So this injection worked, and if you would check other pods, then we should all see the same. Let's have a look at one of deployment 2. And here as well, environment my secret, the mount, and the share volume. So this is an easy way to inject resources to multiple pods that share the same set of config or the same volumes or the same environment variables. As long as there is no conflict, your presets will be injected. That's it for this demo. You can try it out yourself. Just keep in mind that this is still an alpha feature, so it's best to wait until this goes to beta or stable until you use it in a production cluster. I would say you can already test it, but then make sure that you have a much more recent version of the cluster as I have. Right now, this is the latest version, but in a couple of months, there will be new versions. At some point, it will definitely be stable. I will now be talking about stateful sets, stateful distributed apps on a Kubernetes cluster. Pet sets was a new feature starting from Kubernetes 1.3 and got renamed to stateful sets, which is now stable since Kubernetes 1.9. It is introduced to be able to run stateful applications that need a stable pod host name instead of a pod name -random string, as you see when you run, for instance, deployments. They have a random string after the pod name, so they don't really have a stable host name. You always need to go over the service to then get access to one of the pods you're running. Your pod name in a stateful set will have a sticky identity using an index. For example, pod name -0, pod name -1, and pod name -2. And when a pod gets rescheduled, it will keep that identity. So if pod name 1 gets rescheduled, it will still be pod name 1. Stateful sets allow stateful apps stable storage with volumes based on their ordinal number. So if our pod name 1 gets rescheduled, it will keep the storage because it's stable storage. It will not have to be reinitialized. And then deleting and or scaling a stateful set down will not delete the volumes associated with the stateful set, preserving the data. So if you go from 3 to 2, then it will not delete the volume. You will have to clean it up yourself. This is to preserve the data. A stateful set will allow your stateful app to use DNS to find other peers. Cassandra clusters, Elasticsearch clusters use DNS to find other members of the cluster. For example, you can use the DNS name cassandra-0.cassandra for all the pods to reach the first node in the Cassandra cluster. So if you, let's say, have 5 nodes, all those 5 nodes can use the same DNS name to reach the first pod, which is Cassandra-0. So they will then contact, in Cassandra, it's called the seed node. So this is the way they find each other. So in this case, you need a stable host name for all the pods, for all the nodes that are running to find each other. Using stateful sets, you can run, for instance, 3 Cassandra nodes on Kubernetes named Cassandra 0 until Cassandra 2. So then you will have Cassandra 0, Cassandra 1, and Cassandra 2. If you wouldn't use a stateful set, you would get a dynamic host name, which you wouldn't be able to use in your configuration files, as a name can always change. A stateful set will also allow your stateful app to order the startup and teardown. Instead of randomly terminating one pod, one instance of your app, you will know which one that will go. When scaling up, it goes from 0 to n-1, where n is the replication factor. If you have 3 nodes, you have 0, 1, and 2. If you create another node, then your n will be 4. When scaling down, it starts with the highest number, so n-1. So replicate, if you have 4 nodes, it will tear down number 3, then 2, then 1, then 0. This is useful if you first need to drain the data from a node before it can be shut down, because then you know that the highest number will be scaled down first, so you can drain that node if necessary. In this demo, I will show you how stateful sets work. For this, I will use Cassandra. I am here in my Git repository. There's the directory stateful sets, and I have a cluster running using kops with 4 nodes. 3 nodes where I can schedule something on. I'm going to deploy Cassandra, and Cassandra is a database. You don't need to know much about it to be able to deploy it. It's a database that needs static host names, so they need to find each other, those nodes, otherwise it cannot work. And to be able to find each other, you need those static host names. So let me show you what is in the YAML file. We have kind stateful set. We give it the name Cassandra. We want 3 nodes. Every node in Cassandra is the same, so it uses all the same Docker image. The image that we're going to use is coming from Google. There's a Google example that includes Cassandra. We're going to use version 13. These are the ports that are defined. So there are intra-node ports, JMX for statistics, and CQL for the client. We're going to give them limits. So we need 1 GB of memory free to be able to run this pod on the node. So we need 3 GB in total to run this. That's why I added another node. It's for T2 small nodes, not T2 micro, so that I have a total of 2 GB per node that I can scale on. Secure context, we add the capability IPC lock. So we're just going to give a little bit more privileges so that Cassandra can use IPC lock. If we're going to stop the pod, the Cassandra, then it will use the command node tool drain to make sure that the data from that node goes first to the other 2 nodes. Then we have the environment, and this is just what Cassandra needs. It needs, for instance, the heap size. It's going to use half a gigabyte of memory. And then this is the most important, the Cassandra seeds. So where does every node needs to go to for its seed? Because they need to connect. We can have 10 nodes, we can have 100 nodes, but all those nodes need to contact one node. That will be called the seed node, and that seed node knows about the whole network. In this case, we're going to use Cassandra 0, which is the first deployment, is the first pod of our Cassandra cluster. And this we can do because we are using static host names. So we can use this static host name, Cassandra-0.cassandra, which is a service name, .default svc cluster local. And this host name will always stay like this. So when we use this host name, we'll always reach the first node in our cluster. And that is what the difference makes between a stateful set and a deployment. We give it a name, a data center rack, and then we also pass the pod IP address so that the image knows about the IP address that it's using. There's a readiness probe to see when the Cassandra node is ready. This script is provided with the image. There is an initial delay of 15 seconds and a timeout of 5 seconds. I'm going to mount the volume. So this is Cassandra data. Mount path is /Cassandra data, so that's where we're going to find the data. Then we have the volume claim template. We call it Cassandra data. Read write once, and the storage class is standard. And this is then the storage class that we're going to provide. So it's GP2 in EUS1A. 8 GB of storage per node. And then we create a service. So this will be the Cassandra service. Name is Cassandra. Doesn't have cluster IP. It will have a port 9042. And the selector is app Cassandra. So this will be the port that we are going to use to connect to our Cassandra cluster to use SQL. Let's Cubectl create this Cassandra. And then we can immediately check our pods. So we start with Cassandra 0. So this one is pending. Then we also see the volume. So we have now one volume here, Cassandra data, Cassandra 0. And we also have a claim. So if you do watch Cubectl get pod, then we can keep an eye on the launching of the pod. So first we'll have the first node, Cassandra 0. This is the host name that we're going to use in the config. Then we will have Cassandra 1. That Cassandra 1 will contact Cassandra 0 to tell this Cassandra 0 that it is alive, it is there, and then it will start creating a cluster. Now our first Cassandra node is running. It's not ready yet, but it's initializing. First one is ready, so now the second one is creating, and the second one will contact the first one. And now the third one is creating. So we have 2 ones ready, and now the third one is creating. So let's check again. Now all our pods are running for a couple of minutes now. And we should be able to do Cubectl exec of Cassandra 0. And we should be able to execute no tool status, which will give us a status. Don't worry about this error, it's just a temporary DNS error because my cluster is only just a couple of minutes old. So the DNS is not yet propagated to all name servers yet. No tool status gives us UN, status up, state normal, of are 3 nodes. So those are the 3 pods, and they are all working. They all have a part of the data in Cassandra. So you have the data and then it's replicated. They communicate with each other and they're all working. Let me just show you how this now works with the DNS lookup. So if you do bash, then we are now logged into Cassandra 0. And if you use ping Cassandra 0.cassandra, we can ping the first one, the second one, and this is the third one. And in our 3-node cluster, these are static DNS names, so we'll always be able to reach these nodes. Let's try to kill a pod. Kubectl delete pod Cassandra 2. Cassandra 2 deleted, and this one will spin up a new pod. It will actually spin up the same pod, the same Cassandra 2 will be spun up. Kubectl get pods. So you see there's already a new one spinning up right now. Kubectl get PV, and you see no new storage has been created. It's still the same storage that it uses. So it's still the same storage that was spun up earlier. And now it is running again with the same data. So if you do node tool, we have again our 3 nodes in the cluster and they're all healthy. So it can recover, it can contact the nodes again. They have static host names. So you can use a stateful set if you have a distributed database like Cassandra, like Elasticsearch, that you need to run on Kubernetes that needs static host names and static volumes. This lecture is about daemon sets. Daemon sets ensure that every single node in the Kubernetes cluster runs the same pod resource. This is useful if you want to ensure that a certain pod is running on every single Kubernetes node. When a node is added to the cluster, a new pod will be started automatically on that node. Same when the node is removed, the pod will not be rescheduled on another node. You have 4 nodes, you will run 4 pods, 1 on each node. You remove 1 node, you will then run 3 pods instead of 4. That 4th pod will not be rescheduled. So you always have the same amount of pods as you have the amount of nodes. The typical use cases: logging aggregators. So when you want to have 1 logging aggregator per node, where maybe all pods send their logs to. Monitoring. Again, if you want to monitor per node, then you typically only want 1 pod that is going to do the monitoring per physical node. Load balancers, reverse proxies, API gateways. There are third-party API gateways like Linkerd that also use daemon sets to run just 1 pod per node that you have in your Kubernetes cluster. And in general, running a daemon that only needs 1 pod instance per physical instance, then you're going to use daemon sets. So this is an example of a daemon set specification. It's very simple. You're going to use the API version extensions v1 beta, and the kind is daemon set. And all the rest is exactly the same as the previous definitions that we used. You have metadata and then you have the spec. In the spec, you define a template where you have your pod specification. I'm not going to do a demo now about daemon sets. It will come back later on in the course. Now I'm going to talk about resource usage monitoring. Heapster enables container cluster monitoring and performance analysis. It's providing a monitor platform for Kubernetes. It is a prerequisite if you want to do pod autoscaling in Kubernetes. Pod autoscaling is going to be the next topic after monitoring. Heapster exports the cluster metrics via REST endpoints, so other technologies can then query Heapster to get the metrics. You can use different backends with Heapster. So a backend is where the metric data is stored. I will use InfluxDB, but others like Google Cloud Monitoring or Google Logging and Kafka are also possible. InfluxDB is a database that is fit for time series. That's why it's a good fit for our Heapster metric data. Visualizations, graphs, can be shown using Grafana. So with InfluxDB, we can also deploy Grafana. The Kubernetes dashboard that I showed you earlier, the web UI, will also show graphs once monitoring is enabled. You don't even have to use Grafana, you can just see the graphs in the dashboard as well. All these technologies, Heapster, InfluxDB, and Grafana, can be started in pods. The YAML files can be found on the GitHub repository of Heapster. This is the URL that I'm going to use in the demo as well. It's still the Kubernetes github.com account, but then there's another repo called Heapster. You're typically going to use the master branch because that is the most up-to-date branch. After downloading the repository, the whole platform can be deployed using the add-on system or just by using kubectl create -f and then the directory with all the YAML files. If you don't use the add-on system, if you're just going to deploy it using kubectl, then you need to make some changes in the files, which I will be explaining in the next demo. This is roughly how it looks like. This can change a little bit because there are still a few outstanding issues to make this a little bit more performant, and the Kubernetes team might make some changes. But this is on a high level how it's going to look like. On the right, what we are going to deploy is the Heapster pod, the InfluxDB pod, and the Grafana pod. The kubelet has a process cAdvisor, which is now in the kubelet, but it's going to be separate in the future. That's why I put it a little bit out of the kubelet. This is going to gather all the metrics from the pods and send all those metrics to Heapster. Heapster is then going to save this in InfluxDB, and you can then get an overview of those metrics in graphs using Grafana. So basically all the data goes from the kubelets to Heapster, and Heapster then saves it into InfluxDB. In the next demo, I will show you how to set this up. Before you start with the Heapster Grafana demo, I want to make you aware that now Heapster is actually deprecated. So for newer clusters, it's actually not necessary anymore to install Heapster to get your metrics. There's now a metric server that came out that you can use. The metric server is a stripped down version of Heapster. It's very similar, but you cannot extract any metrics from it anymore. So you cannot use a sync to InfluxDB and then show your metrics in Grafana. So now, if you want to show external metrics, it's a little bit unclear how you have to do that. You have to use a third-party tool like Prometheus, but there's not a lot of documentation out there yet, and still metric service isn't incubating. So it's a little bit early to do a full demo that shows you the statistics in Grafana, but I can already show you how to install the metric server rather than using Heapster for newer clusters, because Heapster will be deprecated from version 1.11. So this is the Heapster GitHub repository, and from Kubernetes 1.11 there's an initial deprecation. So no new features or things will be added, bug fixes might be made, and then starting from 1.13 Heapster will be retired. At that point you should be using the metric server instead. The metric server is still in Kubernetes incubator, but is now the way to go to get your node and pod metrics. So if you choose for metric server instead of Heapster with Influx and Grafana, you don't really have a front end. Even the dashboard hasn't changed its code yet, but I'm pretty sure this is going to happen very soon. Then rather than using Grafana, you're just going to get the metrics in the Kubernetes dashboard, and then you don't even need Grafana anymore, unless for other statistics, but not for these specific statistics that you then just need maybe for pod auto-scaling. So metric server is definitely the way to go in the future. So let me show you how this is set up. In my Kubernetes course Git repository, I have directory metric server, and here I have all the YAML files copied. So I just do kubectl create of this directory, and then I should be able to do kubectl top. So let me just show you without an argument. So you can do kubectl top node and kubectl top pod. So let's try kubectl top node first. No metrics available yet. It actually takes some time to create those. We also need to be running a pod. So let me just run a simple service. So I created the deployment hello Kubernetes. This will start a pod. Just get pod because it has this random string here. Let's try again. Top node. Now I have statistics. So now we see CPU cores, CPU percentage, memory, and memory percentage. So I have 3 nodes, 1 master node and 2 normal nodes. This is the master node and these are the normal nodes. Now let's try kubectl top pod. And this gives me then the usage of the hello Kubernetes pod. So it only uses 2 megabytes. Currently it doesn't use any CPU because we're not even contacting it, we're not even using it. So 2 megabytes. So if you have more pods running, you will then see this increasing and changing. So to do the auto scaling lecture, which will come next, you only need the metric server. You don't need any of the other components anymore that I will still explain in the next lecture, because those are deprecated. If you run an older cluster, then you can still use Heapster and Influx and Grafana, but for newer clusters starting from 1.8, you don't need this anymore. You can use this metrics server. In this demo, I will show you how to set up Heapster with InfluxDB and Grafana. You first need Heapster, which you can download from github.com Kubernetes Heapster. So here you clone or download. You can just download a zip file, for instance. Or you can use git clone to clone this repository. I will then download this master zip of Heapster, unzip it. Then you can find the files that we need to deploy in deploy kubeconfig influxdb. But those files are meant for the Kubernetes add-on, and I'm not going to use the add-on system. What I'm going to do is I'm just going to use kubecontrol and add those as a pod. So I will need to edit some of these services. So we'll first start with Grafana service. And here it says, if you are not using this as an add-on, you should comment out this line. So that's what I'm going to do. And this needs to be of type node port, because we are not going to use a load balancer on our Minicube. If you are using AWS and you want to use a load balancer, you could change this in load balancer. I'm going to edit the Heapster service.yaml. Again, this line needs to be commented. And if I want to access this service externally, I could add a node port. But for now, I don't need this. And then we have InfluxDB service. And then I comment this line again. This one again, InfluxDB has a UI that you can use. Then you just have to uncomment node port and uncomment these ports, and then you can use the InfluxDB API and you can then do queries directly on this database. I'm only going to show you the graphs using the dashboard and Grafana. I don't need those. Kubecontrol, create -f, and I can do -f also on a directory. Doesn't need to be a file. And this is then going to add all those files. But I see that I'm trying to connect to my Kops cluster, which is offline, and I want to use Minicube. So I'm just going to exit here. And on my MacBook itself, I have Minicube running. So I'm going to use kubecontrol create -f right here, because I use this Ubuntu Xenial to connect to my Kops cluster, and I have my local MacBook Pro to connect to Minicube. So these now are all running, and I need at least one pod to show you the example. So I'm just going to create from the Kubernetes course, a deployment, the hello world.yaml. Oh, kubecontrol create. And then when this monitoring Grafana service is up, I can do Minicube service monitoring Grafana --url, and those are launched in a different namespace. So I have to specify the namespace kube system. This is going to give me the URL, and then I should be able to connect. This is Grafana. You might need to log in here, so make sure that if you make this public, that you immediately change the password or that you password protect this UI. Standard user and password is admin. I'm going to log in with admin, and then I can see the cluster. This can take some time before it is running. So I just refreshed, because you have to wait a couple of minutes after you launch your cluster. And now we have one data point. It becomes more interesting when we go, instead of cluster, to pods. And then here we can then see our pods. So we have the namespace kube system and the namespace default. And in the namespace default, I have, for instance, my Hello World deployment that I just started. And then here you will be able to see how much CPU, how much memory, how much network usage, how much file system usage the pods are using. And then also more interesting now is that if you go to the dashboard, you will also be able to see the graphs. So if I type Minicube dashboard and then the URL, and I go to the Cube dashboard, I will also now see memory usage, CPU usage of all those pods, which is very good to follow up. And you also need this monitoring to do auto-scaling, which I will explain you in the next lecture. Let's talk about auto-scaling, horizontal pod auto-scaling. Kubernetes has the possibility to automatically scale pods based on metrics. Kubernetes can automatically scale a deployment, a replication controller, or a replica set. In Kubernetes 1.3, scaling based on the CPU usage is possible out of the box. With alpha support, application-based metrics are also available, like queries per second or average request latency. You need to make some modification to enable this. The cluster has to be started with the environment variable enable custom metrics to true. This is probably going to change in the future because this is still in the alpha stage and they are going to make some improvements. Autoscaling will periodically query the utilization for the targeted pods. By default, this is every 30 seconds. But that can be changed using the horizontal pod autoscaler sync period when launching the controller manager. If you would want to change this default value, you can, but it needs to be done in the initialization scripts when the controller manager starts on the master node. Autoscaling will use Heapster, the monitoring tool, to gather its metrics and make scaling decisions. Heapster must be installed and running before autoscaling will work. So make sure that you followed the demo that will enable Heapster. So here is an example. You run a deployment with a pod with a CPU resource request of 200 M. 200 M means 200 milli CPU, or also sometimes called 200 millicores. 200 M is actually 0.2, which is 20% of a CPU core of the running node. If the node has 2 cores, it is still 20% of a single core. So it's absolute numbers. You can introduce, for instance, autoscaling at 50% of the CPU usage, which is 100 milli CPU. Horizontal autoscaling will increase or decrease pods to maintain a target CPU utilization of this 50%, or 100 milli CPU, or 10% of a core within this pod. So a core on this node. This is a pod that you can use to test autoscaling. Here we have a deployment, and in the specification we are going to use a Google image. It's an image that has a web server that is going to do some calculations if you visit the website. To make this work, we're going to specify resources, and we're going to request the request CPU 200 milli CPU. This means that we are requesting that our pod can use 200 milli CPU. We can use more, but Kubernetes can use this 200 milli CPU for scheduling purposes. It will not put this pod on a node that doesn't have 20% of a core available anymore. For us, in this example, this 200M is also needed for our autoscaling. So this example is an autoscaling specifications. This object is of kind horizontal pod autoscaler. It has a name, also a specification, and here we're going to say that we are going to use a deployment that needs to scale. The minimum of the replicas is going to be 1 and the max replicas is 10, and the target CPU utilization percentage is 50%. 50% of, if we go back to the previous slide, then it is 50% of this CPU that we requested. So the target is going to be 100 milli CPU. When it goes higher than 100 milli CPU, more instances will be launched until we reach 10 replicas. If it is less than 50%, then pods will be removed until we hit the minimum, which in this case is 1. In the next demo, I will show you how that works. In this demo, I'm going to show you autoscaling in action. So I'm in my Kubernetes course and I have a folder autoscaling. And I have just one file here, HPA example. And this is the example that I showed you during the theory. So I'm just going to add this to the cluster. So we have a deployment that is created, we have a service that is created, and we have a horizontal pod autoscaler that has been created. This is a service, so my app will be accessible at port 31001. So if I do kubectl get HPA, I will see that I have a horizontal pod autoscaler with a min pods of 1, max pod of 10, and it's currently waiting until it gets some metrics, which in the beginning is going to be 0% because nobody is going to our app yet, but that's going to change because I'm going to launch a shell and I'm going to connect to this endpoint. I'm going to run this image busybox called load generator, which is just the pod name, it's just a busybox. And because I exposed this service right here, HPA example, I should be able to use wget in this pod to connect to the web server and fetch the index. So wget HPA example.default, which is the namespace svc for service cluster.local, and this works. And what is in this index HTML, it just says OK. It says OK, but actually it executed some code that will generate some CPU, so that if we run this in a loop, we will get to a higher CPU percentage and then our autoscaling will kick in. So let's try to run this in a loop. And now we just have to wait some time. It takes some time, like a minute or so, for the autoscaler to see that there is more CPU usage, and then it's going to start scaling it. So I'm just going to open a second window, and then here I will check how many pods I have running. Still currently I have 3 pods running, and what the HPA says about my usage. So now I have 40%. It needs to go a little bit higher, and then it will start adding more pods. So I'll just pause the video for a second, and when it starts scaling, I will start again. And then you can see current is now 155%. So it is starting to scale all these pods. So in a few moments, I will just have 10 pods running, which are then going to take all this load. Now, what I'm going to do is I'm just going to stop this one, Control C, and then you can stop it. You can even close your container or end your session, and then you can remove the whole container if you want. What you will see now is that after a couple of minutes, this load, this current CPU usage is going to drop again. And when it drops, it's going to get lower than the target, and then Kubernetes or the autoscaler is going to remove pods. And we're going to end up with just 1 pod, because if the current utilization is 0%, because I'm not hitting this website anymore, then it will keep on downscaling until the minimum, and the minimum is 1. If you want to always keep a couple of pods running, you specify minimum 3 or something like that. In my case, it will just go down to 0. So I'm going to give it a couple of minutes again. And here we are a couple of minutes later, current 0%, and there's only one pod running anymore. All the other ones were terminated. So this basically is how auto-scaling works. In this lecture, I'll be talking about affinity and anti-affinity in Kubernetes. In a previous demo, I showed you how to use the node selector to make sure pod gets scheduled on specific nodes. This was the example that I was using. It's a deployment, and in the specification, I used a node selector to only schedule the 3 pods that this deployment is going to start only on nodes that have the label hardware equals high spec. So if the node doesn't have this label, the pod will not be scheduled on that node. So you need a node with exactly this label to have this pod scheduled. Affinity and anti-affinity that I'm going to show you in this lecture are similar to what the node selector does. The affinity-anti-affinity feature allows you to do more complex scheduling than the node selector, and also works on pods. So not only for nodes, also for pods. The language that you can use is more expressive. You can create rules that are not hard requirements, but rather a preferred rule, meaning that the scheduler will still be able to schedule your pod even if the rules cannot be met. So with a node selector, if a node doesn't have your label, it will never get scheduled. Whereas with affinity and anti-affinity, you can create a different type of rule where you set a preference. So you will prefer nodes with a specific label. But if there's no node with that label schedulable, it will still get scheduled on another node. You can create rules that take other pod labels into account. So affinity also exists not only for node affinity, but also for pod affinity. For example, you can create a rule that makes sure 2 different pods will never be on the same node. Kubernetes can do node affinity and pod affinity anti-affinity. Node affinity is similar to the node selector, and pod affinity anti-affinity allows you to create rules how pods should be scheduled, taking into account other running pods. Affinity anti-affinity is a mechanism only relevant during scheduling. Once a pod is running, it will need to be recreated to apply the rules again. Don't expect that if there is a new node with a label and it's a better match, that Kubernetes will automatically reschedule your pod. You will have to terminate your pod first, and it needs to be recreated to make sure if you want to have your pod scheduled on another node. I will first cover node affinity and will then cover pod affinity anti-affinity. There are currently 2 types you can use for node affinity. The required during schedule, ignored during execution, and the preferred during schedule, ignored during execution. The first one sets a hard requirement, like the node selector. The rules must be met before the pod can be scheduled. The second type will try to enforce the rule, but it will not guarantee it. Even if the rule is not met, the pod can still be scheduled. It's a soft requirement. It's a preference in this case. So here's an example that I will use in the next demo. So in your deployment specification, you can define affinity, then node affinity, and here you can define the required during schedule, ignored during execution, and also the preferred during schedule, ignored during execution. So you can combine both. In this example, we're going to look for nodes that match the expression env in dev. So the environment env needs to be dev before this pod can be scheduled on that node, because we have the required during schedule, ignored during execution, and not the preferred. If the label env is dev on one of our nodes, then we can be sure it will be scheduled, because we have a preferred rule, a second rule, and the preferred rule is a preference. So it will look for nodes that match, but if it doesn't match, it will still get scheduled. We're going to give it a weight, and I will explain the weight in the next slide. And then we have the preference. And the preference is match expression, team in engineering project 1. So we're looking for the label team equals engineering project 1. But if there are no nodes with engineering project 1 as a label, then we'll still schedule it on a node that has env equals dev, but is missing this label. So I'll show you how that works in the next demo. Now, in the previous slide, I also supplied a weighting to the preferred during scheduling, ignored during execution statement. So here it is again, weight is 1. The higher this weighting, the more weight is given to that rule. When scheduling, Kubernetes will score every node by summarizing the weightings per node. For example, if you have two different rules, preferred rules that is, with weights 1 and 5. If both rules match, the node will have a score of 6. So in this case, we have one node where both rules match, but we're probably going to have other nodes. So let's say that we have another node, and on this other node, if only the rule with weight 1 matches, then the score will only be 1. So then we have one node with score 6 and one node with score 1. The node that has the highest total score, that's where the pod will be scheduled on. So in this example, our pod would be scheduled on the node that has a score of 6. In addition to the labels that you can add yourself to the nodes, there are pre-populated labels that you can use as well. For example, if you want to know the hostname, you can use the label with the key kubernetes.io/hostname. So this will reply the hostname, and you can use that in your affinity rules. You also have the zone, and this can actually change once this becomes stable. So you would have to double check your node labels to see what labels that you have. I will also show you that in the demo. The zone is cloud dependent. If you're on AWS, then the zone can be EU West 1A, for example. The region, also cloud dependent, can be EU West 1, can be US East, US West, and so on. The instance type, for example, T2 Micro, the operating system, and the architecture. So depending where you deploy, these can all have different values. But nevertheless, these are labels that you might want to use for your decision making. So here I have spun up a cluster using kops with 3 nodes. So here are 3 nodes running 198. And if I describe one node, I will be able to see the labels. So I'm going to describe node, and then I'm going to describe my first node, not the master, but the first node. And let's scroll up, and then we see the labels. So here we see the architecture AMD 64, instance type T2 Micro, OS Linux, region EU West 1, and it's in the EU West 1A zone. And the host name is the full AWS host name. So these labels already exist. You can use them for affinity if you're going to make your own rules. I'm going to use the example I showed you in the theory. So I'm going to go to my Kubernetes course Git repository, and here I have a folder affinity. In this folder, I have node affinity YAML, and I have a deployment that's called node affinity that I will deploy to my Kubernetes cluster. So I need env dev, and I need team engineering project 1, which is optional. So let me just create this one and see what happens. I'm going to create a node affinity YAML, and it's going to launch 3 pods. So I do kubectl get pod, and I get pending because I haven't created labels yet. So if I do kubectl get describe pod and the pod name, 0 of the 4 nodes are available. The first one is the master, so it's not going to schedule on that one. And then all of them, they don't match my required affinity rule. So let's then start creating labels using kubectl label. So I can label a node, and I will do get nodes first. So I'll label node, and I will take the first node here, and I'm going to label it env equals dev. And I'm also going to label the second node env equals dev, and now you will see that all the pods have been scheduled. It can take some time, obviously, and then you can see that now the pods are being scheduled. 2 running, 1 is still creating. If you now do describe this pod, then we see it was successfully assigned to one of our nodes. So now it is running on this node, the one that ends with 119. That is the first one here, the first node here. And you can see that these two nodes now have the label env equals dev, but the other label, it doesn't really matter. The other label was not taken into account because it doesn't exist on either of them, so it got scaled anyways. So now if we label our node that ends with 1996, and we add a label team equals engineering project 1, and then let's have a look at our YAML file, engineering project 1, team engineering project 1. So this is preferred. So now if you would stop this node here that is running on the node ending with the IP ending on 119, then it should be rescaled on the one that is ending with 196, because now this one is the only one with the label engineering project 1. So let's try that. Let's try to get the name of this pod. This is node affinity with VK70G at the end. And this is now running on the one with 119. So let's say kubectl delete pod, this one. And then we do kubectl get pods. Then we see that this one is terminating. A new one has been created. This one is 5 seconds old. Let's describe this one. Kubectl describe pod. And where is this one now running? On the one that ends with 196. Because the one that ends with 196 is the one that best matches our affinity rules. Because this is the only node that also has the team key value pair, the team label that I'm looking for. So now typically all the pods that I restart are going to be first scheduled on this node. And if this node is full or it cannot schedule anything anymore, then it will be scheduled on other nodes that have the tag env equals dev. If it doesn't have that mandatory tag, that required tag, then it will not be scheduled at all. So that's it for this lecture. In the next lecture, I will then explain you about pod affinity and anti-affinity. In this lecture, I'll be talking about interpod affinity and anti-affinity. This mechanism allows you to influence scheduling based on the labels of other pods that are already running on the cluster. Pods belong to a namespace, so your affinity rules will apply to a specific namespace. If no namespace is given in the specification, it defaults to the namespace of the pod. Similar to node affinity, you have two types of pod affinity and anti-affinity. You have the required during scheduling, ignored during execution, and the preferred during scheduling, ignored during execution. The required type, the first one, creates rules that must be met for the pod to be scheduled. The preferred type is a soft type, and the rules may be met. So in the preferred type, the pod should always be scheduled. In the first one, if the rules are not met, then the pod will not be scheduled. So interpod affinity and anti-affinity is very similar to the node affinity and anti-affinity, just that here we do it on a pod level in a namespace instead of a node level. A good use case for pod affinity is co-located pods. You might want that one pod is always co-located on the same node with another pod. For example, you have an app that uses Redis as a cache, and you want to have the Redis pod always on the same node as the app itself. Another use case is to collocate pods within the same availability zone. So it's the same as the previous use case, but rather than on a machine basis, you can do it on an availability zone basis. So then the pods are collocated within the same availability zone. If you have multiple zones, then these pods will only be scheduled within one zone. When writing your pod affinity and anti-affinity rules, you need to specify a topology domain called topology key in the rules. The topology key refers to a node label. If the affinity rule matches, the new pod will only be scheduled on the nodes that have the same topology key value as the current running pod. This is a bit hard to understand without an example, so let me show you an example. Here we have two nodes and we have one pod on our node 2 called pod, and it has the label app with the value my app. We want to schedule a new pod on the left here that has the label app equals Redis. This pod has this in its specification. It has pod affinity, required during scheduling, ignored during execution. It has a label selector, and the match expressions is app in my app. So it's going to match this app here, this pod here on the right. And when it matches, then the topology key is important. Here we says the topology key is Kubernetes IO/hostname. So that's the host name of the node. So if the expression matches, then this pod will be scheduled on the node that has the same topology key value. So the value of Kubernetes IO hostname is node 2 in this case. So this pod will only be scheduled on a node that has this label kubernetes.io/hostname equals node 2. And this is only one hostname. So that's going to be node 2. So then the new pod is scheduled on node 2 and not on node 1. Let me show you another example. Here we have three nodes. Node 1 and 2 are in EU West 1A and node 3 is in EU West 1B. So the first two are in the same zone. We want to schedule a new pod. This has the label app equals DB. And the pod affinity is exactly the same as the previous one, except the last line. In the last line, we say topology key is the failure domain beta Kubernetes IO zone. So here, if our expression is true, the expression is here app in my app. So if there's a pod app equals my app, and this is true, then this new pod will be scheduled on a node with a label failure domain beta Kubernetes IO/zone equals the same as the node where the pod is running on. So pod app equals my app is running on node 2. Node 2 has as a zone EU West 1A. So the new pod is going to be scheduled either on node 1 or either on node 2, but never on node 3. So if we have replication factor 2, then the chances are high that one gets scheduled on node 1 and one gets scheduled on node 2. So never on node 3. So this is a difference with the topology key. Contrary to affinity, you might want to use pod anti-affinity. You can use anti-affinity to make sure a pod is only scheduled once on a node, for example. For example, you have three nodes and you want to schedule two pods, but they shouldn't be scheduled on the same node. Pod anti-affinity allows you to create a rule that says to not schedule on the same host if a pod label matches. So here we have again two nodes. We have a pod running, which is app equals my app, and we're going to schedule a new pod with the label app equals DB. Now we're going to use pod anti-affinity in our specification. The expression is still app in my app, so it will match the current running pod, and the topology key is the host name. Because it's anti-affinity, it will not schedule when the expression matches on the same host name. So where does it go? It goes to node 1, because node 1 has a different host name than node 2. So this is basically just the reverse of pod affinity. Anti-affinity makes sure that it doesn't get scheduled on the node with the same topology key value. When writing pod affinity rules, you can use the following operators. In, not in, does a label have one of the values that you specify? And exists, does not exist, does a label exist or not? Interpod affinity and anti-affinity currently requires a substantial amount of processing. You might have to take this into account if you have a lot of rules and a large cluster. For example, if you have more than 100 nodes. And then in the next demo, I will show you an example of interpod affinity and anti-affinity. I will now show you a demo of interpod affinity. So I'm here now in the affinity folder of my Kubernetes course Git repository. And here I have a file podaffinity.yml. Let's have a look at this. It's going to deploy two deployments. The first deployment is podaffinity 1. Second one is podaffinity 2. This first deployment is just a container, no pod affinity defined. is the second one that has a pod affinity defined. And here we're going to say affinity, pod affinity, required during scheduling, ignored during execution. Then we have label sector, app in pod affinity 1. If this is true, then the pod will be scheduled on the node that has the same host name. So this is Redis. So that means that the Redis pod is always going to be scheduled next to the first pod, the pod affinity 1 pod. Let's kubectl create this pod affinity. 2 pods created. Container creating. Let's use O wide, and then we can see on what nodes they are created. Both of them are running. Both of them are on the same node. Maybe that's coincidence. So let's scale this deployment. Replicas 4 maybe of our deployment pod affinity 2. Now it's scaled. All the new pods are on the same node. So you see pod affinity makes sure that the new pod, the second one, pod affinity 2, is always scheduled next to the first one. We can use different labels as well. So let's say that we kubectl delete this pod affinity to delete those 2 deployments. Let's have a look at our labels. Get nodes, describe nodes, that will give us our labels. So here, these are all the labels that we can use. For example, if we want to use the failure domain, the zone, then we can also use this. And pod affinity, here we can just change the topology key in the failure domain. This will also work. I only launched in one zone, so you will not see that it doesn't get scheduled on one of the nodes because they are always all in the same zone, but you will see that now they will be scheduled on all the nodes that are in the same region, in the same availability zone. So let's create it again. Let's scale this to 5. kubectl get nodes, all wide, get pods is what I'm looking for. And you see now they are getting scheduled on different nodes because now we are using the failure domain and not the host name. So that's it for this demo. In the next demo, I'll show you how pod anti-affinity works. In this demo, I'm going to show you how pod anti-affinity works. So I'm in the affinity folder, and here I have a pod anti-affinity YAML file. I have again my first deployment, the pod affinity, and then I have a second one, pod affinity 2. That is the same one as the previous one, so it's pod affinity app in pod affinity 1. So this one will be co-located to the first pod. It's the Redis container. And then I have another one, the pod affinity 3, and the pod affinity 3 has pod anti-affinity. And the anti-affinity is, if the app is pod affinity 1, then don't schedule on the same host name. So let's try this one. kubectl create pod anti-affinity. There's a fourth one, but I will first show you the third one, and then I will show you how the fourth one works. kubectl get pod minus all wide. Pod affinity 1 is running on 181. Pod affinity 2, those 3 are running, all of them on 181 because these are co-located. And the next one, the pod affinity 3, also 3 of them are scheduled on another node because they cannot be on the same node as pod affinity 1. So this is all working. This one, pod affinity 3, is using anti-affinity to make sure that it doesn't get scheduled on the same node as pod affinity 1. Let's have a look at the pod affinity 4. So I have one more here. This pod affinity 4 says I have pod anti-affinity. The match expression is app in pod affinity 1 and 3. So this pod cannot be scheduled on a node of the same node host name of pod affinity 1 and pod affinity 3. So if you have a look at kubectl get nodes, we only have 2 nodes here. This is the first node, pod affinity 1 is running on it, and then we have the second node that ends with 46, and we have pod affinity 3 running on it. So pod affinity 4 needs to be not on a node where pod affinity 1 is running and not on a node where pod affinity 3 is running. So there are no nodes because I only have 2 nodes. So if I do kubectl describe pod affinity 4, then 0 out of 3 nodes are available. The first one is the master, so I cannot schedule on that one. And the other ones are, because of the anti-affinity rule, I cannot schedule on any node because it's just not possible. Now, the pod doesn't schedule because we used the required flag. If you have a look, pod anti-affinity.yaml, we used required during scheduling, ignore during execution. So let's say if we change this into the preferred one, what would happen then? I have this already prepared in pod anti-affinity5.yaml. Here we have pod affinity 5 defined. And the only thing that is different here is that I have preferred during scheduling, ignore during execution. You have to give the weight, you have to use the keyword pod affinity term, and then we have a label selector. Expression is exactly the same, app in pod affinity 1 and 3. So because this is anti-affinity, if there's already a pod 1 or a pod 3, it cannot be scheduled on that node because we're using host name as topology key. Let's run this. Kubectl create pod anti-affinity number 5.yaml. Let's have a look at our pods. All white. So this is our 4, it's pending, and this is our 5th, which is running. So you can see it is now running on the same node as our pod affinity 2 because we have preferred instead of required. So it still gets scheduled even though it's not an ideal match. So that's it for pod anti-affinity. So you can play around with it a bit. And if you have any questions, you can always use the Q&A to ask me questions about pod affinity or pod anti-affinity, or if you get stuck somewhere. In this lecture, I'll be talking about taints and tolerations. In the previous lectures, I explained to you the following concepts: node affinity, which is similar to the node selector, interpod affinity and anti-affinity, and the next concept, tolerations, is the opposite of node affinity. Tolerations allow a node to repel a set of pods. So instead of using node affinity to make sure that pods run on specific nodes, this is the opposite. We can say that pods cannot run on these nodes. Taints mark a node, and tolerations are applied to pods to influence the scheduling of the pods. I'm going to talk about taint and tolerations. Taints are applied to a node and tolerations are applied to a pod. One use case for taints is to make sure that when you create a new pod, they are not scheduled on a master. When you run a cluster that has more than one node, the master has a taint. And the taint that the master has is called the node role Kubernetes IO/master, and the type is no schedule. Because this master has a specific taint, you can only schedule on a master when you have a toleration applied to your pod. And by default, you don't apply any tolerations. So by default, you will not schedule on the master, you will schedule your pods on the other nodes. If you still want to schedule on the master, you can add a toleration, or you can remove this taint as well. To add a new taint to a node, you can use kubectl taint. For example, kubectl taint nodes node 1 key equals value, and then colon no schedule will add a taint to a node. You can specify key equals value. The key and the value you can specify yourself. This taint that is applied to the master doesn't have a value, it just has a key, the node role Kubernetes IO master. The taints applied by Kubernetes don't have a value. So at this point, if you apply this taint, no pods will be scheduled on this node 1. This will make sure that no pods will be scheduled on node 1 as long as they don't have a matching toleration. The toleration needs to match this key equals value. The following toleration would allow a new pod to be scheduled on the tainted node 1. This toleration you add to the pod specification. It has the key, the operator equal, and the value, and the effective no schedule. So this matches the previous taint that I created on node 1. So if you would create a pod or a deployment that uses this pod specification, then this pod could be scheduled on node 1. You can use the following operators: equal, providing a key and a value, as in the example above, or exists, only providing a key, checking only whether a key exists. Just like affinity, taints can also be a preference or soft rather than a requirement. No schedule is a hard requirement that a pod will not be scheduled unless there is a matching toleration. Prefer no schedule. Kubernetes will try and avoid placing a pod that doesn't have a matching toleration, but it's not a hard requirement. So it's exactly the same as with affinity. Just the naming is a bit different. If the taint is applied while there are already running pods, these will not be evicted unless the following taint type is used. No execute will evict pods with non-matching tolerations. So if you apply a taint using the type no schedule, then current running pods will not be evicted. If you use no execute, then pods that are already running will be evicted. When using no execute, you can specify within your toleration how long the pod can run on a tainted node before being evicted. Let's say you have a pod with the following toleration. It's the same as the previous toleration, but here the effect is no execute and the toleration seconds is 3600. So this specification will make sure that if a taint is applied to a node where the key is key and the value is value, then this pod will run for 3600 seconds more and will then be evicted. If you don't specify toleration seconds, the toleration will match and the pod will keep running on the node. So if you don't specify these toleration seconds, then it always matches and the pod will just keep on running, just like a normal matching rule. In this example, the toleration will only match for 1 hour, 3600 seconds. After that, the pod will be evicted from the node. So it's a bit difficult to understand maybe. If you specify the toleration seconds, then the pod will be evicted after this time if the toleration matches. If you don't specify toleration seconds and it matches, then it will always be there. It will not be evicted after a certain amount of time. And of course, if it doesn't match, then it will be evicted immediately. Some example use cases are the existing node taints for the master node. As I explained, you don't want to be scaling anything on the master nodes. Those have their own function. Taint nodes that are dedicated for a team or a user. Let's say a team or a user has a specific node that only he or she can use, then you can also use taints. If you have a few nodes with specific hardware, for example GPUs, you can taint them to avoid running non-specific applications on those nodes. Depends what the easiest is for your use case. You can use affinity or you can use the opposite, which is taints. An alpha, but soon to be beta feature is to taint nodes by condition. I'm doing this lecture when version 1.11 is already out and this feature didn't make it, so it's still in alpha now. But in one of the next versions, it will be in beta. So the taint nodes by condition will automatically taint nodes that have node problems, allowing you to add tolerations to time the eviction of pods from nodes. So this is a very specific feature. A node problem example can be that there is no disk space left anymore. So then this node will be tainted and then you can time the eviction of the pod from the node. You can enable alpha features by passing the -- feature gates to the Kubernetes controller manager, or if you are using kops, you can use kops edit to add the following lines. So this feature can be enabled by taint nodes by condition true, but I would recommend you to maybe just wait until this feature is stable and then you can just use this feature. In the next slide, I will show you a few taints that can be possibly added when you enable this feature, and then you can create tolerations for those. So here is an example of toleration that could be used. Toleration If this node alpha Kubernetes IO/unreachable key exists, then the effect will be no execute, so it will evict all the pods on this node. But you can say, I want only to be evicted after 6,000 seconds. Because maybe if you're gonna reschedule a pod, it will take a lot of time. So sometimes it's better to wait some more minutes to be evicted. If it is reachable again, then no work needs to be done. You have the node Kubernetes.io/not ready, a taint that can be applied when the node is not ready. Unreachable, when the node is unreachable from the node controller. Out of disk, the node becomes out of disk. Memory pressure, the node has memory pressure. Disk pressure, the node has disk pressure. Network unavailable, the node's network is unavailable. Currently this is only the host network. Unschedulable, the node is unschedulable. So these are the taints that are applied on those nodes, and then you control the eviction time by using these tolerations. In the next demo, I will show you how these taints and tolerations work in practice. In this demo, I will show you an example of taints and tolerations. Before I start with the demo, let me show you how you can see the master taint. Because as you noticed, when you schedule pods, they are not scheduled on the master. And that is because the master has a taint. So if you do Cubectl get nodes, and we get the master node, that's the second one here. And I do OYAML to output all the YAML. I will pipe it to less, type in, I search for taint. Then this node has one taint, effect no schedule, and the key is the node role Kubernetes IO master. So as long as you don't have toleration on this key, you will never schedule a pod on the master. I have a folder here, tolerations, and here in the README, I have the commands to taint a node. I'm going to taint my first node here, this one here. So I'm going to do Kubectl taint node, the node name, and I'm going to give the taint type equals special node, and I'm going to use no schedule. Then I have a tolerations YAML file. Here we have two deployments. The first deployment doesn't have any toleration, just a normal deployment, 3 replicas, and the second one is also 3 replicas, but it has toleration on type equal special node, effect no schedule. Let's Kubectl create this toleration, and what is going to happen? I'm going to do Kubectl get pod O_wide, so we get the nodes as well. I tainted this node, so only if the pod has a toleration, it will be scheduled on this node. My first deployment that launches 3 pods doesn't have any toleration, so you see it's scheduled on the node where the IP address ends with 160, so it never scheduled on the other node. And the other deployment, the one with the toleration, has 2 pods running on this node that has been tainted. Let me now taint the same node but with a different key. Taint nodes, and then I will just say type 2 special node 2. What is now going to happen? Kubectl get pods O_wide. Nothing is going to happen because I'm still using no schedule, so it will not evict any pods. Let's say that I delete a pod. I will delete this pod here. What's going to happen now? Well, it doesn't match the second taint, so it will not be scheduled on this node anymore. This one is terminated, and now there's a new one, and it has been scheduled on the 160 node and not on this node anymore. I still have 1 pod running on this third node that ends with 6. So let me do another taint, and I will use test key test value no execute, and no execute is different than no schedule because this will evict the pod. So if I use this node name and I press enter and I do kubectl get pods or white, then I now see that the last pod that was running on this node is now terminating and a new pod is now running, but on 160 and not on 6 anymore. So this is how taints work and how you can use tolerations to still schedule pods on nodes that are tainted. And then I also showed you the difference between no execute and no schedule. You can delete the pods again using kubectl delete. To then also remove the taints, you can use the same taint command, but with a minus sign after the key. For example, I did a taint nodes of this 6 node with test key, test value, no execute. If I just do test key with a minus sign, then I remove the taint and now this node has been untainted. So this key is gone. So you need to do that for every key. So type minus and type 2 minus, and then the taints are gone. In this short lecture, I'll be talking about custom resource definitions. Custom resource definitions lets you extend the Kubernetes API. Resources are the endpoints in the Kubernetes API that store collections of API objects. For example, there is the built-in deployment resource that you can use to deploy applications. So I showed this one in the previous lectures. You would create a YAML file, you would use kind deployment to deploy an application. In the YAML files, you describe the object using the deployment resource type. You create the object on the cluster by using kubectl. So resource is like the deployment resource. You create a YAML file using that resource to describe the object, then you put that object on the cluster and you have, for example, a deployment running on the cluster. A custom resource is a resource that you might add to your cluster. It's not available on every cluster. It's an extension of the Kubernetes API. Custom resources are also described in YAML files. As an administrator, you can dynamically add CRDs, the custom resource definitions, to add extra functionality to your cluster. Operators explained in the next lecture use these CRDs to extend the Kubernetes API with their own functionality. So in a nutshell, anyone can create CRDs. Those CRDs you would have to add to your cluster, and then you can create YAML files with these custom resources. So you could, for example, rewrite a deployment object as a custom resource. Then you could deploy your own custom deployment object that might do something different than the standard deployment. And what it does different, that's all up to you, because you can write that. We are not going to write the CRDs ourselves. We are going to use operators, which are going to use those CRDs that are then going to extend the functionality of your Kubernetes cluster, of your Kubernetes API. In this lecture, I'll be talking about operators. An operator is a method of packaging, deploying, and managing a Kubernetes application. This definition comes from the CoreOS.com website /operators, because it's the CoreOS team that actually came up with this method, the operator. It puts operational knowledge in an application. It brings the user closer to the experience of managed cloud services, rather than having to know all the specifics of an application deployed to Kubernetes. Once an operator is deployed, it can be managed using custom resource definitions, arbitrary types that extend the Kubernetes API. I just explained you this in the previous lecture. It also provides a great way to deploy stateful services on Kubernetes, because a lot of complexities can be hidden from the end user. Any third party can create operators that you can start using. There are operators for Prometheus, for Vault, for Rook, which is providing storage, for MySQL, for PostgreSQL, and so on. On a side note, if you're interested, for example, in Rook, which can provide you storage, I have another course on Kubernetes, which is called On-Premise or Cloud Agnostic Kubernetes. It's also available on the Udemy marketplace. And this has a couple of lectures on Rook, which is also using an operator. In the next demo, I will show you how to start using an operator for PostgreSQL. So PostgreSQL is a database. It's stateful, so it's a little bit more difficult to manage. So our operator will help us manage PostgreSQL. If you were just deploy a PostgreSQL container, it will only start a database. If you're going to use a PostgreSQL operator, it allows you to also create replicas, initiate a failover, create backups, scale, and so on. So you see it's similar to RDS on AWS, if you are familiar with that. The operator is acting more like a service on the cloud. An operator contains a lot of the management logic that you as an administrator or user might want, rather than having to implement it yourself. So if you were just to deploy a Postgres container, you would have to implement replicas, failover, and backups and how to scale it. Here, this is already written for you in an operator, and you only have to use the tools around this operator to then be able to use these functionalities. We will use tools that come with this PostgreSQL operator. Here, I just wanted to give you an example YAML extract where you can see that we are going to use custom objects. Here we have a different API version, and we have kind PG cluster, which is a PostgreSQL cluster. This resource doesn't exist on every cluster. You need to create this CRD first, and only then you can create these kind of objects on your cluster. And this PG cluster is a cluster that is managed by the operator, and then this can provide the extra functionality. In the next demo, I will show you how this works. In this demo, I will show you how to use the Postgres operator. You can find the Postgres operator on GitHub. It's not the only Postgres operator that is available. There are multiple ones. Everyone can create an operator for Postgres or for any other database. I took this one because it's quite popular. It has some stars, and also because it has a lot of functionality. So you can create, configure, manage PostgreSQL clusters. You can scale it. You can make replicas. So it's a pretty advanced operator. You can find the official documentation here, which includes getting started. I will show you step by step how to install the operator and use it. And then afterwards, you can maybe check the documentation to see what else you can do with this operator. Maybe some more advanced things. So I'm logged in to my VM, and I will go to Vagrant Kubernetes course Postgres operator. So it's a folder in my GitHub repository. Here I have a README with all the basic commands that you need to launch the operator and to start using it. First, we need to set up a storage. So this is a storage YAML file to set up a storage class with the name standard, type GP2 in the zone EU West 1A. That's where I launched my Kubernetes cluster. So I'm going to kubectl create this storage, and then we can execute a script. So I took this script from this URL. It's from the Postgres operator GitHub. It's a quick start for the Google Kubernetes engine, but you can also use it for other ones. For example, I'm going to do it with an AWS cluster. This also works. So first it tests my kubectl connection, which is working. These are the namespaces that I have. I created the cluster 9 minutes ago. And then it asks if it can be installed on my current cluster, Kubernetes New Tech Academy. I press yes, and this will then start installation. It asks me what storage to use. I will just say standard. There are some errors here. It's in the script somewhere. I'm sure that it will get resolved in one of the next revisions, but for now, there seems to be some replacements that go wrong. But don't worry, it's for example, the storage class that it wants to replace. That's why I added a standard one, because that's a replacement that doesn't work. So for now, you can only use the one that is called standard, because that's what they use. But like I said, I'm sure it will be fixed in the future. Do you want to deploy the operator? Yes. And now it's going to check whether there's already something that exists. Nothing exists, so it's going to install all those objects. So you see here the custom resource definitions are now being created. Then a service account, a role binding, a secret, config map, and then the deployment for the Postgres operator. So the Postgres operator itself is a deployment that will be running, and a service to reach this Postgres operator. And now we need to do a port forward to be able to use this operator. So I'll do the port forwarding in a new window. So now I'm doing port forward of the Postgres operator. So this is unique. If you do this, it will be another string. And now I have port forwarding from a local port to my Kubernetes operator pod. In order to access the PGO CLI, place it within your path from its default location. I made a script, set path, that does it for you. So you can just execute set path. And then you just need to log in and log out. And then you should be able to use this PGO binary. So PGO client version 3.1, API version 3.1. So this only works if you have the port forwarding on, because this PGO client communicates with this Postgres operator. Let's have another look at the README. So we set up the storage, we set up the operator, we enabled port forwarding, we did PGO version to test it, and now we can create a PostgreSQL cluster. We can do PGO create cluster my cluster, which will create a Postgres instance with the name my cluster. So we have a deployment, a service, and there's some labels. Let's use Cubectl to see what is running. So now the container is creating for my cluster. So you can see here we have also the pod for the operator itself. Pod is running, my cluster is being created. This can take some time because the images need to get pulled. Once it is created, we can do PGO show cluster my cluster, and we can do show secrets true to show the secrets, so that we can then connect using PSQL. So we can use Kubectl run IT, so we get a terminal, remove after we execute the Postgres image, which is just an image that you can use that is available on Docker Hub. PSQL tree, well, the tree you can remove, it just PSQL is the name of the deployment. PSQL -h my cluster, this is the host name, -u Postgres, and ask for password. There are 3 users created: the root user, a primary user, and a test user. I'll use the root user, the Postgres. So let's do Kubectl run. I'll just remove this tree, it's not necessary. I put the tree there because sometimes if you quickly want to run it again, then the pod might be already in use, so then you can add 2, 3, 4, and so on. But now I haven't run it earlier, so PSQL as name of the deployment should be fine. I'm going to connect to my cluster. This is going to pull first this Postgres image because this operator is using custom images. This is the official image. And then once I'm connected, I can use this password. If you don't see a command prompt, try pressing enter. Well, if you press enter, we are just providing an empty password. So now if you see this line, this is the time to put your password, press enter, and then you're logged in. I'm now connected to my Postgres server that you can use now in your cluster. That is called my cluster. So the my cluster host you can now use in your cluster. I'll quit from here. And until now, it's not really different than just running the Postgres server image. But the nice things that the operator supplies are the extra features that are difficult to implement yourself. For example, create a read replica. So you can just do PGO scale cluster, scale my cluster, and this will create a read replica. So now you not only have one instance of our cluster, we have 2 instances, and one instance will be synced with the other one. So we have a read replica. Kubectl get pods all wide. So now we have another instance that is being spun up. So let's use watch to wait until it's running. So now it's running but not ready. But in a few seconds it will be ready. So if you now do pgo show cluster, cluster my cluster, then we now see that we have my cluster, but we also now have a replica, my cluster replica, and they are both running. So this one is the primary and this one is the secondary. So now it's possible for us when we do maintenance on our nodes, or there will be a node failure, that we create a replica on another node if we add some more advanced plan to make sure that our Postgres can survive a node failure. In the simple setup that I did, it actually created the cluster on the same node, but you can supply strategies to make sure that, for example, you have a cluster, a Kubernetes cluster that spans multiple zones, and that there will always be a replica in the other zone, so that your cluster can not only survive a node failure, but also an availability zone failure. You can also create a cluster with automatic failover. You can specify that when you create a cluster. Now what I will show you is manual failover. So this, my cluster here is my primary. So I can do pgo failover my cluster query. And it says that I can failover to this target. So now what will happen is it will create a pg task, a failover task that will make my secondary, my replica, the primary. And then when I connect to my cluster, I will connect to this pod instead, the secondary. So let's do pgo show cluster again. And now the other one became the primary. And now what is happening is that because we did a failover, it also created this replica on another node. So now if you wanted, we could do some maintenance on this node, for example. It's still pending. It takes some time to make this one primary, but this is going to happen very soon. This task, this pg task, is also a CRD. So we can do kubectl get pg tasks, my cluster failover minus o YAML to show this YAML file. So this is a custom resource definition. It's a pg task. So if you want to see, for example, all the resource definitions, you can do kubectl get CRD, and you will see that these are the CRDs created by this operator. So this is extending the Kubernetes API, and this allows me to use this API version and this kind. So we have, for example, one for clusters, one for replicas, one for tasks. We can also upgrade our Postgres, and we also have a CRD for this. So this is all custom, and this tool is creating this for us so that we don't have to do it. But with some other operators, you have to write these custom definitions. Let's have a look again. Get pods. So now we have a running pod on a different node. So my cluster xvis is running on a different node and is now, if you do pgo show cluster, it is now the primary and it's running. So this operator provides so much more than just running yourself a Postgres server. This is a really good example that shows you that operators can be very similar to cloud services. If you want to run PostgreSQL yourself on Kubernetes, you might not want to build it yourself, but use, for example, this operator or another one to make the maintenance and the management, the scaling much easier for you. So this is a great example that you should test out. And then, like I said in the operations lecture, there are many more operators available. On the core OS website, you will find some operators, but also just on GitHub repositories, you will find operators that you can use. You just finished the advanced topics section, and this is going to be the next section, the administration section, where I will explain Kubernetes administration topics. The first topic is going to be the master services. I've been talking a lot about the node itself. Now let's have a look at what is running on the master nodes. This is the architecture overview of the Kubernetes master services. On the right, you have node 1 and other nodes that you can have in your cluster. I already discussed those in previous lectures. Let's focus now on the master components. To communicate with your cluster, you have been using Cubectl. Here on top, Cubectl is going to communicate to the REST interface. First, before it can pass this REST interface, it needs to do authorization. Cubectl first needs to authorize and can then only execute commands to that REST interface. Every time you send new resources, new objects to this REST interface using Cubectl, these objects are going to be saved. And Kubernetes uses etcd as a backend, and that's what you see here at the bottom right. When you send a new object, let's say a new pod definition, then that pod definition will be stored in etcd. etcd is a separate technology, and it's just a cluster, a distributed data store that exists often of 3 or 5 nodes. You can also have 1, but then it's not running in high availability. So typically you're going to have 3 or 5. 3 for smaller clusters, 5 for bigger clusters. So all your data in Kubernetes, the definitions, are going to be stored in this distributed data store. So the REST interface is communicating with etcd. This REST API is called the Kube API server. Then you also have a scheduler that communicates with this REST interface. This scheduler is scheduling pods that are not scheduled yet, and this will become pluggable so that you can use whatever scheduler that you want. You can use the default Kubernetes scheduler, or you will be able to plug in some other schedulers. You also have the controller manager, and the controller manager exists of multiple controllers. You can have a node controller, which is responsible to discover new nodes and then manage those nodes. Or you have, for instance, the replication controller, which is managing the replicas of pods if you have those defined. This REST interface then communicates with the kubelets. The kubelets you find on the nodes, so this is the REST interface that communicates with those on every separate node. From a 10,000 foot overview, this is the architecture overview. In the next coming lectures, we will go in some more details about how Kubernetes works and how the administration of it works. This lecture will be about resource quotas. When a Kubernetes cluster is used by multiple people or teams, resource management becomes more important. You want to be able to manage the resources you give to a person or a team. You don't want one person or one team taking up all the resources, for instance CPU and memory, of the whole cluster. You can divide your cluster in namespaces, which is explained in the next lecture, and enable resource quotas on it, which I will explain now. You can do this using the resource quota and the object quota objects. Each container can specify request capacity and capacity limits, two different things that you can specify. Request capacity is an explicit request for resources. The scheduler can use this request capacity to make decisions on where to put the pods on. You can see it as a minimum amount of resources the pod needs. Resource limit is a limit imposed to the container. The container will not be able to utilize more resources than specified. So this is really a limit where capacity is some kind of minimum amount that you put that Kubernetes can then use to schedule your pod accordingly. Also, request capacity is used by mechanisms like the pod autoscaler, which I explained earlier. Example of resource quotas. You run a deployment with a pod of a CPU resource request of 200M. 200M means 200 milli-CPU, or also 200 millicores. I explained this earlier, I just want to refresh this. It's exactly the same thing as I explained in the autoscaling, it's the same principles. So 200M is 0.2, which is 20% of a CPU core of the running node. If the node has 2 cores, it's still 20% of a single core, and you can also put a limit. For instance, you can put a limit on 400 milli CPU. You can say, I want to have the capacity of 200 milli CPU. Maybe you're going to do some scaling based on that, but the container within this pod can only use a maximum, for instance, of 400 milli CPU. Memory quotas are defined by megabytes or gigabytes. If a capacity quota for instance, memory or CPU, has been specified by the administrator, then each pod needs to specify capacity quota during creation. If you, as the administrator, is going to say, I want capacity quota on my cluster, then every pod that needs to be scheduled needs to have this capacity quota defined when the pod is created. The administrator can specify default request values for pods that don't specify any values for capacity. You probably want to specify those defaults because otherwise people might just get an error when they don't specify the capacity quota. The same is valid for limit quotas. So what I just explained is for capacity quotas, but also for limit quotas. If you set limit quotas as an administrator, then you better also set default limits. If a resource is requested more than the allowed capacity, the server API, the Kubernetes API server, will give an error for a tree forbidden, and Cubectl will show an error. The administrator can set the following resource limits within a namespace. You can set a request CPU. This means that the sum of CPU requests of all pods cannot exceed this value. So if you say CPU request is 1 core, then all pods together that are submitted cannot exceed this value. Same with memory. If you say 1 GB max, then the sum of these memory requests cannot exceed this value. Same with the storage. This is about the volume claims. The volume claims cannot exceed this value. And then you have the CPU limits and the memory limits. Same, the sum of the CPU limits of all the pods cannot exceed this value. So people who want to start pods on the cluster will have to specify this limit CPU and limit memory, and the total of these values need to be lower than the total that the administrator is going to set. The administrator can also set the following object limits. You can have limits on config maps, persistent volume claims, pods, replication controllers, resource quotas, services, the load balancers, the node ports, and the secrets. Any limit on those objects, you can say, for instance, I want to have a maximum of 10 pods on a namespace. I want to have, for instance, a maximum of 10 pods within this namespace. So if someone tries to submit an 11th one, then that person will get an error. What exactly namespaces are and how those work, I will explain in the next lecture. And then in the next demo after that lecture, I will show you how to put those limits on a namespace. Let's talk about namespaces now. Namespaces allow you to create virtual clusters within the same physical cluster. Namespaces logically separate your cluster. The standard namespace is called default, and that's where the resources are launched in by default. So whenever we were not specifying a namespace, we were actually launching pods, deployments, and so on in the default namespace. There's also a namespace for Kubernetes specific resources called kubesystem. For instance, our monitoring was launched in kubesystem. The DNS add-on also is in kubesystem. The dashboard is also an example of something that lives in the kubesystem namespace. Namespaces are intended when you have multiple teams or multiple projects using the Kubernetes cluster. You don't need this if you're the only user. The name of the resources need to be unique within a namespace, but not across namespaces. For instance, you can have the deployment hello world multiple times in different namespaces, but not twice in one namespace. You can divide resources of a Kubernetes cluster using namespaces. You can limit the resources on a per namespace basis. So this is what I just explained in the previous lecture. These are the quotas that you can put, and you typically put them per namespace. For instance, the marketing team can only use a maximum of 10 GB of memory, 2 load balancers, and 2 CPU cores. These are quotas that you can easily put in your Kubernetes cluster. First, you need to create a new namespace. You can easily do that using Cubectl create namespace myspace. If you want to list the namespaces, you can do Cubectl get namespaces. This now shows the default namespace, the kubesystem namespace, and the newly created myspace. If you want to set that namespace as a default, so that when you launch new resources, then those will not be launched in default, but in myspace, you can use those two lines. First, you need to get the context with this command. then you can change the context and you can specify that you want the namespace MySpace used in the config. You can then create resource limits within that namespace. Here we have an object of kind resource quota. We have the metadata, we give the name. Here we also have a namespace. We specify our newly created namespace MySpace. And then we have the specifications. We have a hard limit on request CPU, request memory, limit CPU, and limits memory. The request CPU is 1 core, 1 GB of memory. There's a limit on 2 cores and 2 GB of memory. Here is an example where we specify limits on objects. So we can say, in this namespace, MySpace, you can only have 10 config maps, 4 persistent volume claims, 20 replication controllers, 10 secrets, 10 services, and only 2 load balancers. Those load balancers can be interesting because on AWS they cost money for every load balancer that you have. So these are things that you typically want to restrict. In the next demo, I will show you how this works. In this demo, I will show you how namespace quotas work. In my Kubernetes course, I have a folder called resource quotas. And then I have the file resource quota.yml. And in this file, I define a new namespace. I have an object of kind namespace with the name namespace. This will create a new namespace. And in this new namespace, I am going to define resource quotas. I'm going to specify hard limits on CPU and memory and request limits on CPU and memory. I'm also going to supply limits on objects. So let me create these objects. And now what I'm going to do is I'm going to create a deployment. I'm going to create a hello deployment, but I'm not going to specify any quotas, just to see what's going to happen. You see, it's the same deployment that I used earlier. So I'm going to create this one. This is created. Let's have a look at our deployments. I'm also going to add namespace MySpace. We have hello world deployment, desired 3 pods, but no pods running. Let's debug this. Let's get the replication set, also of namespace MySpace, and let's describe this replication set. And it actually says failed to create these pods because the deployment is forbidden, failed quota, compute quota, must specify limit CPU, limits memory, request CPU, and request memory. So when we create a namespace and we specify quotas, when we launch our pods, we have to supply those things. So I'm just going to delete our deploy hello world deployment in namespace MySpace. And let me then show you another YAML file with quotas. Here I have a deployment that says I want to have 200 milli-CPU, there's a limit of 400 milli-CPU, and I want at least half a gigabyte of memory. Limit is 1 gigabyte. Let me create this one. So again, launching in the namespace MySpace. Let me get the pods. And this is interesting. I asked for 3 replicas, but I only got 2. So my pods have been created, but only 2 pods. And if you take a look at the resources, you will see why. It can only schedule 2 out of 3. So now you have a current of 2, but desired of 3. So let me describe this replica set. And it says the first 2 were launched okay, but the third one says exceeded quota. It was requested to have a limit of 1 gigabyte of memory, a request of half a gigabyte. So let's have a look at our quota usage in the namespace MySpace. And let's describe the compute quota, then we see that our limits memory and our request memory is already used. That's why we cannot schedule 3 pods, but only 2 of them. Let's delete this deployment again. And I already told you in the theory that we can have defaults. So let's say that I want not to specify limits during my pod creation, then I can use the defaults. So we can have limits here. Let's create this resource quotas defaults, and let's describe this limits. Let's describe this limits called just limits. So here, this default limit is the actual limit for the container. Then we have right here, these are these limits. This is the request capacity that you put a default for, and this is the limit that you put a default for. And these are of type container. You can also choose to have limits on, for instance, the pods instead of the containers. That is also possible. So then we can still create this deployment, hello world, with no quotas. And what's going to happen now is that it's going to use the defaults. So if you have a look at the pods in namespace MySpace, then we see that we have 3 pods created now because it is using these lower default limits. And now 3 pods are fitting within this limit and are being scheduled on our Kubernetes cluster. So these defaults is very recommended. Then you don't have to specify your limits for every single pod. That's it for this demo about limits. In this lecture, I'm going to talk about user management. There are 2 types of users you can create. A normal user, which is used to access the cluster externally using the API. For instance, through Cubectl. This user is not managed using objects. And then you have a second type, a service user, which is managed by an object in Kubernetes. This type of user is used to authenticate within the cluster. For instance, from inside a pod or from a kubelet. These credentials are managed by secrets. So if you just want to add more users to your cluster, then you're going to use normal users. There are multiple authentication strategies for normal users. You can use client certificates, that's what we use now. Bearer tokens, which is just a token. An authentication proxy, a proxy in between the API, so that you can choose yourself how authentication will work. HTTP basic authentication, just a login and password. OpenID, which is used by Google and Azure, for instance, on the cloud. It's to use a third-party authentication protocol. And webhooks, and here you also can specify your own authentication mechanism. Service users are using service account tokens. They are stored as credentials using secrets. Those secrets are also mounted in pods to allow communication between the services. So that's the volume that you often see. That is just a secret to allow the pods, for instance, to connect to the API server. Service users are specific to a namespace. They are created automatically by the API or manually using objects. Any API call that is not authenticated is considered as an anonymous user. That's why any service, even within the Kubernetes cluster, needs to authenticate themselves. And it uses service accounts tokens to do that. Independently from the authentication mechanism, normal users have the following attributes. They have a username, can be just a string or an email, a UID, user ID, groups, and extra fields to store extra information. After a normal user authenticates, it will have access to everything. To limit access, you need to configure authorization. There are, again, multiple offerings to choose from. You can choose always allow, just allows everything, always deny, used for testing, ABAC, attribute-based access control, and role-based access control. And webhooks, so that you can configure your own remote service that is going to do the authorization. Authorization is still work in progress. The ABAC needs to be configured manually, so RBAC is definitely more promising and uses the RBAC authorization Kubernetes.io API group. This allows admins to dynamically configure permissions through the API. In Kubernetes 1.3, it is still alpha and even considered experimental. It is promising and it will become stable. If you want to know the current state about the authorization methods, you can check out this URL. The next demo I'm going to show is going to show how to use certificates. The authorization part, I will do a demo about when it becomes more stable. In this demo, I will show you how to add users. I'm going to show it using Minicube, but you can also use any other cluster to add users on. I'm going to use Minicube SSH to SSH into my cluster. So this is where the actual Kubernetes cluster is running. And I'm going to create a new key and certificate for my new user. You can find these commands in the procedure document, so you don't have to type them over. First, I'm going to create a new key, edward.pem, and then I'm going to create a new certificate request. And here I specify my login and my group. Then comes the important part. I'm going to use CA certificate and the CA key to create a new certificate that is signed by my authority. And by using it this way, I'll be able to use the certificate to authenticate to the API server. So now I have a key and a certificate. So let me just cat these files. And those I need to copy to files on my host system. So I just logged out. You can use Ctrl D for that. And then kubeconfig has two files that it's using. I can change these to my key and my certificate. I just need to copy paste the contents of the files into those two new files. So this goes into Minicube edward.key or edward.key Minicube edward.key, and then this is gonna contain the key, and then we have the certificate, and this is just gonna be the certificate. So now I have the same files, and if I do kubectl get node, I'm actually using these two files. I can check this using kubectl config view. I still have the certificate authority. I didn't change that one. I have a key, I have a certificate and a key that I'm using for authentication to this API. So that's it. For every user that you want to create, you can just create new keys and new certificates. If you're in a corporate environment, then you're probably going to implement your own way of authentication because you will use something like Active Directory, LDAP. Have a look at the documentation. You can use, for instance, the proxy to implement your own authentication mechanism, and then you can use some corporate gateway to make sure that the authentication is handled. This is perfect if you just have a few users or you don't have already your own authentication mechanism. So that's it for this demo. In this lecture, I'm going to talk about RBAC. In the previous theory lesson, I explained that RBAC is still in alpha for 1.3, but in the meantime, there are a few newer Kubernetes versions that came out, and RBAC is now stable. It is also now enabled by default if you download and install the latest version of kops. So I will now cover RBAC, and then I will do a demo to create a user on kops and then configure RBAC for that user. Let's talk about authorization. After authentication, authorization controls what the user can do. Where does the user have access to? The access controls are implemented on an API level using the Kube API server. When an API request comes in, for example, when you enter kubectl get nodes, it will be checked to see whether you have access to execute this command. There are multiple authorization modules available. You can use Node, a special purpose authorization mode that authorizes API requests made by kubelets. Attribute-based access control. Access rights are controlled by policies that combine attributes. For example, the user Alice can do anything in the namespace marketing. RBAC does not allow very granular permission control, so it's not very interesting to use. RBAC is a better choice. So then we have RBAC, role-based access control, regulates access using roles, allows admins to dynamically configure permission policies. And this is what I will use in the demo. And you also have webhooks, sends authorization requests to an external REST interface. It's an interesting option if you want to write your own authorization server. You can then parse the incoming payload, which is JSON, and reply with access granted or access denied. So we are going to use RBAC of those options, which is now enabled by default on most clusters. To enable an authorization mode, you need to pass authorization mode to the API server as startup. For example, to enable RBAC, you pass authorization mode equals RBAC. Most tools now provision a cluster with RBAC enabled by default, like Kops and kubeADM. For Minicube, it will become default at some point. There's an open issue for this. In the meantime, to get this authorization mode passed, you can use this following parameter: Minicube start extra config API server authorization mode equals to RBAC, and then your Minicube cluster will also be running RBAC. Once enabled, you can add RBAC resources using kubectl to grant the permissions. You first describe them in YAML format, then you apply them to the cluster. First, you define a role, and then you can assign users and groups to that role. You can create roles limited to a namespace, or you can create roles where the access applies to all namespaces. The object role is a single namespace, and the cluster role is cluster-wide. The object role binding is a single namespace, and the object cluster role binding is cluster-wide. So every time you prefix cluster, it's going to be cluster-wide. So here's an example of an RBAC role granting read access to pods and secrets within the default namespace. So this is of kind role, not cluster role. So this is specific to one namespace. Here we define a namespace default. You can then define the main API group. So if you leave it empty, it's the main API group. Resources are pods and secrets, and you can get, watch, and list them. Once you define a role, then you can use role binding to say, I have a user Bob, and that user Bob needs to get access to the role pod reader. Still in the namespace default. If you want to do the same thing, but then cluster-wide, you just change kind from role to cluster role, and then you don't specify namespace. Then you have a cluster role that is cluster-wide, that is over all the namespaces. And then instead of role binding, you use cluster role binding. Everything is still the same, except that here the namespace attribute is not here anymore. So that's it, and then in the next demo, I will show you how to add a user in Kops and give that user permissions. In this demo, I will add a user on our cluster that we spun up with Kops, and I will show you how RBAC works. I have here in my Git repository a folder users, and this one has a readme, and we are going to do the same as we did in the Minicube lecture about authentication. We're going to create a new user. To be able to create a new user, I need to create a new certificate. And to create a new certificate, I need to copy my CA key and my CA certificate from the Kops state S3 directory. So I can do that using AWS S3 sync, and this will sync those two directories. In each of these directories, you have a key and certificate. So I'm just going to move these so they have the file CA key and CA CRT. To create a new SSL certificate, I need OpenSSL. So just make sure that this is installed. I first create a new key for myself. I'm going to create a new certificate request using cn Edward, which is going to be my login. And then I assign this using the CA cert and a CA key. Now I have a key and a certificate, and I should be able to log in to the Kubernetes cluster. To do that, I'm going to create a new context, which means I'm going to create entries in my kubeconfig file. so that I have a new context that I can use that then will use this new certificate. So I'm going to execute these commands, creating a new user using kubectl config set credentials. I'm setting the credentials for user Edward using my Edward certificate and Edward key file. And then I will create a new context using the cluster that I already have. So maybe it makes sense to show you config view, which shows that I have a cluster here with the name Kubernetes New Tech Academy, with the server API Kubernetes New Tech Academy. This is the server I'm referring to. So I'm going to create a new context called Edward, using this cluster, using this user. So if I now do config get context, I will see I have now two contexts. One is my current context that I'm using. If I use kubectl, this is the context and the cluster and the user that will be used to execute commands. It's Kubernetes New Tech Academy, the cluster Kubernetes New Tech Academy, and the user is also that one. Now, my other context has a name Edward and will use the user Edward, still the same cluster. So if I do kubectl get nodes, I will now use still my admin user, which is this one. If I do kubectl config use context Edward, I will use this context. If I do get context, now the star is here, so this is the current context. If I do kubectl get nodes, I get nodes is forbidden. User Edward cannot list nodes at the current cluster scope because I don't have permissions yet. So now I can authenticate, but I haven't set any roles using RBAC, so I have no permissions. Here we are talking about authorization. So I'm going to switch again my context to Kubernetes New Tech Academy, and then I'm going to add admin user.yaml. So here I have a cluster role binding. I'm binding my user Edward to the role cluster admin. And the role cluster admin is a role that already exists. It's just an admin role. So if you want to give someone an admin role, you just do create admin user.yaml. I'm going to switch the context now. kubectl get nodes. And here, now I can execute the same commands as the admin user. I'm going to switch again, kubectl config use context, Kubernetes New Tech Academy. I'm going to delete this admin role. I'm going to add just user.yaml. And I already added those earlier, so let me just delete those. So I'm going to create them again. So now they have been created. User YAML, let me show you what's in there. This is of kind role, which means it's specific to one namespace, and the namespace is default. And on the default namespace, I'll be able, for the resources pods, I will be able to do get, watch, list, create, update, patch, and delete. So here it says pod reader, but actually it should be pod writer because I can also update and create. For extensions, apps, deployments, I will also be able to do get, list, watch, create, update, patch, and delete. Then I bind this role to the user Edward. So here's the role reference. So pod reader, and here pod reader. So it's a bad name. I'll actually change its name after the demo in my GitHub repository. It's actually pod writer, not reader. I mean, you can choose the name yourself. It's just that I didn't pick a great name for this one. So I applied this. Now I'm going to switch my context again. And let's do get nodes, forbidden. Let's now to do get pods, no resources found, which means I can even run a pod. I'm not getting forbidden. It just says that it works. There's just no pods on this cluster. If I now try get pods kube system, no, forbidden. User Edward cannot list pods in the namespace kube system. So now I am contained to this namespace, the default namespace, but it could also be a namespace that you added, like a custom namespace that you have, that you give a custom name. So that way you can contain users two specific namespaces. Give them the roles, only those roles that they need or that you want to give them. So this is how RBAC works. Now that there is RBAC, people are not using any of the old ones anymore. It is also something that you should have on by default. Kops enables it by default. Minicube not yet, but at some point they will also do it. Let's talk a little bit about networking. The approach to networking is quite different than in a default Docker setup. In this course, I already covered container-to-container communication within a pod that goes through localhost and the port number. I covered pod-to-service communication using node port, using DNS discovery, using the cluster IP. External to service using the load balancer, like the external load balancer on cloud. Ingress controller is also an example, or just the node port. In Kubernetes, the pod itself should always be routable. This is pod-to-pod communications. Kubernetes assumes that pods should be able to communicate to other pods regardless of which node they are running. Every pod has therefore its own IP address. Pods on different nodes need to be able to communicate to each other using those IP addresses. This is implemented differently depending on your networking setup. On AWS, it's Kubernetes networking, which is the kops default. Every pod can get an IP address that is routable using the AWS Virtual Private Network, the VPC. The Kubernetes master allocates a /24 subnet to each node. A /24 consists of 254 IP addresses. This subnet is added to the VPC's root table using the SDK. There is a limit of 50 entries, which means you cannot have more than 50 nodes in a single AWS cluster. Although AWS can raise this limit to 100, but it might have performance impact. Not every cloud provider has VPC technology, although Google Cloud and Azure does have something similar, so we can use something very similar on those cloud providers. For other cloud providers, or even on-premise, there are alternatives available. You can use something called Container Network Interface, CNI. That is software that provides libraries and plugins for network interfaces within containers. Popular solutions are Calico and Weave. Weave can be used standalone or with CNI. Or there's another solution called an overlay network. And here Flannel is an easy and popular way. There are also other solutions that I didn't put on this slide, so if you want to have a full list, have a look on the Kubernetes networking page, or just Google for CNI or an overlay network and you will get all of them. Let me just discuss Flannel in a little bit more detail so that you have an idea what it actually does. So here is a Flannel overview, a diagram. The problem that Flannel tries to solve is that, let's say you use DigitalOcean. You have a public IP and you get a private IP, but it stops there. You cannot allocate more IP addresses, but within one node, you still need more IP addresses to allocate to your pod, because your pod wants to communicate to another pod on another node. So basically, you're going to create some fake network. This is what they call the overlay network. You're going to lay a network over the network that you already have. So we have two host IP addresses here, 192.168.0.2 and 0.3. And that's how our nodes can communicate with each other. Our pod also needs an IP address, and here we're going to use some virtual IP address that is going to be managed by Flannel. Flannel also uses etcd as a backend to store its networking information in. So 10.3.1.2, the IP address of our pod of node 1, is going to go to Docker 0, which is the gateway, which is then going to go to Flannel and then to the host IP. And if you would take a look at the packet that is transmitted between host IP 1 and host IP 2, so the one with .2 and the one with .3, is that the packet is encapsulated, because the source and destination always need to be the 192.168.0.2 and 0.3 IP addresses if you want to send a packet from point 2 to point 3. You cannot communicate the IP addresses 10.3.1.2 or 10.3.2.2 over this real network. So those are encapsulated within this packet. So that encapsulated packet goes then to the host IP, Flannel 0. It actually gets to a normal packet again. and goes then all the way to the other pod. So Flannel acts as a network gateway between the nodes. So you're going to have an overlay network so that you can assign each pod with a unique IP address that is not really known by the real network. That's it in a nutshell. So if you're going to deploy your Kubernetes cluster on-premise, on cloud, but not AWS, Azure, or Google Cloud, then you might need Flannel. For instance, for DigitalOcean, you need an overlay network. You can use a CNI like Calico or something simple like Flannel. Often when you're using some launch scripts that are going to deploy your Kubernetes cluster for you, those launch scripts will include the configuration for software like Flannel. But it's still very good to know that this exists and that you might have to implement it yourself if you're doing, let's say, a manual setup. This lecture will be about node maintenance. It is the node controller that is responsible for managing the node objects. It assigns IP space to the node when a new node is launched. It keeps the node list up to date with the available machines. The node controller is also monitoring the health of the node. If a node is unhealthy, it gets deleted. Pods running on the unhealthy node will get rescheduled. When adding a new node, the kubelet will attempt to register itself. This is called self-registration and is the default behavior. You can do manual registration, but self-registration is obviously more handy. It allows you to easily add more nodes to the cluster without making API changes yourself. A new node object is automatically created with the metadata, a name, IP or hostname, and labels. For instance, the cloud region, availability zone, and the instance size. A node also has a node condition. For instance, it can be ready, it can be out of disk when the disk is full. When you want to decommission a node, you want to do it gracefully. You just don't want to shut it down immediately. You want to instruct Kubernetes to move first all the running pods away from it. So you drain a node before you shut it down or take it out of the cluster. To drain a node, you can use the following command: kubectl drain and then the node name. And you can also pass a grace period, so a period that it will take to gracefully decommission it. If the node runs pods not managed by a controller, like a replication controller or replication set, but if it's just a single pod, then you need to force it, because those pods will then be lost. In the next short demo, I will show you how drain works. This is going to be a short demo where I'm going to show you how to drain a node. I'm going to show this on our Minicube cluster. We only have one node, so I'm just going to drain that one. So kubectl get node. We have one node in the ready status. Let me just schedule something. We're just going to create our hello world deployment. So let me get the pod list. So all three pods are running on one node. Now let's do drain, and our node name is Minicube. The name Minicube comes from get node. So these pods are all going to be removed and cannot be rescheduled. So I'm just going to use force. And if I do kubectl get node, then we can see that scheduling is disabled. We don't have any pods running on it anymore. They're all pending because they cannot schedule on it anymore. If you would try this on your AWS cluster, launch with kops, you would see that these nodes then run on a different node. So that's very simply shown how drain works and how you can use it when you need to put a node in maintenance. In this lecture, I'll be talking about high availability. If you're going to run your cluster in production, you're going to want to have all your master services in a high availability setup. This setup looks like this. You're going to cluster etcd, at least you're going to run 3 etcd nodes. If you just run one and etcd fails, then Kubernetes is not working anymore. So you need at least 3 ones for high availability. You're going to replicate your API service with a load balancer. And you're going to run multiple instances of the scheduler and the controllers. Only one of them will be the leader, the other ones are going to be on standby. here is an overview of the etcd clusters that are typically run. You can run 1, you don't have high availability. You can run 3, this is a typical setup. Or if you start getting a really big cluster, then you're going to run 5 etcd nodes. So this is then how the architecture looks like with high availability. If you take a look at the top left, kube control is now going to connect to a load balancer. So are the Kubernetes nodes. They're also going to connect to this load balancer. This load balancer will then go to the REST interfaces on either master 1 or master 2. Typically, if you're going to go for high availability, you're going to want 3 nodes. Every node is unique, so you just have to spin up multiple master nodes with the same image or the same software. The REST API will communicate with etcd, not shown on this graph. But then you also have the components that make changes to the API, like the scheduler and the controller manager. You can only have one active scheduler and one active controller manager. That's why on master 2 and on any other masters, you will see that they are grayed out. They are on standby. You then also have a kubelet installed on your masters, and you can also have monit, which will then monitor kubelet. A cluster like Minicube doesn't really need HA. It's only a 1 node cluster. If you are going to use a production cluster on AWS, kops can do the heavy lifting for you. If you are running on another cloud platform, have a look at the kube deployment tools for that platform. kubeadmin is a tool that is in alpha, but is very promising that can set up a cluster for you. If you are on a platform without any tooling, have a look at this URL to implement it yourself. In the next demo, I will show you how to modify the kube setup to run multiple master nodes. In this demo, I'm going to show you how kubes can run multiple masters. I'm logged in here in my Ubuntu Xenial box, and you can add some arguments to kubes to run multiple masters. Have a look at this command, for instance. Kubes create cluster, then we have the name, the state, which is S3, and then the zones. You can actually specify multiple zones. This is going to make it a little bit more complex when launching volumes, because pods that use EBS-backed volumes, they need to be launched in the same zone. But Kubernetes labels your nodes, so you can easily use node selector when running pods. You will have therefore a cluster that spans multiple zones. Still the same region, but multiple zones. You can increase the node count, or you can leave it at 2. If you leave it at 2, you will launch only in 2 zones. If you increase it to 3 or more, you will cover all 3 zones. The node size is still the same, the master size is still the same. DNS zone is Kubernetes New Tech Academy, but then here, master zones. So here you specify 3 master zones, which will mean that you have 3 masters running, 1 in each zone. So I'm going to go ahead and create this cluster, and then it's going to preview the changes that it will make. What I'm going to do is, I'm just going to show you the configuration of what is going to happen. So here we have the node configuration, the instance groups. So you see here, min size 2, max size 2, T2 micro, and we have 3 zones. If you still only want to launch your slave nodes, you could just remove B and C here. Then the master nodes, let's say master EU1A, is going to be our first master of size 1. Then we're going to have a second master EU West 1B, and then we're going to have a third master. So even if a full zone fails, our master will still be working. And if your cluster spans multiple zones, then your cluster will also be able to still keep on working even if one data center of AWS completely fails. So that's it for this demo. As you can see, kubes has ways to edit the configuration file, to make custom changes, and to make your own custom cluster. In this lecture, I will explain you how to use TLS on an AWS Elastic Load Balancer. You can set up cloud-specific features like TLS termination on AWS load balancers that you create in Kubernetes using services of type load balancer. So let's say that you create a service using a YAML file. This is of type load balancer. Then you can specify some cloud-specific features if you are on AWS to, for example, terminate TLS on the load balancer so that you can use HTTPS instead of HTTP for your application. You can do this using annotations. This is an example YAML file of a service, and you can see here in bold that you can add annotations, and you can add specific annotations to turn on some flags to enable TLS and to do some other configuration. In this lecture, I will go over the possible annotations for the AWS Elastic Load Balancer, the ELB. In the next lecture, I will show you in a demo how to configure a certificate and how to enable then that certificate using the annotations. The first 4 annotations that I want to show you are all used to enable access logs on the load balancer. So when you have a load balancer, you can have access logs on them. So every time someone visits your app, every time there's a hit on the load balancer, then a line will be written to a log, and this log you can push to S3. You can configure this in the AWS Web UI, but here, when you launch it as a service, you should configure it as an annotation. And these 4 you can use to specify the interval, which is the first one, to enable it or disable it, just to enable the logs, which should be then true. You can specify the bucket name and the bucket prefix to where you want to log to. You also have to configure some specific permissions on your bucket if you want to make this work. So make sure to also have a look at the documentation in AWS if you want to configure something like this and you haven't done it before. You can simply add resource tags, key value pairs, to your load balancer to then identify them later. You can use this annotation to add tags to your load balancer. This annotation specifies the backend protocol to use. So the backend protocol is the protocol that your pod is using. Most often this will be HTTP. So the backend protocol will be HTTP, which is default. If you want to encrypt everything within your cluster as well, it's possible that you enable HTTPS within your application, and then you would have to change this from HTTP to HTTPS. For most use cases, this will be HTTP because you are already within your cluster, traffic is already private. You often just need to enable HTTPS on your load balancer. And that will be the point where you terminate TLS. AWS Load Balancer SSL certificate. This is the certificate ARN. So this is a string, a unique string that you have to put there. And that string is a unique identifier for your SSL certificate. That's what I'm going to show you in the demo. AWS Load Balancer connection draining enabled and AWS Load Balancer connection draining timeout. That this is connection draining. It's a timeout when the backend node stops during, for example, scaling. And then how long are you going to keep this connection open so that clients who still have a connection to that node can terminate their connection. They can receive the content from the app, and then the next request, they will just go to another node. So this is important when you have scaling so that people don't get an error message when suddenly a node becomes unavailable. Then the connection timeout. This is the timeout between the load balancer and the backend. Cross-zone load balancing. Let's say that you have a Kubernetes cluster that is deployed over multiple zones, and then you have a load balancer in front of that. Then you can also enable cross-AZ load balancing. So one load balancer can then have an incoming client from one zone and can still route your request to another zone. This can be interesting, for example, if you only have one node in one zone and 5 nodes in the other one, so that the load balancer would still load balance over all the 6 nodes over multiple zones. And then the AWS load balancer extra security groups in case you want to add extra security groups to your load balancer. If you want to make your load balancer an internal load balancer, you can set the ELB to internal load balancer using this annotation. So you can set the value to true, and then the AWS load balancer will become an internal one. It will not have a public IP address anymore. You can enable the proxy protocol. So if you want to enable the proxy protocol for this load balancer, you can use this annotation. And you have the AWS load balancer SSL ports, what listener to enable HTTPS on. Default to all, but typically if you only want to enable HTTPS on your HTTPS port, you would only say 443. And that is the HTTPS port. So then the load balancer will enable HTTPS on the SSL port, which is 443. In the next demo, I will use this annotation and some other annotations to show you how to terminate TLS on the load balancer. In this demo, I will show you how to use TLS on AWS ELB. The first step before we can enable TLS on our Elastic Load Balancer is that we need to create an SSL certificate. In AWS, you have the AWS Certificate Manager. And this certificate manager allows us to create a new certificate that we then can attach to our load balancer. So this is the AWS Certificate Manager. You need to make sure that you are in the correct region. I'm here in EU West 1. And then I'm going to provision a certificate. So I'm going to click Get Started. I'm going to request a public certificate. And then I will use my domain name that I'm hosting in Route 53 because that's easier to then add the host name. I'll call this one Hello World. And then my domain name that is hosted using Route 53, Kubernetes New Tech Academy. I click Next. I will choose for DNS validation. Choose this option if you have or can obtain permission to modify the DNS. This is the easiest way. You can also choose for email validation, but then you have to make sure that your email addresses work. So DNS is the easiest. I'm going to click Review. Hello World, Kubernetes New Tech Academy. All correct. Confirm and request. Pending validation. So I need to add these records first. So this is the name, it's type C name, and this is the value. And because I have Kubernetes New Tech Academy hosted on Route 53, I can click this button, Create Record in Route 53. You will only see this button if this host name, Kubernetes New Tech Academy in my case, is hosted on Route 53. I click this button, and then I click Create, and then it will create the records for me. So if I have a look at services, Route 53, I'll open it in a new tab. The DNS record was written successfully to your Route 53 hosted zone. So let's go to my Route 53, hosted zones, Kubernetes New Tech Academy. And then here I have this C name that has been added. If you don't have Route 53, you have to add this manually yourself. So name, C name, and then the value. This will take some time to validate. And then after maybe 5 to 10 minutes, maybe even 30, you get status issued. This is the ARN. So this is the ARN that you could then use in your YAML file. So this is a unique ID that you need. So let's create our load balancer. In my Kubernetes course GitHub repository, I have a directory ELB-TLS. And here I have two files. I have the Hello World YAML file that just contains a deployment, one that we used earlier already. And then we have the Hello World service. And here I'm going to use these annotations. So the first change I need to make is this one. It's a cert. I need to here paste my ARN that points to the certificate I just created. The backend protocol is HTTP because the communication between the load balancer and my pod is HTTP. My Hello World deployment is not on HTTPS, so this still needs to be HTTP. The SSL port that I want to use, this is the listener of my load balancer, is 443. So port 80 will not use SSL. So it's important to set this, otherwise Kubernetes will just put SSL on every single listener. I also enabled connection draining, and connection draining is 60 seconds. So if a node gets deleted, it will keep the connections still live for another 60 seconds. And I also add two tags, environment equals dev and app hello world. These will be tags added in AWS. Then I have two ports that will be added to the load balancer, an HTTP port on port 80 that will go to my deployment, and an HTTPS port on 443 that will also go to my deployment. So it will connect to the Node.js port of my Hello World app So it's encrypted to the load balancer, and then TLS is terminated, and then it will go over plain text to my pod, because then I am in my internal network. I don't need SSL or TLS in my internal network. So that's it. I save this. I do kubectl create of hello world.yaml and of my hello world service.yaml. And this will then create a new service that you can then get the hostname of using all-white. And now that we have this hostname, we should also add the DNS name hello world Kubernetes New Tech Academy, so that we can connect on that hostname rather than this one. Let's do that first. So I'm going to go back to root 53. Let's go to root 53. Hosted zones, my Kubernetes New Tech Academy, and let's create a new record set. It's going to be hello world. It's going to be an alias. You can also use CNAME, but alias is easier because this will just show us the ELBs that are available. This is my ELB. Let's check that in another window. Services, EC2. And here we have load balancers on the left. So we only have one load balancer. So this is correct. We do create. And now we have hello world Kubernetes New Tech Academy that points to our newly created load balancer. So we now should be able to use this hostname, and they should then go to this load balancer here. Let's have a look at the configuration of the load balancer. We have two instances. These are our nodes. The master node is never used. We only schedule pods on the node itself. They are in service, that means that they are healthy. And then let's have a look at the listeners. We have two listeners, an HTTP listener on port 80, an HTTPS listener on 443. And this one uses our certificate. And then we also have our tags. There are some tags that are added by Kubernetes, and we have the tag app equals hello world and environment equals dev. So those we added. So this should all be working. Let's test it. Back to our terminal. kubectl get services all white shows us this host name. Let's test the HTTP connection first. Replies hello world. Let's try HTTPS. And this works, but it says certificate subject name hello world Kubernetes New Tech Academy does not match target host name. And that's why we had to create this DNS name hello world Kubernetes New Tech Academy, because this needs to match, because our certificate needs to match before we can use this. Curl of hello world Kubernetes New Tech Academy shows us no warning and shows hello world. Same if we do it over regular HTTP. So that's why we need this extra configuration. We need to use a host name, otherwise it will give us a warning. We can also ignore the warning with curl, that's -k, and then it will still work. In a normal browser, it will ask you whether you want to proceed. So this is how you can configure and add TLS certificates on your load balancer, and then you can terminate encryption on your load balancer, which is a great way to manage your TLS and SSL certificates, because there's almost no management of this. AWS will manage and renew your certificates. I am now going to talk about admission controllers. An admission controller can intercept requests sent to the Kubernetes API server. For example, when you create a new pod, a request will be sent to the Kubernetes API server, and this can be intercepted by an admission controller. This interception happens after the user is authenticated using a token or certificate or any other way of authentication, and authorized, for example, using RBAC, and before the object is persisted, saved in the backend. And the backend is basically etcd. Admission controllers can be enabled by the administrator. They are typically added at cluster creation by passing an argument to the Kube API server. So when you launch a Kube API server, Then you can add the enable admission plugins, and you can specify a list of admission plugins that you want to enable. By default, there are already quite a few enabled, which I will go over in the next slide. And in the next lecture, I will explain you one that is currently not enabled by default, but an interesting one that you should enable. This default list is specific to a Kubernetes version. Newer Kubernetes versions will have a different admission plugin list because there are always new admission plugins coming out. When using kops, it can be configured using the YAML configuration or with Minicube by passing an argument after Minicube start. I have this documented. You will see that later on in a demo. Here is a list of admission controllers. These are enabled by default in the Kubernetes version 1.16, but then in later versions, you will see that it might change. So for example, the first one is the namespace lifecycle. It enforces that no new objects can be created when a namespace is in the terminating state. So when you delete the namespace, this admission controller makes sure that no new objects can be created. It will intercept these objects and make sure that these are not created when the namespace is in a terminating state. Then you have the limit ranger. Using the limit range object type, you can set the default and limit CPU memory resources within a namespace. The limit ranger admission controller will ensure these defaults and limits are applied. So you can apply defaults and limits of CPU and memory resources within a namespace, and then this admission controller will make sure that these are applied when you create a new object. Then you have the service account, which implements the service account feature, and you have the default storage class. If a persistent volume claim is created and it doesn't specify any specific storage, then this admission controller will add the default storage class to the persistent volume claim. This is mainly to avoid that a user using the cluster needs to know the storage types. So if it doesn't specify a specific storage type, then the default storage class will be injected. Then you have the default toleration seconds. Sets a default toleration in seconds if not explicitly defined by the pod specification. So this has to do with the tolerations, where I have also lectures on if the default toleration is not set, then this admission controller can set this for you. Node restriction makes sure that the kubelets that run on every node can only modify their own node and pod objects. So only those objects that run on that specific node. And then you have two interesting ones that are used a lot: the mutating admission webhook and the validating admission webhook. And the mutating admission webhook, you can set up a webhook that can modify the object being sent to the Kube API server. The mutating admission webhook ensures that the matching object will be sent to this webhook for modification. So you will run some program, this is called a webhook, in a pod somewhere within your cluster, and then you can make sure that whenever an object is created, it first goes to your program, to your webhook, and then maybe it will make some changes, maybe it will inject a container, and then that will then be persisted to the cluster. So if you want to inject, for example, a container for every pod that is being created, you would use the mutating admission webhook. And this is exactly how Istio, for example, is injecting its sidecars. And then you have the validating admission webhook, which is similar. You can set up a webhook that can validate the object being sent to the Kube API server. If the validating admission webhook rejects the request fails. So for validation purposes, you can then validate whatever specification that is being used within a pod, for example. If you don't agree with this specification, you can reject the request and then the request will fail. The pod will not be created, for example. And then you have the resource quota. We'll check incoming requests to see if it doesn't violate the constraints defined in the resource quota object in a namespace. So again, this admission controller can then make sure that the resources are checked so that it doesn't go over a specified quota. And this pod security policy is not enabled yet by default in Kubernetes 1.16, but it might be enabled in the future. And this one enables you to control the security aspects of the pod creation and updates. So for example, privileged, non-privileged. And I have a separate lecture on this admission controller. So the mutating admission controller and the validating admission controller are actually quite interesting because they are very flexible and they allow you to extend yourself the webhooks, because you can write your own software, your own mutating webhook or your own validating webhook that will then modify the pod specification, for example, or validate the pod specification. So here's an overview of how the mutating and the validating admission work. You have a request coming in to the API HP handler. So this is the Kube API server. A request can be, for example, when someone does kubectl create of a pod. So that is a request, is sent to the API server. Authentication and authorization needs to happen first. Once the user is authenticated and authorized, then the mutating admission invokes the webhook, which can be a custom piece of software that might mutate the request. Then you have the object schema validation. Validating admission might add some extra validations, and only then it is persisted to etcd. And when it's persisted, it might actually have added, it might have modified your object, it might have injected a container, for example. So that's it for admission controllers. And then in the next lecture, I will talk a little bit about the pod security policy admission controller. Pod security policies. Pod security policies enable you to control the security aspects of the pod's creation and updates. For example, you can deny using privilege mode in pods. So if someone then starts a pod using privilege mode, the pod will not be scheduled because it's not allowed to run a pod in privilege mode anymore. You can also control what volumes can be mounted. For example, can it use a config map, a secret, or is that denied? And then an interesting one, make sure containers only run within a UID/GID range, or make sure that containers cannot run as a root. So you can add this extra layer of protection to make sure none of your containers can run as a root. Or then even specify that particular pods have to run within a certain UID/GID range. So UID is a user ID and GID is the group ID. So basically you can influence what user ID and GID in Linux in the container needs to be used. The pod security policy is an admission controller that can be enabled at cluster startup. The pod security admission controller will be invoked at pod creation or modification. So when you create a pod or modify one, then it will check whether you are allowed to run this kind of pod, and if not, it will not get scheduled. It will determine whether the pod meets the pod security policy based on the security context defined within the pod specification. So basically, if you enable privileged mode, but you're not allowed to use it, the pod will not be scheduled. The pod security policy admission controller is currently not enabled by default in Kubernetes 1.16. It probably will be in the future. In the next demo, I will show you how to enable it and create a pod security policy to implement some extra security controls for new pods that are then created. You will typically need at least 2 pod security policies, one for the system processes because some of them need to run privileged or as root, and then one for the pods users want to schedule, which should be tighter than system policies. For example, deny privileged pods. And that I will show you in the next demo. I will now show you a demo of the pod security policies. In the Kubernetes course Git repository, there's a directory pod security policies. And here there's a README, pod security setup, that you can follow to use for either Minicube or kops. In case of Minicube, we need to create this .minicube files etc Kubernetes add-ons directory, and then copy this initial PSP.yaml as an add-on so that it will be launched at boot. And then we can start Minicube with extra config, and then here we say API server enable admission plugins, and all these plugins that are enabled by default plus the pod security policy. This is for Minicube. I will be using kops. For kops, we do a very similar thing. We do the Kube API server append admission plugins pod security policy. So it will just append this to the default list, and the default list is actually all these admission plugins. So in kops, it's a bit easier. We also don't need to copy this initial psp.yaml because kops will create itself an initial pod security policy, because you need a pod security policy by default for the system processes. So in case of Minicube, we need to create this ourselves. And in case of kops, it will do that for us. So let's start with kops. So I'm going to create a new cluster, same command as we've been using earlier. And then I'm going to edit my cluster. Kops edit cluster, the cluster name and then the state. And then I have the specification here. And then from the README, I'm just going to paste this. So make sure that the Kube API server has the same indentation as API. And then it's going to do append admission plugins pod security policy. I'm going to save this, and then I will be able to do kops update cluster --yes and my state. And this will then launch the cluster. Will take 5 to 10 minutes, which gives us time to go over these YAML files. So now the cluster is launched. We'll wait a couple of minutes. And then let's have a look what's in this directory. I already went over the README. We have the initial psp.yaml and we have the restricted psp.yaml. So these have the pod security policies. Let's have a look at the initial PSP. We don't need it for kops, but if you are using Minicube, it's interesting to know. And it's also something that kops will do for you. So it's also interesting to know what kops will do for you. Here we have an object of kind pod security policy. And this one is privileged. So this one will be actually the one that will be used for our system processes. In the specification, we will then specify what pods are allowed. So for the privileged pod security policy, we want to have privileged true. Pods can be privileged and also not privileged. Allow privilege escalation true. Allow all capabilities. You can run as any user ID. So there's no restriction. And then we'll have a new policy. The pod security policy restricted. And here we will say that we cannot use privileged pods. We will not allow privilege escalation. And we'll also define what volumes can be used. And we also cannot use certain capabilities, like using IP tables and networking and stuff. We don't want our normal users to be using that. We also require that the container must run as non-root. And that's interesting because I will show you if we try to scale a pod as root, it will not work. So also here, supplemental groups ranges between 1 and 65,535 to make sure that we cannot use root. So basically we can also not say when we mount something, use this UID root because it will also be denied. To make this all work, we are going to use a cluster role. So here we see that the PSP privileged will then have access to the policy, pod security policy use. So it will be able to use the privileged group, the one that we just created higher. So this makes sure that we have in the cluster role that can use this pod security policy, the privileged pod security policy. And then we create a second cluster role, and this will be for the restricted pod security policy. And then we can bind the cluster role to groups, service accounts, and users. So here we see then we have two role bindings, a cluster role binding here and a role binding here. This one is for the restricted one. So if you are authenticated, you automatically get the restricted cluster role. That means that you're authenticated. It's a default role from now on. It will only be the restricted one. You will not be able to use privileged pods. But then there's a role binding for the namespace Kube system. If you are in the Kube system and you are in the group system masters, system nodes, or you're in the group system service accounts Kube system, then you will get the cluster role PSP privileged. So that's how then the Kube system gets more privileges to then run the privileged pods. And when we log in as a normal user, we will have this cluster role binding, which lets us only use this cluster role here, which only lets us use the restricted resource. And the restricted resource is then defined here, the pod security policy restricted. If you then go to the top, this here, this privileged one, is defined by kops itself. So kops will define this privileged one. So we don't really need to define this. It's only when you're using Minicube. Minicube currently doesn't do it by itself. So then you need this initial PSP. So I also split them out. So this restricted pod security policy, the cluster role, and the cluster role binding are in this file restricted PSP. So then if you are using kops, we can apply this restricted PSP.yaml. And also something that I forgot to mention, make sure that you're using 1.16. It's still in alpha right now, but I'm sure it will be stable when you see this lecture, because the stable version will come out soon. Only from 1.16, this admission controller is available by default. Not enabled by default, but available. Let's have a look at the pod security policies. Let's first see if our node is running. Not yet. We'll have to wait a little bit longer. Now it is available. So I'm running version 1.16.2 because I'm using kops 1.16. Let's have a look at the pod security policies. Kubectl get pod security policy. So like I said, we have this default one, the kube system, which is privileged and is used by the kube system processes. So let's add the restricted PSP. Otherwise, we will not even be able to scale anything because we haven't assigned a pod security policy for the default user. So we need this restricted PSP. And then we have two pods, a bad pod and a good pod. Let's have a look at the good pod. This is deployment, simple deployment of an HTTP echo service that I have, and it will respond with the hello world text when you go to port 8080. But that's irrelevant. We are just going to check whether we can run it or not. We add security context run as user, and this is UID 100. So it needs to run as this UID. It's non-root, so this should work. And if we have a look at bad pod, then we see here security context run as user 0. And this one should not run because this one tries to run as root. So let's try that out. Kubectl create. Let's try first bad pod. Let's have a look. Get pods. No pods found. Let's have a look where it went wrong. The deployment runs, but the replica set, well, the deployment, you can see it's also not ready, but it has been created. The replica set says there's one desired, but there's nothing running. And here we'll actually find a logging. So if you do kubectl describe replica set of this replica set, error, creating pods. This pod is forbidden, unable to validate against any pod security policy. Invalid value 0, running with the UID root is forbidden. So it actually works. We cannot run with the UID root, but let's now try to run with another UID. Let's try to run the good pod. And let's have a look with kubectl get pods. And then we see container creating running. So that works. So the good pod works, the bad pod doesn't work. So we achieved what we wanted. There's just one little thing I will have to note here. That is that we had to say here, security context run as user 100. If we remove this, it will also not work, even though that in this container we specify that we are not running as root. And why is that? If we run it, it will actually tell it. Kubectl delete good pod, and then let's create it again. I made a mistake here. I'll just remove this. I see it already. This needs to be, there needs to be an array here. So now it should work. But is it also created? No, it says create container config error. Let's have a look. Describe pod. So now it pulls the image, and then when it pulls the image, it's going to check whether it runs as root. But what do we get here? Error, the container has the run as non-root, and the image has a non-numeric user. app cannot verify user is non-root. So actually there's a limitation. There's a limitation, unfortunately, that if in the Docker file you say user app, because we are using user app here in Docker file, I can actually show this to you. So this is the Docker file. This is the Docker file of the HTTP Echo repository. So then here you see at the bottom, it will run as a user app. But user app is not a UID, it's actually the name. And Kubernetes cannot see whether app has not a UID 0. Because we could easily create here the user app with UID 0. Then it would still be an admin user, the root user, it would just not be called root. So it actually wants that you say user 100 or you use the security context to make sure that Kubernetes can see that it's really a non-zero numeric value. Just having user app will not work for the security context. So what I did is I pulled this container, logged in, typed ID to see what is the real ID of this user app. It has 100, then you can use in the pod security context 100 to make sure that you can run this pod. Because otherwise you will then get this kind of error. It cannot verify the user is non-root. So that's also something that you want to take into account when using this admission controller and this pod security policies. So that's it for this lecture. This is quite new as we speak, but it will definitely become the default in Kubernetes. And then when you want to securely run pods, you'll have to make sure that they run as non-root, non-privileged, and so on, so that your containers are more secure running on your cluster.